Hello everyone and welcome to this session on Artificial Intelligence Full Course. AI is a technology that mimics human intelligence, allowing computer applications to learn from experience via iterative processing and algorithmic training. AI applications are already having a huge impact virtually on every industry, and they are also likely to continue growing in importance as new applications and technological solutions are created. AI engineers are the need of the hour in many MNCs. In this session, you will learn all about artificial intelligence. So let's check the agenda for this session. We're going to start with the overview of artificial intelligence, and then we are going to talk about the difference between artificial intelligence, machine learning, and deep learning. Moving further, we'll talk about the artificial neural network, the deep learning frameworks, and multi-layer perceptron. After this, we will talk about the popular algorithms, KubeFlow tutorial, and pre-processing and feature engineering. To sum up this session, we are going to talk about artificial intelligence developers and artificial intelligence interview questions. I hope you are clear with the agenda, so without any further ado, let's begin. Before we begin, subscribe to Intellipaat and don't forget to press the bell icon to get more updates.
Hey guys, welcome to Intellipaat. In today's world, artificial intelligence has revolutionized how we approach and solve problems. It is not only a skill that you need to have to get a highly paid job, but it's also to build something really cool. Artificial intelligence is an extensive, large field and it's very difficult to wrap your head around all the concepts that are involved in it. It's difficult to get past through the jargon and the terminologies associated with it. Keeping that in mind, we have come with this YouTube video on artificial intelligence. This video will teach you everything that you need to know in artificial intelligence as a beginner. Before we start, please do subscribe to Intellipaat's YouTube channel to not miss an update. Now, let me walk you through the agenda for today's video. First of all, we start to know what artificial intelligence is brief history and introduction. Then we move on to key major points in the history of artificial intelligence. Furthermore, we'll understand what an artificial intelligence algorithm is, whether it's supervised or unsupervised, and then we'll go on to the world of deep learning. Furthermore, we'll also like you to understand what is an artificial neural network, the topology of an artificial neural network, and perceptron, and many more. Then we take a closer look into one of the most popular tools used in your AI platform, your TensorFlow and your PyTorch. Going further ahead, we go into the details of your TensorFlow, learning concepts like tensor, computational graphics, feed-forward neural networks, multi-layer perceptron, and backpropagation. Last but not least, we make our own facial recognition program using computer vision and most of the popular tools in AI. Now, if you guys want to become a certified artificial intelligence professional, we recommend that you read through the description that's below. We at Intellipaat provide all courses of artificial intelligence covering up all major concepts. Thank you very much. Now, let's continue with the session.
One important aspect comes into picture when we talk about artificial intelligence. It is the year 1956, guys. Well, pretty much in the year 1956, the term artificial intelligence was actually coined. Well, how did this actually come to happen? I mean, a lot of us might actually know that it was coined at the Dartmouth conference and so much more. But what exactly is this conference? Well, in 1956, for a couple of years, basically, there used to happen, there used to be meetings and a couple of meetups where a lot of scientists and researchers used to come together under one roof. And this eventually was called the Dartmouth Conference. And here, basically, what started out as a summer research project, and it lasted about 8 weeks. And at the end of it, the product of their research and the product of basically their entire project was one person who coined out the name what is artificial intelligence, and it has ever been stuck with us right back from 1956, right? So I hope you got the Lord of the Rings reference there. So it's one conference to rule them all. It's basically one ring to rule them all if you haven't got that. And coming back to the presentation, so even after 64 years of the term being coined by Mr. John McCarthy, he is regarded as the father of artificial intelligence, guys. Even after 64 years, the world is still going mad, still going gaga about artificial intelligence when you think about it. Well, especially in the last 10 years, right? I mean, everyone is on the trend of artificial intelligence, and it's just gonna go like this for the next couple of decades is actually what analytics tell us, guys. So here's a quick excerpt that I read. Pretty much this is from the person called as Daphne Koller. She's a scientist at the Stanford Artificial Intelligence Lab, and she says that John McCarthy believed in artificial intelligence in terms of building an artifact that could actually replicate human level intelligence. Replicating a human human is pretty much the toughest thing that even these big scientists could ever think of. And this was thought about way back in the 1950s as well. And she says that he was very happy with a lot of artificial intelligence today, because at the end of it, it is not replicating the human level intelligence that it was actually sought out to be. And it is said that he wanted artificial intelligence to pass something called as the Turing test. Well, if you guys know about the Turing test, just head to the comments section and talk to your fellow viewers and let them know about the Turing test. And if you cannot hold on to the curiosity, give me 2 or 3 more minutes. I'm going to tell you what the Turing test actually is, guys. So on that note, we need to check out what artificial intelligence actually is. So let me give you the breakup of the textbook definition, guys. Well, the definition goes like this. It's the theory and the development of computer systems, basically, which are able to perform tasks normally, which actually requires a human to do the task. It might be something as visual perception, speech recognition, decision making, and translation between multiple languages as well. Well, that definition will make sense if you actually go through it twice. I mean, this is the textbook term, right? So I usually keep all the sessions very simple for all the viewers, from the beginners to the advanced level, guys. So, you can have a lot of takeaway from it if we actually, go about simplifying certain things for you. So, the current goal of artificial intelligence, if I have to put it in one picture, is basically to tell you that it is just mathematics on steroids, guys. Because when you think about it, all artificial intelligence is trying to achieve is better ways and faster ways to do something that a human can do. A lot of terms like machine learning, deep learning, and come into the picture when we talk about mathematics as well. Because at the end of the day, to achieve artificial intelligence, we use so many concepts which involves a lot of mathematics and implementing this mathematics using code, guys. And at the end of the day, it's mathematics plus programming which will actually lead to us achieving cognition, guys. So what about the future? Well, again, achieving cognition has always been the goal, even it's been the goal of the person who actually coined the term as well, and pretty much every one of his followers and everyone who wants to do something with artificial intelligence pretty much can tell you about how important and how amazing it would be to actually achieve cognition. Well, by cognition, I actually mean that getting a machine to replicate what a human can do exactly the way the human does, or even do it better as well, guys. So what do you guys think about it? What do you think in the future, what do you think artificial intelligence has a grip in the future? So head to the comment section and do let me know there. So then you might have heard of these terms, as I mentioned, right? Machine learning, deep learning, and so much more. Well, guys, I would love to explain all of these to you guys, but we've already put out a lot of videos on our YouTube channel, and we have amazing subject matter experts writing out blogs for us as well. So if you want to know more about these terms, machine learning, deep learning, or how they are used to achieve artificial intelligence in general, I suggest you head to our YouTube channel after this video, and then you can go about checking our blogs as well. But hey guys, make sure you stick till the end of the video, because I'll help you fast track your career to become an artificial intelligence engineer, and I'll be giving you a special coupon just for the viewers of this video, guys. So on that note, let us quickly check out the timeline of what artificial intelligence was, what it is now, guys.
Now, if you guys want to become a certified artificial intelligence professional, we recommend that you read through the description that's below. We at Intellipaat provide all courses of artificial intelligence covering up all major concepts. Thank you very much. Now, let's continue with the session.
Let us head back to 1943. Well, it was the time of World War II, guys. It was almost ending, and pretty much this person is the reason, in my opinion, why World War II ended. I am a major history buff, and I believe personally, and many people agree with me, thousands of people agree with me when I say this, Mr. Alan Turing, who was a British mathematician, was the person who ended the world wars, because the Germans used a very nice coding system which was called as the Enigma, and they used to use that to send messages, and well, the Allied forces never got to know what these messages were because they were all encoded and they just look like rubbish. But Mr. Alan Turing developed the first artificial intelligence machine. He went about using a lot of mathematics, a lot of formulas. It took a lot of days, months, and years to go about cracking this amazing encoding system, which was basically generated by the Germans to go about sending their messages, guys. There's also a movie on that, so if you could watch that, it would be pretty nice as well. So this person, alongside breaking the Enigma, also it was called the Turing machine, basically, and then he invented something called as a Turing test. Well, what does the Turing test do? Well, I just told you 3 slides back that I'm going to explain it, right? So here it comes. So basically, consider this scenario that you are a human and you obviously are humans, right? So basically, you're just sitting in front of your computer and you're asking a couple of questions to random people around you. And instead of saying it as random, let us consider 2 situations. One, your questions are being seen by a computer, and the other, your questions are seen by another human. So whenever you ask these questions, if you cannot figure out the difference between the answers that the computer can give and the human can give, I mean, if the answers are equally good where you cannot tell apart between the computer answer and the human answer, that particular computer which answered for you has passed the Turing test, guys. So that computer is intelligent enough to pretty much give you answers just like a human, and it can do a damn good job at it, guys. So this particular test, this sets the bar for an intelligent machine, let's say, because if a computer can fool someone into thinking that they're actually talking to another person, then we can say to a certain extent that pretty much that computer has achieved enough cognition, because it is pretty much going about, let's not say pretend, but it's trying really hard to replicate a human, and it's doing a good job at it as well, guys. So fast track to 1956, again the term was coined there, and scientists begin to tackle the concept. They were like, okay, now the term is set, let's work on it. And one of the top scientists, his name is Mr. Marvin Minsky. So basically his view, along with McCarthy's view, got him very good funding from the then American government, United States government, who basically hoped that with the help of artificial intelligence, it will actually give them an upper hand in the Cold War, which was ongoing back then, guys. So pretty much Mr. Marvin Minsky along with McCarthy actually got good funding from the government, and they went about doing that as well, guys. So this another important thing happened in 1956 was Mr. Marvin went about starting the artificial intelligence laboratory at MIT, guys. And this lab, right from 1956 all the way till 2019 and 10 years from now, has been punching out amazing solutions to the world's problems, and it has been the most efficient laboratory in terms of artificial intelligence that the world has ever seen. And there are very intelligent people, and very much a force in these people which drive them towards achieving artificial intelligence, is what I can tell you, guys. And then again, a quick fast track to 1981. Well, 1981, artificial intelligence actually got commercialized. So this person called Mr. Ken Olsen, he is the founder of Digital Equipment Corporation, guys. So basically here he realized that, as a business leader, we can actually, start making use of artificial intelligence and start selling artificial intelligence to the common folk as well. And then fast track to 1997. This was one of the most important key moment, in my opinion, back in the 90s regarding artificial intelligence, because this was the first time there was a chess tournament conducted between the grandmaster Garry Kasparov. He was a world champion multiple times in chess. He actually played against IBM's Deep Blue. Deep Blue is basically their then supercomputer, and then Deep Blue actually defeated the world's best chess player at that point of time, guys. And people were saying that IBM's Deep Blue could actually think like God, because it was evaluating over 200 million moves in the game of chess at once. So for every move, it could bring up 200 million combinations of how you could go about playing. How amazing is this, guys? This is still 1997, and then artificial intelligence was already on the roll, and people could say it could think like God. I mean, that is a huge statement, and every time I go about reading about Kasparov or Deep Blue, I am amazed by the fact that this actually happened. In fact, multiple tournaments happened. You can probably read about it after the video, guys. And then fast track to the 21st century. We are finally at 2002, guys. I'm sure most of you might have heard of Roomba. Well, Roomba is a company, pretty much, it's from iRobot. It's basically a carpet cleaner, and it's a vacuum cleaner, guys. So it's a robot vacuum cleaner. So, in my opinion, again, this was another big achievement, because all it took was just few layers of behavior generating systems, which basically guided this machine around your house, around your living space, and it could efficiently clean carpets and floors autonomously without your help. And this has been sold across the world as well. There is 15 million units sold, and I use pretty much Roomba every day. So it basically has a docking station where it comes out of its docking station. It cleans our living room. It goes into the bedrooms. It cleans the bedrooms, and pretty much it just comes back, knows where its docking station is, and just goes back, charges, comes back again 2 times a day. You can program all of these, and it is an amazing thing, guys. It doesn't even sometimes it starts doing it at the middle of the night, and I'm taken aback. Basically, you can set all of that. You can set the timings of which your robot actually starts cleaning and all of that. But it's actually amazing to know there is an autonomous system that I personally use to get my housekeeping stuff done, guys. So they've sold about 15 million units of these across the world, and that number is rising as well. And then coming to the maybe not so nice part of it, in a couple of people's opinion, but in my opinion, again, another amazing use of this is in war machines, guys. So many autonomous war robots were pretty much deployed to Iraq and Afghanistan. In fact, 2000 plus robots which are capable of war, everything from helping our soldiers carry heavy loads, diffusing bombs which would be a threat to the life of the soldiers, patrolling enemy area, till all the way till they could make a stable war robot which is capable of inflicting heavy damage on the opposition forces, guys. Well, this is good in terms where our forces or any country's armies, navy or military forces are not put into immediate danger. Well, if the robot pretty much is shot dead or whatever, if it's malfunctioned or something, or if it's taken a lot of damage during the war, there is no human life lost there, and that is the important thing. That is the good thing. Well, the bad part of it is if this pretty much keeps on going, then every superpower, every nation who's a superpower will want to go about hoarding these. And then, I pray to God there isn't another big war coming. But if there is, then we will, see a lot of these war robots, guys. That's the sad part of it. And I'm sort of confident it really won't come to that. But if it does, then you can see a lot of robots there, guys. Let's just pray it doesn't come to that. Well, the next important thing in between the robots and the Tesla autopilot actually came about Google's self-driving car, guys. So I'm not sure if you guys know about Google's self-driving car, but instead of just telling you what the self-driving car is, I just thought of telling you the Tesla autopilot directly, guys. Here, basically, this was the biggest breakthrough in terms of artificial intelligence technologies, because Tesla, as a company in the United States, co-founded by Mr. Elon Musk, started providing cars to the public where the car could drive itself throughout. It could park itself, and all you had to do is basically sit in the car, and every 15 minutes or so you had to hold the steering to make sure that you're not sleeping or something. So how amazing this is this. There is a photo on your screen right now on the top right, if you can check it out. That is an actual photo from the car's dashboard, guys. So it basically instead of having a huge speedometer or something, it has this amazing display where it shows you, it detects all the cars around it, it detects rain, it detects the shortest distance, guys. You have to read about Tesla's autopilot, and I'm sure many of you guys will find it fancy, guys. In my personal opinion, if this is brought throughout the world, the capabilities of self-driving, that would be an amazing thing, guys. We've already seen a lot of companies actually bring out parking aids and autonomous parking, and it's basically called as parking help or whatever it is. A lot of companies like BMW, Skoda, and Mercedes, and all these big guys have already had autonomous parking capabilities. But when you think about when you think about how it goes about in every country, I'm sure it's very different. But then when you again contemplate about it, if this was brought to every country, it would be amazing, right? And then coming to 2019, guys, I mean, it's one more month to the end of 2019, and one amazing thing happened this year is pretty much in the field of medicine with respect to artificial intelligence, guys. Well, because artificial intelligence, as we all know it, has been helping the world in many different ways, and it has done so in the field of medicine as well. Well, it can be used to ameliorate reading time for digital breast tomosynthesis while maintaining or improving the accuracy of the reading. Well, what it's basically trying to tell us is that artificial intelligence is basically helping us to accurately make sure we detect cancer cells early on, guys. So this, again, we already know the victims of cancer, and we already know that it is an uncurable disease, and it takes a lot of time, endurance, patience, and so much more to go through with this, guys. But then if artificial intelligence can help us to check out what cells are harmful, what cells are harmless, basically what cells are benign, and so much more, then definitely this would help, right? Well, it has actually, the research has already been done. It is being implemented in many countries, and as a part of an artificial intelligence researcher, I am extremely proud of the fact that we've brought artificial intelligence down to the field of medicine, guys. So on that note, we need to check out what's next. We've seen all these different fields, and I'm sure there are hundreds of fields that I could have put in here due to the shortage of time, and pretty much to keep it to the scope of this tutorial for all of our viewers, I had to cut it down, guys. But take a second, head to the comment section, and let me know what you think about the views of artificial intelligences, and what are the other applications that you find amazing, guys.
Now, if you guys want to become a certified artificial intelligence professional, we recommend that you read through the description that's below. We at Intellipaat provide all courses of artificial intelligence covering up all major concepts. Thank you very much. Now, let's continue with the session.
So on that note, we need to quickly check out what are the types of artificial intelligence, guys. If we keep diving into the depth of these, then it might actually go out of the scope of this video. So let me quickly tell you what are the types of artificial intelligence. Well, we have three different types of artificial intelligence, guys. One is narrow AI, next is general AI, and then super AI, guys. With narrow AI, it's basically, it is the concept which is meant to, assist or take over specific tasks and do it better than a human would do. Basically, an example of a narrow AI would be pretty much your mobile phone assistants, right? It can be Siri, Alexa, Cortana, and so much more. So you just make your work easier. Instead of opening the calendar app, setting your calendar, all you do is say, hey Siri, set my calendar for so and so. So that again is a very good example of narrow AI, guys. Coming to general AI, it's basically taking knowledge from one domain and transferring this exact knowledge into another domain. Well, general AI will almost require the intelligence of a human. If it will not require more intelligence, but you have to match the intelligence of the machine with a human or something very close to that. Well, a good example to give you about this is, when you think about it, it's it's usually very advanced level of chatbots. I mean, sure, Siri, Alexa, all these are amazing chatbots. And then general AI is again a lot of mathematics involved here as well. A very good example would be AlphaGo and so much more, guys. So AlphaGo is basically again another computer which beat the world champion at this game called Go. I wouldn't say it has the cognition level of a human, but pretty much, even though it sounds simple on the outside, it is actually very complex. And even the world champion said that this is the most intelligent Go player that I've ever met in my life. So that brings us to super AI, guys. Super AI is on another level, guys. This is I would say artificial intelligence, mathematics, programming, all on steroids at once. Because when you think about it, super AI consists of machines that are extremely smart compared to humans. They can outrun a human, outthink a human, outgun a human, and so much more. For either good or bad reasons, super AI is pretty much either in good terms or in bad terms, guys. I've never seen neutral sentiment about super AI, but for the scope of this video, all you need to know is that super AI is pretty much the domain which consists of machines that are extremely smart when you compare it to humans, guys. So on that note, we need to quickly talk about what is the cause for all of these intelligence, guys. So what makes artificial intelligence intelligent? Well, in my personal opinion, the art of training a machine is amazing, guys. When you think about it, you can go about showing your computer images of cats and dogs and asking it to classify it for you. I mean, from our childhood, we have been trained by either school or by family members or friends to know what a cat looks like and what a dog looks like, but your computer does not. It might have taken you 3 years to figure out the differences, or 1 year to, let's say 1 year, you took 1 year to figure out the differences. Your computer will probably take 5 seconds or 10 seconds to figure out this entire thing what took you 1 year, guys. So when you think about it, everything from a very simple cat dog classifier all the way till achieving cognition, in my personal opinion, is just art, guys. Because at the end of the day, taking a concept which does not exist and bringing it right up to the level of a human being, and in a lot of people's personal opinion, human beings are the most intelligent species out there right now. Well, unless there are aliens and all the conspiracy theories. Well, jokes apart. Well, coming back, bringing a machine up to the level of a human is definitely achieving cognition, and it's being done right, guys. So we need to think about the challenges we face when we go about making artificial intelligence intelligent, guys. there are four important points which pose as challenges. One is knowledge, guys. Because again, when you think about it, when you have to train a machine to figure out stuff on its own and hold these and implement it later is very difficult. This brings us to the second point. Well, holding it, if you think getting your machine to hold information and to make sense of it is difficult, then think about learning, because you can learn at a rapid pace, at a slow pace, or whatever it is. But getting your machine to learn, getting your machine to understand about a new concept, contemplate about it, work with it, analyze it, store it, and use it later is something very difficult. And this brings us to the next thing, which is problem solving. Even though you got your machine to have all the knowledge and learn very easily, it needs to go about implementing all of these in a perfect way, guys. Well, it can have the knowledge of all the worldly things which goes by, but what is the use if it cannot solve a problem? Because again, all the artificial intelligence terms or whatever points towards artificial intelligence mostly is a problem, right? Anything in the field of military, medicine, or so much more, we give the developers, the researchers, the scientists a problem so that they can solve it for us easily using artificial intelligence, right? So if your machine cannot solve a problem, then it is pretty much no good, guys. And this is actually very tough to achieve as well. And next comes obviously cognition, as I've been telling you for so many times right now, because again, bringing your machine up to the human level is again a very daunting task, guys. And in the middle of this, let me give you a very quick fun fact. I'm sure most of you guys might have heard of it already. Artificial intelligence has been used in terms of litigation, litigation and law and court and so much more as well. How? Well, I'm sure you guys have heard of JP Morgan, right? They are the banking giants of the world, and they came up with an artificial intelligence model which basically was used to go through and analyze some legal documents. You wouldn't believe the numbers, and the first time I read this a couple of months ago, I was taken aback, guys, because when you think about it, it reduced the workload from 360,000 man hours to a matter of seconds. Think about it, 360,000 hours of job. This is what it takes a human to do it. But as soon as they implemented that model, it just took the model a couple of seconds to do it. And I have read that the model is very accurate as well. So when you think about it, think about the odds, 360,000 hours and a couple of seconds. So, if you didn't know this fact, then I hope you find this very entertaining, and I hope you guys feel very interested about this fact at the same time, because we already know artificial intelligence is being used in every field, but not many of us know how it was actually used in litigation, right? So I just found it very interesting to tell you guys about that. And this brings us to the dark side of artificial intelligence. Well, is there a dark side? Well, you remember Elon Musk, right? The founder of Tesla, the founder of SpaceX, the founder of SolarCity, and so much more. He's basically a billionaire entrepreneur, guys. Well, he says that, at least when there's an evil dictator, that human is going to die. But for an artificial intelligence being, there will be no death. It will live forever. And you will have an immortal dictator from which, you can never escape. So I am sure our views on this particular topic, we can debate about it all day, all night, and we're going to have very different opinions about this. And we need to respect people with very different opinions about this, because at the end of the day, all of these, what we look at as different opinions actually come under one umbrella, and it helps develop artificial intelligence in the right way, guys. So I hope there is a good in fact, I am sure that there is a good way and a good path for the development of artificial intelligence, but you can never know at any point of time. Well, according to a lot of experts, that it might take a turn for the bad as well. Again, let's hope that it doesn't go there. And on that note, we'll quickly bust a couple of myths and facts, guys. So the myth is that superintelligence by the year 2100 will be inevitable. Well, when you think about it, it might happen right now, it might happen in a decade, in a couple of years from now, or it might never happen at all. To achieve super intelligence, again, as we've been talking, is a very, very, very challenging task, guys. And the myth is that, only people who do not know about Luddites are basically people who are not very well informed. That only these people are worried about artificial intelligence and all of its bad things for the future. Well, not exactly, because even many top artificial intelligence researchers are concerned about how it's going to go about in a good way or in a bad way as well, guys. Another myth is that artificial intelligence is turning evil, it is turning conscious, and so much more. Well, the actual worry that we need to go about doing is, artificial intelligence actually turning to be very competent with a goal that would be misaligned with our particular goal. So it might take a very staunch deviation from what we set it out to be, and it could do something on its own. So that is the actual worry when you compare to the myth. And then to bust another couple of myths, people say that robots are being the main concern, like those Terminator movies and whatnot. Well, again, here as well, misaligned intelligence is again the main concern, because we live in a world of technology. In every device, every home, I'm sure most of the world is connected through an internet connection, right? So you will not need an actual robot in case if something goes wrong as well. So that is something to think about. And then artificial intelligence cannot control humans is a myth. Well, intelligence actually enables control. So we do this very sad thing where we trap animals in cages and create zoos around them. I mean, I'm not much of a zoo fan. I hope I do not offend anyone regarding that. So we are smarter than tigers and all of these other animals, so we can go about controlling them because we are smarter. Now think about a machine which is smarter than humans. It can go about controlling us as well, right? So that is a fact to think about again. So machine cannot have goals. Well, this is wrong, because again, let us say two planes are fighting in the air. It's called as a dog fight. So two planes are fighting, and the plane behind just launched a missile. If you have seen in a lot of movies that I'm sure you would have, this missile exactly knows where the plane is and to go hit it. This basically works on the concept of heat seeking. Well, it has detectors in the front of the missile which will find the hottest thing it can see and then just go hit it. So the hottest thing in a plane is, in the plane which is in front is its engines. So this will basically chase the plane's engines and hit the engines. So that is a heat-seeking missile for you. And then the next mythical worry is that super intelligence is just years away. Well, not really. It is a couple of decades away, as I've pretty much told you. But again, it might take way longer than 2 decades, 3 decades, 4 decades, and so much more to just to make it safe for us to use as well, guys. So that is all with the dark side concepts that I had to just inform you guys in case you weren't knowing. So this brings us to the next concept, which is basically the domains in which artificial intelligence has its hold, guys. Again, number one, as I've been saying for a long time, is healthcare, guys. That is the best thing that I've seen artificial intelligence being put to, and there are so many things live as well. So it has been so subtly integrated into your lives that you would not even know it is there. When you think about it, probably you just open a health app installed on your mobile phones or your computers. You'll be talking to a chatbot instead of a human, and you wouldn't know it. Most of the time, you can just set an appointment with your doctor and ask more information about your appointments and so much more by just talking to a machine instead of talking to a human on the other side, guys. And from that till helping detection and curing of cancer is again an amazing thing in my opinion. And the second thing is stock trading, guys. As an investor, personally, I could sort of relate on this as well, because if stock trading again is a very tipsy-turvy world, right? So sometimes you lose money, sometimes you make a lot of money. But if you had if you had a different approach, if you had a more intelligent being to look at graphs, to look at data, and to make better sense of it than an expert trader, then that would be an amazing thing, because you could end up making more money and losing less money at the same time, right? So this brings us to another next thing, is sales, guys. Well, this is a personal recommendation from me, because here at Intellipaat, let me tell you how we implement machine learning and artificial intelligence for our sales team, guys. So we get about 10,000 or 15,000 sales leads every single day. Imagine calling those 10-15,000 people, guys. So it would be a daunting task to go about doing it, but we have a machine learning model which is in place, which basically helps filter out these people, categorize them, and make sure it basically makes sure that they get in touch with our course advisors, and then later our course advisors basically help them get the course that they were actually looking for, guys. So this makes the entire process of going through the part of sales very interesting, very simple, and we get lot of analytics from that as well, guys. So this is us at Intellipaat using artificial intelligence to help out you learners as well, guys. So that brings us to my final thoughts regarding artificial intelligence. So you might have this question at this point of time: will artificial intelligence take over the world? Well, when you think about it, since we are the most intelligent being right now, it is as good as we are, because if we are extremely good at programming, our artificial intelligence model will be extremely good as programming. So it totally depends on us and how good we are. Unless machines start writing code and they can write it better than us, right? So until we go there, we are the most intelligent beings we know, and then artificial intelligence will be as good as we are, guys.
So before we even begin, right, what does artificial intelligence mean? With respect to artificial intelligence, right, basically what we are trying to achieve is that, of course, in the current situation, in the real world scenario, I mean, there is nothing that is more intelligent than a human, right? But humans tend to process and think in a certain way that, obviously, from the history we know that it is beneficial for us, right? Because we have brain, we have things like brain cells, neurons, and so on. So we process, and we are naturally intelligent, right? So but the machines, usually how the machines work is that you have to like give the input, and you would get a certain output, right? So basically what we are trying to achieve with artificial intelligence is that making them, like someone just quoted, we are trying them, or we are training them to mimic how a human thinks and become more intelligent, in the sense that, let's say, you train your computer, you train a machine. Tomorrow it shouldn't be like waiting for your input, it should act on its own. So that's what we are trying to achieve, and that's what artificial intelligence also means. Basically, artificial is, obviously you're trying to create something synthetic, and the intelligence is the quotient, the thinking quotient, or the action quotient. Okay. Yeah, so we'll see where all artificial intelligence is used. So these are widely used in banking and finance, for predictions. For example, today in the banking world, right, I don't even have to like call people and so before they use this campaign strategy called spray and pray, wherein they just call a random 1,000 people and say, if you want to have like if you want to take a loan and so on, right? Now what happens is that I have a machine learning model, and now it will just pick the right candidates for me to call, so that I don't waste my time. So if 1,000 people, calling 1,000 people take about $1,000 and 5 hours, in order to reduce my cost of acquiring the customer and also reducing the time, I would simply pick the customers that have high propensity or probability to convert, right? So that's where machine learning kind of helps in the banking industry. And of course with medical science, I think we are also in this COVID situation, right? So many of the machine learning, especially the CNNs, right, that helps in processing images right now. Doctors also, and big hospitals, even India, they have started to implement some sort of image learning models to basically look at x-rays. So basically what happens, how the process is that when a patient comes in, they would just put him through an x-ray. If he comes with certain COVID symptoms, they'll just put him through an x-ray, and this x-ray is fed to a machine, and this machine will tell if he has to go to this entire process of seeing the doctor, being admitted, and so on. So what basically this machine does is, internally they use like a ImageNet or a CNN. At a high level, it's a CNN, convolutional neural network, that reads the image and see if it has like this probability of being COVID or not, right? So based on that, even hospitals, right. So if you look at it, right, doctors don't have to waste time like looking at each patient's x-ray and so on. So we can focus upon patients who actually need the attention, and not waste time on like all for example, you can also have like a very common cold that could actually be very similar to the COVID symptoms, right? So basically, like, it will help categorize patients that require immediate attention. Basically, we are seeing it in the current situation. So it's also used for heavy industries. Will, for example, right, there's a concept called robotics, right? So machines are used to perform certain tasks that can be automated and so on. There also, AI is being used, of course, also in air transport right now. So there is a mechanism, or there's a concept or technology that is called a TCAS in airplanes. So basically, when two airplanes are in the same path, the probability of their collision is high, right? So what this does is, this understands the path, this understands the probability for collision and so on. And what it does is, it will send signals to each of these planes, asking one plane to move higher and asking one plane to move lower. So those kind of things are also those are also some of the applications of artificial intelligence. And again, in gaming, I think many of us would have played all the recent high graphic games. Intelligence again is being used there, right? So these are some of the overall, at a high level, these are some of the major applications. And these are something that we have our hands around, right? So you'll notice all of this in the real world, so when you're interacting with your environment, right? Okay, so this is the actual definition behind artificial intelligence. It's a field of computer science that emphasizes on the creation of intelligent machines which can work and react like humans. Basically, this is the part that we are trying to achieve. How can we ensure that the machines work and think like a human, right? Okay, so the one that I'm pointing at, the third image. Okay, so what's so special about this car? Why is it famous? Autonomous. Okay, correct. So we use a technique called so there are two techniques involved, obviously. Correct, reinforcement learning, and the input for the reinforcement learning is basically like image processing acts as the actual input. So this car drives by its own. And how many of you guys are aware of this humanoid? This is basically a robo, right? How many of you guys know its name? This humanoid has actually done many bit of public appearances and also has been in multiple debates with humans. So that's the kind of intelligence that we are currently achieving right now. So basically letting a robot think of its own, come up with arguments, and she's started giving like public appearances on TEDx and so on, of course. And then you have like drone. So if you I mean, one of the key technologies that the current US Army has is this UAV, right? Unmanned aerial vehicle. So what it does is basically it hovers over your enemy's territory, and if it identifies that the enemy is armed or something, it tries to, I mean, give signal to the other weapon system, and it will try to bomb that area without even like, I mean, humans interfering in its actions. So that's how some of these things are like really intelligent. Intelligent, I would say, intelligent machines that have been created. Of course, autonomous vehicles are also coming to India, so we'll have to probably see how it works in India, given our traffic systems aren't that efficient when compared to something like the US or other Western countries. Okay, all right. Yeah, so these are the things that actually makes the humans intelligent, right? So the reasoning, let's say, I mean, someone is asking, hey, why are you even doing some of these things that you're doing? Why are you learning machine learning? Why are you learning deep learning, right? So what would be your answer? You will say, hey, I mean, I have so much data, I'm trying to apply certain techniques so that it makes my work easier and I'm able to analyze the data, give insights and so on. That's what you call as reasoning, right? So intelligence actually is an encompassment of all of this. It involves everything. And then comes linguistic intelligence. For example, humans have this tendency to understand context better than a machine, right? So for example, Apple, right? You have Apple as a brand, you also have Apple as a fruit. So when I say organic apple, I know that apple here, when I use it with words like organic, I know that it's a fruit and it's not a phone or a brand anymore, right? So that's the kind of linguistic intelligence that we have. Then is the problem solving ability. I mean, everyone has a problem solving ability, right? So I mean, from the childhood, people are like, I mean, we've been solving a lot of problems knowingly or unknowingly. Even for that matter, when you first start crawling, that itself is a problem because you tend to fall down, then you correct yourself, then you start walking, then you start running, and so on. So then is the perception. For example, each one will have a different perception. Their understanding could be different, and sometimes how this can help. That's why we tend to work as a team, right? So each one, given a same problem, 100 people will think in 100 different ways, right? But when you average all of that, right, so you get a better solution. So that's why perceptions are important. People having different perceptions, working, collaborating together and solving a problem is more efficient than 1% just solving the problem. And again, intelligence obviously is learning, because intelligence is developed through continuous learning, right? So that's what we are trying to achieve through the machines as well. We feed them the data, we try to ensure that they are fed with the right quality of data, with the right set of or amount of data, with the right features and so on, right? So so that's how we also tend to program the computers to become intelligent like humans. Yeah. So this is the actual growth of the market for artificial intelligence, if you think about it, right? So the evolution in the last 20 years. In the 1990s, there was this special phenomenon called the internet boom, wherein every company wanted to be on the internet, like something like Yellow Pages, right? But right now, the focus is going to be more on AI, crypto, blockchain technology, and so on. So this is how the pace has been growing. Of course, this is quite exponential, right? Plotted instead of like a bar graph, but as a point line, you'll see it's quite exponential. So right now, the market is at about 60, I think, about 16,000. But in the next 4 years, it's going to about quadruple, right? It's going to go 4 times, right? So that's the growth that people who are transitioning into like a data scientist can actually tap on, right? So right. So how many of you guys actually think AI, machine learning, deep learning are all the same? Okay. So artificial intelligence is more like an umbrella term. I mean, sometimes I've seen people. So I've seen people many times use all of these in invariably, right? So people tend to use. People tend to say that I'm using artificial intelligence, or say something like I'm solving a problem with AI tech and so on, right? So they use all of these terms interchangeably, but there are certain differentiating factors. Like someone just quoted, artificial intelligence is more like an umbrella term. So ML, DL, RL, everything comes under artificial intelligence, because
If you want to make a career in data science, then Intellipaat has IIT Madras Advanced Data Science and AI Certification Program. This course is of very high quality and cost effective, as it is taught by IIT professors and industry experts.
the objective that we are trying to achieve here is to ensure that the computers learn, right? So that's AI. Okay. So again, AI, of course, it can be split into ML and DL. I mean, you can associate these two things in like one very simple way, right? So use machine learning when there is like not there's not enough, or there's not much of data, right? But when you want to do certain things like with large amount of data, we tend to move towards deep learning. Also, I mean, with machine learning, you can solve, I would say, at least to 90% of what we are not 90%, but maybe to 70% of an extent we can solve all the problems. But that may not be enough, right? Because with deep learning, you're using multiple layers, and the deep learning, we'll see during the due course, but you'll see that deep learning is more sort of like mimicking our human brain itself. So we have layers, those layers have perceptrons, neurons, and so on, right? And then we apply certain functions and it works in a certain way. So with machine learning, the other problem is that usually, right, we tend to solve linear tasks with machine learning. For example, if A tends to X and Y tends to B, we'll say that this will give me like a Z, right? But with deep learning, there are certain complexities that you can I mean, that you can use it to your own advantage. If I'm processing a image, right? If I'm processing, like, let's take this example of Tesla itself, right? With machine learning, I obviously can solve some of these image classification problems, but not to an extent that DL can do. So deep learning, with more data, deep learning kind of like improves. But the problem with ML is, even with more data, it kind of like stagnates after a certain time. Think of it more like a sigmoid curve or a logarithmic curve, right? So after a certain point in time, it will start to converge. It will not go beyond a certain level. But with deep learning, more data, the curve is actually kind of sort of I would say, exponential. So your algorithm, your model improves with the amount of data and with the amount of features. So that's the I would say main differences. Again, the techniques used are also slightly different. For example, in machine learning, you use kind of numerical and statistical approaches, whereas in deep learning you tend to use things like layers, and in each of these layers you tend to use a different activation function and so on, right? Okay, so that's the, I mean, overall difference. But again, data science in itself consists of all of these, machine learning, deep learning, AI, and these are the some of the major branches or nodes of each of these. For example, we have rule based reasoning. There's not much learning here, more like rule based. Let's say, like I said, if you let's say if you walk 20 kilometers daily, obviously, let's say you lose 1 kg in a day, that is going to remain a constant, right? So I don't have to like learn any of the intricacies or relationship between the variables. It's a simple this thing. So if I walk for 20 kilometers for 5 days, I'm going to lose 5 kgs, because it's going to be 1 plus 1 plus 1 plus 1 to the 10 n tends to 5, right? So there's not a bit of learning here. So that's also one, rule based reasoning. Then comes machine learning, deep learning, natural language processing. So natural language processing tends to like deal much with text, convert basically text classification and all that, doing NERs, named entity recognitions. Like I said, the one example that I gave, organic apple. So there's this concept called the named entity recognitions, wherein I'd be able to identify, given a sentence, if apple is a brand or if apple is a fruit. There are certain this thing, for example, we use deep learning there. We also use things like Markov decision processes and Markov models, hidden Markov models. We'll probably look at some of those. And one other thing that is kind of evolving right now is this translation. Many of us, right, maybe would have used Google Translate. Yeah, so many of us would have used Google Translate, right? So in the backend, what happens is that it's a simple transformers model or a auto encoder decoder sort of deep learning model, right? So this space is also kind of has started to pick up in the last 3-4 years. We have been started using deep learnings for translation from one language to another and so on, right? Then comes machine vision, obviously the one that we saw with the autonomous vehicles, right? So that is vision, and probably something. So there are these new technologies wherein, like, given a video, it will be able to suggest the right set of titles, so that your when you upload this video on YouTube, you get a lot more views. So there are these kind of research that are happening with respect to machine vision. Then speech to text. Okay, so how many of you guys have used Alexa, Amazon's Alexa? How many of you guys have like this integrated home? Have you guys tried you guys talk something to Alexa, and Alexa like kind of knows what you're talking, right? So in the backend, what happens is that this speech gets converted to text, and this text is being sent to as an input to a machine learning model, and then it will do what you are asking. Let's say I'm saying, hey Alexa, play me the latest Hindi movie songs. Or let's say I'm saying, play me the latest English song, okay? Or say Justin Bieber song or whatever, right? So this speech of yours in the backend, it will get converted to text. This will get searched in, say, their search environment. It could be Google, it could be YouTube, or whatever, right? So then it starts playing some music, right? So that's your speech to text. And there's also the reverse that is happening from text to speech. For example, if you type just one word in Google, right? Let's say if you want to say let's type something like wealth, okay, WEALTH. So if you type this in Google, you'll see this under the search bar, you'll see the like a speaker like button. If you click on it, it'll spell this out, okay? So that's text to speech. So we are trying to hear how wealth is spelled. Yeah, but in the backend, what happens is that this text is getting converted into speech, and we are able to listen to Google, okay? So that's also one branch. And then comes robotics. Robotics are, obviously in the heavy industries, most of the work gets done through robotics only, and which is probably like a subset. Autonomous vehicles are probably a subset of robotics. It involves a lot of things, but you can at a high level, you can classify them under robotics, right? Okay, all right, so we'll move forward. Yeah, so I think this is a famous example, Amazon's product recommendation, right? How many of you guys have heard this technique called the recommender systems? Okay, all right. So I think when we are starting out as data scientists, I think product recommendation is probably the first thing that you would pick up, because it's certainly definitely very interesting if you actually solve some of the real world problems. Have you guys ever wondered how Amazon is correctly able to predict what you're trying to search for? So basically in the backend, there is there are different ways to solve this, but something called as recommender systems. Basically, it uses your historical customer data to arrive at a certain products that the machine thinks should be of interest to you, right? So I'm just posting this here for the rest of the folks. Just read about it. It's a pretty interesting concept, okay? See, SVM is an algorithm, right? So we can use a lot of algorithms to solve the recommendation problem, but yeah. So at the end of the day, it's a recommender system that runs in the backend using machine learning, or probably even deep learning for that matter. Okay, yeah, cool. Again, we saw this. We saw Alexa, right? So basically, you tell Alexa something, and it will do certain things for you. I think even cars are right now coming with Alexa integrated, right? So you can, you can just say, Alexa, turn on the AC, and it will turn on the AC. And let's say you have ventilated seats, you say, turn on the ventilated seats, and it will cool up your seats for you. So that's the kind of technologies that we are moving forward. Probably in 10 years or now, I think everything would revolve around machine learning and deep learning. So yeah, again, Alexa is a great example of the use of machine learning and deep learning. All right. Similarly, the recommendation systems that we saw, movie recommendation is also involved in that. So how basically this happens is that there is something called as cohort level analysis. What they do is they do not the I mean, let's say you're visiting Netflix for the first time. Okay, so you would have obviously seen they ask for certain data of yours. What is your name? What is your age? Where do you come from? What are your interests and so on. So with that data, what they do is they build some sort of relationship. Let's say, for example, there is a certain let's say there are 10 people like you, same age group, same place, same interest. So what basically how they solve this cold start problem? Basically, cold start is they don't have enough data about you, but you have given certain data, like very basic data, right? What's your liking and so on. So what they do is they'll convert you, or maybe they'll categorize you into one of these other categories, one of the categories that their historical customers have belonged to. Okay, so let's say you come with certain features. For example, you're 18, you're from Delhi, or you're from say London, and you're more interested in the pop music. What they do is they look at people who are very similar to you, who are around the age 18 to 20, and who have like interest towards pop music and live in and around London. So what they would do is they'll surface the things that these people have already watched. So that's how you get all these movie recommendations happening. But it slightly gets a little more complex. We use certain things like SVD and PCA and so on when the data starts. So when you've been a frequent user of Netflix, you would have obviously noticed a difference in the recommendations than when you visited the first time, because now Netflix has more data about you. What are your likes, what are your dislikes, and so on. Every click that you do on the Netflix, every search that you do and that you do on the Netflix application, they take that data, convert that into as an input to your to the some of the machine learning models, and then they come up with recommendations. Do they use cohort analysis to group people? Yeah, collaborative filtering, correct. When it's a cold start, right? What I mean by cold start is when they don't have any data about you, we start with this simple cohort level recommendations. But then again, yeah, like Yashwant is saying, it moves to collaborative filtering and few other concepts. Okay, again, Google traffic prediction is also like a famous example of machine learning around you. So it'll exactly tell you what time would it take based on the traffic, based on the directions you're taking, based on the current even weather. So in the US, on also even in let's say in countries where the winter is like kind of uh, very heavy, right? In places like Alaska and so on. This Google traffic prediction also takes into account the current temperature, how much it is snowing, and so on, to predict the actual duration. Otherwise, if it's just think about it, right? Otherwise, it's from if it's point A to B, I would know like what it would take. But it also takes into consideration the people around at that place, whether there's an event happening or whether it's snowing, whether it is rainy, and so on, and then comes and computes the actual duration. So that's also one example. Yeah, so we'll see I mean, like we just discussed, machine learning is obviously a subset within artificial intelligence. With respect to ML, you'll have to like have your data up to the mark, good quality, and then you can train your algorithms on it to predict whatever you're trying to achieve here. Okay, so that's machine learning. Okay, yeah, so this is more like a workflow. Basically, you obtain data, you train a model. If the model is good enough, you move it to production. If it is not good enough, you retrain the model with some improved data, improved pre-processing techniques, or you get more data, you do data augmentations, or sometimes you tend to also replace the data with the new data, right? So that's how the machines learn, and that's what is kind of depicted in how does a machine learn. This is more of a life cycle of how a machine learns, right? You guys are well aware. So yeah, so machine learning, of course, as you guys know, can be categorized into these three, right? So basically, I mean, as humans should have done some kind of supervised learning only, right? Because people, I mean, you either read it upon the internet, or your school teacher teaches you, and then you kind of tend to understand, oh, this is an apple, and so on, right? So that's what we are trying to achieve through supervised learning with machines as well, right? But the one thing is that we'll come up with, so we'll not be saying I'm 97% sure that it is apple. We'll say it's an apple or it is not, right? But the problems with machines is that it comes with a, I mean, always it throws out certain probability to the output, right? So I mean, if you guys have done some bit of classification, it's not always that 100% it is apple, or 100% it is not apple, right? So there will always be this 80-20, 99.1, and so on. So there is always this you know, machine always does this in probability, but we are like extremely sure of our decisions. That's one difference, right? And spam classifier, I think, so it's like, I mean, the basics, just like your Titanic dataset, spam classifier is also the basic supervised learning that we kind of try out as we start transitioning into a data science, or when we start learning data science, right? So it's a text categorization problem. Basically, it's a binary classification. We look at the text, then we figure out whether the text is a spam. If it's a spam, we just mark it as one. If it is a not spam, we mark it as zero. Internally, actually, Gmail actually does this only, right? So you'll have a folder called spam, wherein like many of the junk emails just gets transferred directly without even you having to mark them. So internally, that's what Gmail or any of the major mailboxes does for you. So with unsupervised learning, like we've been seeing, it's more about given the data, what can I achieve out of it, right? So here we are not trying to like label something or anything, but with unsupervised learning, we are trying to kind of make sense of how can the data be transformed into, or what categories does the data have, what is the sort of distribution that the data has, whether like I mean, given a set of fruits, I have like 99% apple and just 1% banana and so on, right? So in this example, if you see, these are fruits, but I have like different variety of fruits. With unsupervised learning, these will all probably get clustered into different clusters, right? So similar clusters will have similar or the same type of fruits here. But yeah, so for example, if you see here, these are like probably different varieties of apple, and like a piece of apple, a cut piece of apple is also being classified into a cluster one. And then you have like different types of bananas. This is long, this is like grouped together and so on. So what we are trying to achieve out of this is that basically we are able to like cluster our data, find if we have like a pattern. Sometimes we do unsupervised learning as an input to the supervised learning itself, right? So again, Netflix recommendation can also be like a one this thing where unsupervised learning is pretty helpful, right? So then comes reinforcement learning. We have these things called as rewards. When the machine takes a certain action, we reward it with certain let's say +1, 0, -1, and so on. So every time so basically the objective in reinforcement learning would be to achieve the maximum high or the highest reward. There are certain things that you can do. For example, you cannot just there are these problems, if you guys are really interested in reinforcement learning, called as multi-armed bandits and so on. It's a pretty interesting topic, but it's slightly at a math heavy and a slightly complex topic, right? But yeah, again, reinforcement learnings are being used in robotics, these Tesla autonomous cars and so on, right? Self-driving car uses obviously reinforcement learning, and I think even Google now has its own car. So all of these kind of have started using reinforcement learning. So we're looking at some of the basic machine learning algorithms. So we start with supervised. In supervised, you have regression, obviously linear polynomial. You can have any, kernel as your regression. Then you have decision trees. Then you have random forest, which is more like amalgamation of multiple trees. Then you have these classification algorithms like k-nearest neighbors. Again, there are a lot of trees that you can use. For example, GBMs and GBTs and so on. Then you have these logistic regressions, naive-bayes, support vector machines, and so on. In unsupervised, you have these clustering techniques, singular value decomposition, principal component analysis, k-means. So in association analysis, you have this a priori and FP growth. Again, like I said, hidden Markov models sometimes are used for identifying the states and the next state that the probably the state can move into. That's this is one thing that is being frequently used in named entity recognitions. So you use this if these are like continuous variables. Mostly this is a clustering algorithm you would choose. If it's categorically, you would choose some of these, right? Similarly, you have reinforcement learning. There are, I think, similar to these algorithms, there are a bunch of reinforcement learning algorithms. For example, epsilon greedy, softmax, there are different optimalities also you can choose from. Pack optimality, regret optimality, asymptotic optimalities, and so on. Yeah. So we'll right now then we look at some machine learning limitations. For example, it requires good amount of data to train your models, and if it's a black box model, finding out where your model is going wrong can become difficult. Example of black box models, guys. Any of you guys know what black box model is? And maybe like tell me an algorithm that is can be considered a black box. All right. So black box model is let's take this example of random forest, right? So when you apply a random forest to a particular data, you'll never know why the random forest is predicting certain things. I mean, there are feature weights and stuff, but still at the end of the day, you're not sure exactly what is happening inside. So these kind of algorithms are called as black box models. Okay, and so hope you guys get a drift of what a black box model is. Yeah, so to address some of the negativities or drawbacks of the machine learning, so basically black box model is nothing but any model given an input will throw an output, right? But you'll have to understand why the model is like giving out a certain output. For example, if it's a linear regression, it's just a linear equation problem. You'll know, okay, because my weights are so much, because my intercept is so much, I'm getting this equation, and finally this is the error that I'm getting. But with the algorithms like random forest and so on, though you can, I mean, in a high level, you will be able to understand.
Just a quick info, guys. Test your knowledge of AI by answering this question. In which of the following application does AI has its expansion? A. Planning and scheduling. B. Game playing. C. Robotics. D. All of the above. Comment down your answers in the comment section below. Whoever gets the correct answers will win 5000 points in Intellipaat wallet. Subscribe to Intellipaat to know the winners. Now, let's continue with the session.
What are the features that it is taking into consideration and so on? But inside, right, it's more like a if else loop, right? So if my feature, if this feature is X and this feature is Y, I'll be predicting this, but you'll never get to understand like the insides of it. Of course, there are things like Shapley values you can do, but of course, that's why these are called black box model. You'll never know what's happening inside. Okay. All right. So that's where deep learning will come to your help. For example, this is the image. If I use a machine learning, I just have this algorithm classify this image. But deep learning, it's the actual learning, right? It's the actual machine learning usually isn't learning, though it is called as machine learning. But deep learning is actually, it learns. So if you see, this image is broken down into multiple edges, then it also has like combination, it also learns the combination of these edges, and then in the final layer it also has these object models. So what are the different kind of objects that I can see? So this is actually, in essence, this is where the learning is. Deep learning is where the actual learning is, because with deep learning we're obviously trying to mimic our brain, right? These are like set of neurons or brain cells. We send in an input, there are bunch of cells, and finally you get an output. Okay, so I think I told you, right? So with machine learning, what happens is that your graph with the amount of data tends to, it will attain a optimal level, and post that your performance will never improve in a machine learning model. But with respect to deep learning, with the amount of data, your deep learning model's accuracy and its performance will like keep improving. Okay, so this is speech recognition is one of the important applications of deep learning. Again, text to speech, speech to text, and so on. For example, if you guys have iPhone, you would have done this. You would have played around with the Siri, right? I would say, Siri, call my friend X or call my friend Y. So your speech is basically getting converted into text, and it will take an action based on the speech that you are giving. Okay. Yeah. Another application is deep learning. For example, for the reinforcement learning, basically your computer kind of starts classifying all the images that it sees through the camera that's fitted in your here, in your headlights, in your bumper, and so on. So then for the learning, we use reinforcement, but we start processing these images to understand if there is moving traffic, if there is a collision that is about to happen, and those kind of things are being used in the deep learning. So those are the applications of deep learning. Okay. So then, like I said, this is a common Google Translate would be a common example, right? I've put in my keyword in Spanish usted es muy, and in English it's saying you are very, right? So this, you would think that this is more like a word to word translation. Basically, usted means you are, you, es is are, muy is very, but in certain languages, for example, from English to Hindi, you cannot do a word to word translation, right? Because uh, in certain languages, 3 to 4 words would combine to form a particular context. But so if you do a word to word translation at that point in time, your objective is defeated there, right? Because you'll not be able to translate it to the point, right? So that's where understanding the context of the language is much important, and there are a lot of NLP techniques that can achieve this. Okay. All right, so then we have this visual translation. Just open your camera, you read it, and it will get translated into your language of choice. So that is also, where deep learning is being applied. Okay, if you ever go to abroad and you don't know the local country's language, you can open up your camera and just wave at the signboards, and then you'll be able to understand what the signboard is trying to tell you, right? This is very helpful. Okay, so I'll just touch upon this at a high level, because later on we anyways be seeing some of these in detail. So if you think about it, this is how a common deep learning architecture would look like. You'll have input, then you'll have something called as hidden layers, and then you'll have your output. So you can send in whatever you have as your input. All of these nodes are interconnected with each other. This will be connected to all the nodes. This node will be again connected to all the nodes in the front and the back, right? Again, the output nodes will be connected to all. So think of it more like an Excel sheet with numbers being filled in. So basically, the learning happens in these hidden layers. It will try to learn what the inputs are, what the inputs mean, and then it will try to predict an output. Okay, so at a high level, this is how a deep learning is, or an architecture is. Okay, so then this is a proper neural network. So basically, with neural network, you can have like one layer, or like you can have 100 layers. So this is a single layer. Like I said, we are trying to mimic how the human brain itself learns, right? We are trying to link all the inputs to all the hidden nodes. This is where we apply certain equations, or called as activation functions. Then we try to learn certain patterns that are coming in from the input. Then we try to predict the actual output. Let's say I pass in an image of a girl, and I'm trying to predict whether the image is a girl or a boy. It will learn the features of a girl and a boy, and it will try to predict the with certain probability that it's a girl or it's a boy. Okay. Yeah, so artificial neural networks are nothing but you just create certain artificial layers in between the input and output. Whereas there are things like convolutional neural network, then there are recurrent neural networks, and so on. The obvious difference is that here you just add as many layers, but these layers will not actually solve like a purpose. So for example, in convolution, right, use a convolution grid to learn the pixels and so on. Here it's more of just stacking different layers, and basically you try to get an output. Okay, so that's what an artificial neural network is. And like I said, we're just touching upon these concepts. We'll look at the difference between ANN, CNN, and RNN, like in the due course, right? So this is it. So the first one is going to be on the topology of a neural network. How does a neural network actually look like, right? So this is how it would look like if you have to visualize it. So we have input layers. Basically, this is where your input would act. For example, let's say you have a linear equation, ax plus b. Okay, so this is where those inputs would come in. And finally, there is this hidden layer. So this is a very, very simple neural network. We just have one hidden layer, but typically that will not be the case. In the real world, you have multiple hidden layers that are interconnected. So what do we mean by interconnected here, right? So we have this as let's go with the actual nomenclatures, right? So these are called the neurons, right? So how do we have in our human brain? This is something that we looked at in the last week, right? With the help of neural networks, we are typically trying to mimic a human brain. Or how does a human learn? We are just trying to copy that, put it into a machine, and let the machine learn. So since that's the case, this is called a neuron. All of these round dots that you see are called neurons. So typically all the neurons are interconnected. So if you see, this is an input neuron, right? In the hidden layer, we'll also have neurons. And one thumb of rule is that usually the number of layers, or the number of neurons in hidden layer is usually greater than your input layers. That's when it will learn. But yeah, once we move to coding bit, you'll understand why. So all of these input neurons are interconnected. What it means is that, so this neuron, so we have three neurons in the hidden layer. So the first neuron of the input is connected to 1, 2, 3. So this is what you call as interconnected. And the input layer, and the neuron number 2 in the input layer is also connected with 1, 2, 3. So this is how a fully connected neural network would look like. And these three will go on to fetch the output for us. So the output layer usually is a single neuron, right? Yeah. So typically, this is our topology, or a architecture of a neural network would look like. Okay, there is no method per se, like Sagar, like I'm saying, right? So when there is a rule, you can have things that can optimize them, right? But so there is no rule here. For example, you can have 100 layers, you can have 150 layers and so on, and in each hidden layer you can have like 100 neurons, 200 neurons, 500,000 neurons and so on. But typically we do not go to that number. Basically your model size becomes too much, and the training time will also take at least a couple of days. So there are few things, but yeah, what is the work of this hidden neuron? So yeah, Shashi, this is how your deep neural networks learn, right? So these neurons are the ones that actually map your input to the output, and while doing so they learn what features are important for the prediction. See, these are components of the neural network. So these do not actually mean data point. Okay, like I said, there are few thumb rules that you follow. There is no strict rule on you'll have to choose 100, you'll have to choose 200 and something like that. There is no rule or boundaries. But yeah, this is something that we'll anyways look at. This is how your neural network would look like. So I mean, if you guys are interested in, or if you guys are, some of you guys are from a biology background, you'd already know this. So this is how your typical human brain would work in this way, right? So we have dendrite, we have cell body, we have axons, and each of them do their own functions. So these connections, you can relate these connections to different neurons as these. For example, what we have here. So different brain cells are connected using axons and so on. So you can relate the artificial or any neural network for that matter to that of a brain. Okay, so we'll understand some of these concepts a little more in deep. So this is what your so artificial neurons, like we've been seeing, is the most important component of a deep neural network, right? So these are all your so like we saw, these are all your input layers, and this is your input layer. All of these w1 w2 are your weights, but we'll see where these weights bias are from. But this is a typical representation of a perceptron. Okay, so before artificial neural networks came into place, this is how a neural network would look like. So if you compare it to the previous slide where we saw the topology of a neural network, you'll not have like many neurons in the hidden layer. So we just had one neuron, and that would do the function. Okay, so neuron is typically that think of it more like a cell, right? That takes in an input, passes it to the next cell for doing computations, and then finally you get an output. How in a brain it is like a biological function, right? Here neuron is more about mathematical function. So we have these neurons, then these neurons are connected to another neuron. That neuron will again do some bit of computation, then it will throw an output. When we say neurons are biological functions in our brain. Similarly, neurons in artificial neural networks or any deep neural networks are mathematical functions, right? So you have all these neurons. These neurons get connected to another neuron. Basically, these neurons get connected to another neuron to pass some information, and that information. So this neuron again will take some bit of information from this thing, and all. It will either add, multiply with say something like a 0.1 and so on, and then there is an activation function that happens on that is get applied to the all the hidden layers or that particular hidden layer, for example, and then we get an output. And activation functions are not neurons. Activation functions are functions. Yeah, so these are so assume that x1, x2, x3 and xn. So basically x represents your input, and it can take all these ith value until it n. Basically x can be like x200, x300 and so on. So these are your inputs. Okay, so these inputs get associated with something called as weights. Typically in your machine learning also you have these weights and bias, right? So like I said, this is your typical neural networks function would look like. Okay, now we'll get to an example. Okay, so these three arrows that you see are, yeah, so these three arrows typically represent your input. Consider them to be x1, x2 and x3. Can someone tell me what x1, x2, x3 can represent here? Is it like rows or is it features? Great, yes, like everyone is saying, all of these are features. So let's assume in a given input we have these three features coming in, and each have its own weights, right? So what does this sum actually represent? Have you guys seen this type of equation before? See, it's a simple linear equation, right? So given an input, you're adding a weight. Given the second feature of the input, you're adding a weight to it. Exactly. So inside the neurons, this is exactly, or I would say inside a perceptron, not a neuron. Inside a perceptron, this is exactly what would happen. right? So given an input, there are weights that get attached to each of these input. And how do we determine weights? So in a neural network, you typically randomize the weights and set it. For example, it could be as small as 0.1 or it could be as high as 100, right? So these weights aren't constant. I will get to why in a bit. So each of these features of the input are acted upon by weight, and then we get their weighted sum. For example, here the weighted sum is x1w1 plus x2w and so on. Finally, let's assume that the weights are 0.7, 0.6 and 1.4. Let's say we assume.
If you want to make a career in data science, then Intellipaat has IIT Madras Advanced Data Science and AI Certification Program. This course is of very high quality and cost effective, as it is taught by IIT professors and industry experts.
Or we initialize the weights with 0.7, 0.6 and 1.4. This is how your final weighted sum would look like. Let's assume x1 and x2 to take something like 1, 2 and 3. So we just multiply 1 into 1.7, 2 into 0.6 and 3 into 1.4. Your final, let's say you get say something like 10. That would be your input. Where is my name? Yeah, so there are certain reasons that we add weights to it, yeah, which we'll come to in a bit. Okay, so inside a perceptron, so you get, so inputs are sent into a perceptron, then these are acted upon by weights. Basically, when I say acted upon, these are also these get assigned to weights, get assigned to each of these input features, and then we finally get their weighted sum. And with this weighted sum, we add a bias. Someone just quoted y is equal to mx plus c, right? That c is your bias intercept. Guys, in linear regression, what is c? We have y is equal to mx plus c, right? What is c there? Yeah, c is a constant, but what is the use of it? So like everyone is saying, that's the intercept. So we have the same concept in neural network as well. We add this term called bias. The reason that we add this is that, so if you see here, once we get weight, then once we sum it, we add a bias, and post that we get this activation function, right? So the need for the bias, like everyone has been asking, is that bias is used to delay the triggering of the activation function. So basically, with the bias term, let's say your bias is high, it can lead to faster trigger. If your bias is low, it can lead to slower trigger. I'm just giving a relational example. That will not be the case, but just understand it that way, right? So basically, your bias function, see, if your weights are higher, right, it will increase the steepness of your activation function. So we'll see some of these activation functions in a bit, but bias is used for mostly like a scaling purpose, like how we have in a simple linear regression. So when we add the when your c goes higher, your entire linear equation becomes greater, right, depending upon what your weights are. Similar to that, we add bias in neural network also, which is used for a scaling purpose. So once an activation function acts upon this particular equation, we get an output, right? So to transform or scale the let's say scale the equation inside like a boundary, we use that bias. Yeah, so inside the perceptron, this is what happens. Just reiterating it for clarity, your input comes, these are acted, weights get assigned to each of the features, then we get their weighted sum, then there is a bias term that gets added for scaling purpose, and then finally these activation functions act upon them. So some of these activation functions, see, what we call as algorithm, I'm just giving again a very relational example. Like you have linear regression, you have logistic regression, and so on, right? So these typically are like algorithms that act upon like a particular equation of your input. So similarly, we also have these functions in deep learning, which is what we call as activation functions. So basically your particular, so this is an equation, right? So x1 into 0.7 plus bias, this will be your equation for your input, right, for your row number 1. So let's assume that we want to convert this to 0 to 1 and so on. Okay, and get some number such as 0.5 for this value. So how do you do that? Let's say x1 has something like 100 and x2 has something like 200. Obviously this will exceed 0 to 1, right? So in order to map these values to the output, we use activation functions. Okay, so coming back to why do we even need weights? But what else is that weight doing there? So why do you think the lines change or the slope changes for that matter? Let's say I have this equation, x1 into 0.7, x2 into 0.6, and x3 into 1.4, right? Now I'm going to replace this 0.7 weight with 100. So basically this becomes 100x1, right? Now what am I doing here? I'm basically shifting the equation altogether, right? Because now my feature x1 will have the highest weightage because I'm giving it a higher weight. That's the reason that we need to have weights. The reason that we're doing this is, let's assume, so basically weights are added to determine the importance of a particular feature. Okay. Okay, I'll just give you an example. Let's say the objective of our prediction, or what we are trying to predict for the day, is whether it will rain or not. Okay, so let's assume there are two features. One feature describes what is the amount of clouds that we have over our head. Okay, second is that color. Second is the color of the road. Okay, now the first feature, which is the number of or the volume of clouds that we have are upon our head, that will have the highest weight, right? Because that will be able to predict my output more clearly, whether it will rain or not. If the day is more cloudy, obviously I can predict with a certain probability that it is going to rain. But if it is completely sunny, obviously that the weight that I associate with that feature will come down. But apart from that, so this second feature that we have, which is the color of the road, could be determined by, yeah, it's not really deterministic for whether it will rain or not, right? So let's say you're living in a village, the color would be the roads would be cement and it will be like in a gray color, whereas if you live in a city, it will have like black color. But what does it even have to do with prediction of rain? So in this case, you'll have to give more weightage to the cloud or the volume of the cloud instead of like the color of the road, right? So that's why we have weights. So when the neural network understands that a particular feature is important, it will adjust the weights so that the feature that is actually or directly deterministic of the output gets a higher weightage. Okay, is it clear on why do we add weights? See, this is very simple, right? It's a very simple example that I've just spelled out. So basically your weights will determine the importance of that particular feature. It's as simple as that. That's why we need weights. Without weights, there is no point in predicting, or there is no way you can predict the output, right? So now what I did was, so each of the input that I'm getting, say, let's say I have x1, w1, x2, w2, and so on. Each of this, I just did a cube of it. So let's say I have 3, I just got 27 instead of 3. Now I'll be able to project it into into 3 different dimensions, and then I can have like, so if I just draw a line here, or when your dimension increases, you cannot draw a line, you'll have to draw a plane. But let's assume I have a sheet that runs through 0.4. Okay, then I can have a really good classifier, right? I'd be able to classify all that is greater than 0.4 and to be as this dot, and whatever comes below this 0.4 plane, I can consider that to be triangle, right? This is a very simple example on why we need an activation function. All right, so coming back, activation functions, right? So there are a bunch of activation functions that we look at typically in a neural network. Some of these are predominantly used based on their application, but some of them are not used anymore. We'll see which of them are used predominantly and which are not. But that's the exact reason why we use activation function. So basically, the activation function will help you convert your basically let's assume that the characteristics of your input data is non-linear in the first place. You will not be able to draw a straight line that will perform the classification. That's where activation function comes and helps in transforming your data such that we can perform these complex classifications. Okay, so how many of you guys already know these activation functions? Now you guys have an understanding, right? Why do we need an activation function? Just very simple. If we don't have an activation function, it becomes for certain distribution or characteristics of the data, it becomes very difficult for us to predict the output. That's why you see, people would have said, hey, if it's if the output is just going to be like continuous number, why not use linear regression? You would have applied it, but then you'd figure out that the accuracy of your linear algorithm is going to be like something like 30-40%, right? So the reason some of these happens is that basically that means your effective problem itself cannot be linearly classified. Okay, so this is an identity function, right? So this is what the formula for identity function is. Whatever your x is, it is going to return x, which is going to be like proportional to the input, right? If I give 2x, my output would be 2x, or 2 of whatever the output will be, right? so we have this identity function, right? And I mean, we've been talking about linear regression for so long. So this typically basically represents your linear equation or linear regression problem. The range for this identity function is minus infinity to plus infinity, right? Can someone guess why so? Yeah, values could be in that range, but if you guys have done linear equation problems before, it's no, typically yes, it's a straight line, but I'll tell you, right? So if you guys have done or solved linear regression problems before, even I mean, in a rough calculation, right, you'll understand that typically the input is directly proportional to the output, right? So let's say I have, like we were just seeing, right, some of the, if my weight is high for some of these inputs, obviously my output is going to be high, because we are not reducing it anywhere, we are not squashing it everywhere, anywhere or so on, right? So that's why ultimately it depends upon the equation itself, right? So the output, that's why, can range from minus infinity to plus infinity. Let's say some of my weights are in millions, okay? So what would it mean is that obviously my output is going to be in millions. That's why the first line says that your identity function will always be when you apply an identity function, the output will always be proportional to the input that you give. If you give it in millions, the output will be in millions. If you give it in minus 0.0000, it will be in, your output will also be that level. Negative or positive doesn't matter, the scale will remain the same. It's the same as a linear equation. Whatever your scale and the sign of your input is going to be, that will be that is going to be the scale and the sign of your output also. That's why the range ranges from minus infinity to plus infinity. Higher your input, higher will be the output. Lower your input, lower will be your output. It's as simple as that. This is a very simple one, right? It's just a line. If you guys know how to solve this line, you'll get the output. So what I'm saying is, with identity, so there are multiple activation functions. So the first one that we are seeing is identity function. So basically this weighted sum that we saw before, x1 w1 plus x2 w2 plus x3 w3 and so on, right? So if you think about it, right, even logically, even in an Excel sheet, if you just type out some numbers and do some weighted sum, you'll understand that your output is always going to be proportional to the input. If my weights are going to be at the scale of millions, my output obviously is going to be in millions. Of course, you can decrease it and so on, but still it is going to be really proportional, right? Let's say your other weights are not contributing so much to the equation. My output is going to be at that level, at that scale, right? So if it's positive, it is going to be positive. If it is negative, it's going to be negative, right? So basically, with identity function, everything is, the output is going to be proportional to the input that you give to the equation. All right, so we'll move to the second, binary step function. So what does this graph actually represent? So typically people from the electronics electrical background, exactly, right? So we guys would have done this in some kind of practical examinations, right? Step function, exactly. Yeah, so this is your typical step function. For any value that is negative, the output will always be 0. For any value that is positive, your output value will always be 1. That is your step function. If you, again, I'm saying, always visualize it with the help of this graph. So if you see here, anything that is negative, right, all is 0, right? Anything that is positive in the you get a 1. So always think about this as a, visualize it with the help of a graph is what I'm saying, right? So this again is a very simple one, right? So anything that is positive will have 1. Anything that is negative will have 0. So there is no concept of having 0, 0.5, 0.7 here. So if your input is going to be greater than 0, you're going to get what? If your input is going to be less than 0, it is going to be 0. Clear? Just remember these graphs. It's going to be very helpful when we move in the future. Okay, so since many of you guys have been asking, where do you use these activation functions? So again, like, very simple, right? You can use it for a binary classification problem. If the output is just to predict whether it will rain or not, whether India will win the cricket match or not, something like that, where the output is a binary, true or false or something like that, we will use these binary step functions. Clear? So this is one application of where you use a binary step function. Okay, cool. Yeah, so now comes this important concept, sigmoid. So what does this, have you guys seen this graph before? You would be able to define about a certain threshold where I need a positive. If my threshold is 0.5, I can say that only if it is above 0.5, give me 1. If it is less than 0.5, give me 0. That is also possible. It doesn't have to be exactly 0, between above 0 and below 0. Okay, that is also possible. Just wanted to highlight that. Okay, that's why I was asking, I mean, whether 0.5 is possible. But I mean, yeah. So like many of you guys have been saying, this is a simple logistic regression, right? This is how we will look. Anything that is greater than 0.5, you will have 1. Anything that is less than 0.5, you will have 0. So always, I mean, if, okay, so what happens if my if this value is negative? The output that I get from exponential of minus x, sorry, 1 by 1 plus e to the power minus x. Minus x is going to be your equation, right? Whatever your weighted sum is, that is going to be represented by x. What if it is 0? What if it is highly negative? What will happen to this curve? Maybe 0. Okay. See, if you see here, there is one more concept. I don't know if you guys have are aware of this in ML, but yeah. So the curve kind of gets flat when it's at the top or at the bottom end, right? So what this basically means is that doesn't matter how big your number gets to. Let's say let's say
Just a quick info, guys. Test your knowledge of AI by answering this question. What is artificial intelligence? A. Putting your intelligence into computer. B. Programming with your own intelligence. C. Making a machine intelligent. D. Putting more memory into computer. Comment down your answers in the comment section below. Whoever gets the correct answers will win 5000 points in Intellipaat wallet. Subscribe to Intellipaat to know the winners. Now, let's continue with the session.
doesn't matter how big your output is. It could be like 3 billion. Okay, let's say 3 billion as a number, right? It's quite a big number. Doesn't matter. Finally, if you use this function, it's going to reduce to 1. So large positive numbers are scaled towards 1. That's why we use this term called scale. Basically, we convert all the output that we get between 0 and 1. Clear? Sigmoid function. So like we were discussing, the output is always going to be 0 to 1. If it is a highly negative number, it is obviously going to get squashed towards 0. It will be like 0.00001, which can also be equal, or we can assume that to be equal to as good as 0. So so that's the in effect, that's the sigmoid function. Okay, so basically here your x represents your entire equation. For each row, you apply 1 by 1 plus e power minus x. X can be x1 plus w1 plus x2 plus w2 plus c. So here x would represent your equation. Yeah, so we'll go ahead. You just define a range, and based on the range, it will give an output, which is going to be linear based on your input, right? So it's a linear function only. Only your sigmoid is a non-linear function. And of course, the functions that we'll see after sigmoid, for example, tan h and so on, ReLU, those are non-linear. But your step functions and linear functions are obviously linear functions only. Okay. More flat towards the end, the range, some straight part is there. Okay, both are exponential, values are different but similar. See, tan h and sigmoid are very similar to each other. Okay, it is just that the range is shifted here. If you see in sigmoid, your output is always going to be between 0 and 1, but in tan h it will always be between -1 and 1. That's why, like if you see, even the formulas are typically or very similar, right? You get 1 by 1 plus e power minus x. Here you get 2 by 1 plus e power minus 2 x minus 1. So just the range gets shifted. Here it is always between 0 and 1. That's why you see it is always, you can also think like this. It is always centered at 0.5. Okay, anything that is greater than 0.5 will be your output would be true. Anything that is less than 0.5 would be your output would be. Typically, that's how you do your logistic regression, right? If the probability is greater than 0.5, you assume it to be true. If your probability is less than 0.5, you assume it to be false. But here, it is centered around the origin or 0, right? So basically, this passes through the 0. If anything is, I mean, if you want your output range between -1 and 1 instead of 0 and 1, you typically go for tan h. That's the only difference. Rest of the characteristics are almost the same. Yeah, the range is there, but like I said, this passes through the origin. This passes through the 0. Basically, the activation function is centered around 0 here, right? Because the middle value between -1 and 1 is 0, right? But here it is the middle value is 0.5. It is centered around 0.5. The middle value between 0 and 1 is 0.5. Okay. So we'll look at the next activation function then, which is ReLU. ReLU stands for rectified linear unit. Okay. So So this is your typical positive part. Basically, what happens is that any value that is, if you see here, any value that is less than 0 will always be 0, but any value that is greater than 0 will take x. Correct. Any value that is greater than 0 is a linear. Exactly. So, but there is, I mean, with ReLU, there is a concept called as dead neurons, which we'll see when we implement the neural network. So basically, neural networks learn with a concept called backpropagation, right? Wherein your errors get backpropagated through the layers and the layer weights are adjusted. So typically what happens is that, let's assume the weights to be negative. In that case, some of the neurons that have the ReLU function being their activation function, they'll become dead. One other since you are asking, I mean, with ReLU, right, if you want your outputs, some of your outputs, obviously, I mean, again, this will be a little complicated. That's why I'm not taking this point. So in your typical neural networks, usually your output layer can contain multiple neurons. Okay, if you typically want your output layer, some of the outputs to be equal to 1, you can use ReLU again, but you will understand it when we start coding it out. You'll see all of this when we do that in the practical class. Again, the idea here is to make you guys understand that there is a certain function that does this. Okay, if I say I use ReLU, if I say I'm going to use ReLU function, you'll have to understand that, okay, the output of the layers will always be between 0 and infinity, whatever the weights that we add, or whatever the scale of the equation is going to be. Okay, so understand it more from that perspective, visualize it with the help of this graph. So that's all we are trying to understand with this theoretical classes. Okay, cool. So like someone just explained, there is a parameterized way of ReLU. When we say parameterized, so here you're quashing your ranges to be between I'm saying, hey, I want my output between 0 and infinity. I can typically use ReLU, but let's say I want to use ReLU, but still I want my outputs to be between minus infinity and plus infinity. Then there is a parameterized way of doing leaky ReLU. Again, there are certain applications, like we said, right? For example, there is a concept called the vanishing and exploding gradient problems in neural network. So typically, when you see that, hey, my neural network is underfitting, then there are, for example, how you have in your machine learning, if my model is underfitting, you do certain things, then you'll tune up your model to fit the data better and so on. Similarly, that's where you typically, if you're using a ReLU and you see that your data isn't getting fit better by the neural network, you will go to something like a leaky ReLU. So parameterized ReLU that we call basically shifts your range again, right? Basically, before it was 0 to infinity, now it becomes minus infinity to plus infinity, if you see here. So what happens is, when you do from 0 to infinity, is that, assume your neuron value becomes closer to 0. Then what happens is that it is not going to add any information onto, or pass any information onto the next neuron, right, or to the next layer. We do not want that typically in a neural network. We want all neurons to learn some pattern, learn some weights and so on. So if my output from a particular neuron is going to be 0, what value does it add to my next layer? Nothing, right? So we don't typically want that. That's why we have something called as leaky ReLU. That's what you call as the dead neuron problem. If my output is very close to 0, it's not going to add much value to the next layer. We typically do not want that, and hence we shift the range. Instead of from 0 to infinity, we get it from minus infinity to infinity. Also, what you guys have to understand is that some of these functions are evolution of another function. For example, we've been using ReLU, okay, but then we figured out that, hey, ReLU is causing this problem wherein the output that is negative is close to 0. Why would I not want to store information, or why would I not want the neuron to learn something, right? So then comes the evolution of this ReLU function called the leaky ReLU, right, wherein I'm shifting the range between minus infinity to plus infinity. Similarly, like what we saw with TANH, basically I'm shifting the range around 0, around the center, around the origin, right? So think of it more from that perspective. Okay, that time. Okay, so we'll look at again, right, the activation function. You can think of it this way. You can use your own activation function, right, in a typical layer. What are activation functions? These are just simple equations at the end of the day, right? You take an input, you apply some equation on top of it, you get an output. This equation can be anything, right? So it depends. I mean, you are as flexible. You can play around with it as much as you want. It's as simple as that. Okay, now coming to the final and the most important activation function is softmax. Typically this is used in your output layer. Okay, so people usually get confused between softmax and sigmoid. Okay, but the thing is that softmax, if have you guys used softmax in your ML problems, what would be the output of softmax? Okay, so when do you typically use softmax? So typically softmax is used when there is a multi-class classification problem, right? So let's say you're doing a multi-class classification problem. You want your output to be belong to say classes A, B, C, and D, right? For each of these classes, you'll get a probability. The class with the highest probability will become your output. That's where your softmax is, right? That's the help of or that's the use case for softmax function. When there is a multi-class classification that is happening, exactly, digit identification. So Ashutosh, like the example that Ashutosh is quoting, in digit identification you get from 0 to 9, right? So which means you get 10, you got 10 classes to classify a number into, right? So you get a probability for all the classes. The class with the highest probability will become your output. So that's the use for softmax function. And in neural network, typically softmax would become your final output layer. The activation function that you use in your output layer will be softmax. And since it's a probability, obviously it is going to be between 0 and 1, right? Anything that is close to 1, we can say that we are pretty confident that it is the best, or it is the final output, right? Anything that is closer to 0, we can say that the probability of that being the output is not that great, right? Softmax is usually used even in machine learning for multi-class classification problems, wherein the output is the probability of all the classes. Let's say you have the objective is to classify a particular input across 10 different classes. You'll get probabilities for each of the class. So we usually pick the one class with the highest probability as their output. So the sum of all the probabilities would, if you add up all the probabilities, it will always be equal to 1. Right, so here k represents the number of classes that you have, and softmax function in itself is determined or the formula for the softmax function is this, right? Usually in deep learning, softmax is usually used as your final output layer. Okay, so we'll move forward with some of the new topics. Okay, so that's the objective. We are not trying to look at what to use where, but I've also at places where it is quite fixed, like for example softmax, and binary step functions and so on. It is very fixed, right? So usually softmax in deep learning is used as your output layer, at your output layer. Stepwise is usually for categorical, when the objective is a categorical classification or a binary classification problem, right? So wherein it is applicable, I've already mentioned that, but for some of these things, these could change depending upon the problem that you're trying to solve. There is no hard and fast rule on which activation function to use where. Okay, all right, now we'll see how to train a perceptron. Like we said, right? Perceptrons were the precursors for all our neural networks that we have in today, right? So, and perceptrons are usually just used for classification problems. Yeah. So while using perceptrons, it is typically understood that the problem that you're trying to solve is a classification problem, and the perceptron could also have something like a multi-layered perceptron, wherein post the input layer we could have multiple layers of perceptrons acting to map the input to the output, right? So we'll take a quick simple example on how the training of a actual neural network works. This if you are from a ML background, or if you have done some bit of research on machine learning, you'll find the concept to be almost the same, right? So what are we trying to achieve here is, so we have a set of dogs. We have 3 dogs. We have 3 horses here, right? So assume these are passes. Okay. So let's say I have put 1, put 2, and put 3. Okay. So let's say there are certain features that I have, and I have my target variable, which is y, or let's say I have an output. Output is dog, horse, and dog. Okay. Let's say dog has short, so maybe short ears, short nose, height less than 3 meters. Okay, so let's say I fill in true here, false, and I have false here, false. Okay, so this is a very simple example. So this is going to be my input. These are my features, and this would is what we are trying to get as an output. Okay, right. So what happens here, or what is represented through these diagrams, is that always how a deep learning, obviously how learning in deep learning or neural networks works is that you send this all these as input, right? So now what you'll have x1, right, x2, then you have x3 finally. So what happens in the next step? Weights get added, right? So w1, w2, w3, right? So we get a final weighted sum. So 1, then you get x2 dot w2, then you get x3 dot w3. So this you get your weighted sum. Okay, finally bias is added. Then let's assume an activation function we are going to use. We'll assume there is going to be just one single layer. The hidden layer is just going to be one. We'll assume an activation function of relu. Okay, so now we got this weighted sum x1 plus w1. Basically, if it's a 0 for false, 1 for true, so we get w1, x2, w2, and x3, w3, right? This w1, w2, w3 can be randomly initialized. Okay, it could be, we can start with any number. Weights are randomly initialized. Bias is also randomly initialized. Okay, so I assume my weights to be 1, 2, 3. Okay, and I assume my bias to be 5. But I mean, this will not be so straightforward in real life learning, but this, so that you guys understand, I'm just giving a quick example, right? Yeah, so coming back to the weighted sum, your bias gets added, okay, and your activation function is applied on top of it. You get an output, right? So let's say for all of these outputs, you get horse, or maybe, it's easy to figure out this. So let's assume that it doesn't even, it has gone wrong with this input horse, right? So what we call in machine learning epoch, right? So basically what epoch means is that how many times this entire data set is seen by the machine learning or your deep learning algorithm. Okay, so let's assume the epoch is 3. I mean, I'm just representing this. Okay, so what happens is here is that it has gotten 2 of them wrongly classified, right? So basically either this should come here or this should go there, right? So it has gotten 2 of it classified. So in the first epoch, let's say this is the first time that my model is seeing and we are getting an output. In the first pass, it's a first pass, my model is seeing all this data for once, and I'm getting an output. Okay, and this time we are seeing that it has classified 2, that is 2 elements wrong, right? So either it has identified 2 dogs as horse or 2 horses as dog, right? Vice versa. So now the error is 2, right? Next what happens is that there comes pass 2. Okay, now the error reduces because it has seen the data again. It will make some changes. We'll come to how it will make changes and all that. Okay, but it will make some changes in the weight and the bias that we have, right? So then it figures that, then it has figured out, or it has improved itself. Now the error is going to be 1, right? So this is your vanilla model baseline. Okay, so obviously this is going to be your baseline, right? So in the first pass it hasn't performed well. In your second pass it has improved over the previous pass, right? So it's an improved v1, improved, or let's assume it to be version 1. So in my pass 3, right, what do we see here? We everything has been correctly classified. So error would be 0, 100% accuracy, right? So obviously this is going to be my best model, right? So exactly what is represented through this diagram. So in essence, let's say you have these inputs, you have these features, you have an output. In the first epoch, usually that's why we train a neural network for like multiple epochs, or again, epoch here means the number of times the neural network algorithm has seen your input data, right? Okay, now coming to how does it actually become better after each pass, right? Now, so since it has so the output is all dog here, what would have it already done inside is the features that represent some of these things, right, would have gotten higher weights, right? So let's say short ear, short nose has gotten higher weight, or height less than 3 feet has gotten higher weight, and short nose did not get any weight at all. I'll just change it to true. Okay, now what happens is that these 2 guys or these 2 features would have gotten the highest weight, right? So then what happens? So if these 2 have gotten the highest weight, if short ears is true and height is also less than 3 feet, I would simply classify it to be a dog, right? Now so how does it learn is that, so we have these weights, right? So associated with each of the features. After every pass, right, it will understand that which features become important for the right classification, because it'll I mean, you obviously feed in, if you train it, you obviously feed in with the output also, right? So it'll know that it has classified two dogs as horses. Okay, so this will be known to the model. Now what it has to figure out is that, so I have gone wrong in two places. Now how do I fix this equation? How do I fix my weights and bias, right? How do I fix these two to ensure that these errors are eliminated? Now how will that come? Basically by understanding the features that are deterministic of your output, right? And how do we weight them? We use w1, w2, and w3. So what happens is that basically from the errors that it has produced, it will go back and fix the weights. So let's say we initially assumed it to be 1, 2, and 3, right? Now w1, let's say, would become less than 1, or it can become greater than 1. Finally, bias is also tuned to ensure that this equation that we put in post activation function gives the right output. So basically, in short, how does a neural network learn is that after every pass, these weights will get adjusted based on the error that it has output, right? Once these weights are fixed to a certain extent, or once we've crossed a certain accuracy level, we stop and we assume that to be the best model. Okay, if you also increase the number of epochs, there is also this problem of overfitting. We'll come to all of that, but again, this is more about understanding how a neural network learns. We'll set the epochs and all of that a little later. Yeah, so I have my weights 1, 2, 3. Okay, let's assume the output that I'm trying to get is marks. Okay, let's say I have student A, student B, student C. Now output marks is, let's say, 98, 99, 100. Okay, so let's assume some features. If handwriting is good, something like that, or I mean, it could also be very nuanced, right? For example, the features can be anything. Maybe I'll just take, if handwriting is good, let's say you have this between 0 and 1, so I have 0.8. Detailed explanation and understanding of the subject. Okay, so I have these three features. So depending upon the input, let's say I have 0.9 and 1.1, 2.3, 4.6, 1.7. Again, I'm just giving a random numbers, so these may not have any meaning to them. So let's say I have these, right? So these are three features which I would so let's assume these are the three features that and finally my output is also continuous variable, right? It can arrange anything from 0 to 100. Okay, now what do I need? I have weight associated, right? So I'll multiply all of this with my weight, then I add a bias, right? Finally, how will it look like? So it will be like into, let's assume the weights to be 1 plus 0.9 into 2 plus 0.1 into 4. So I also add a bias term. Let's assume C to be 5. This, for the first equation, it will be equal to 98. Similarly, for the second and third equation, it will be 99 and 100. Now, once we start tuning these 1, 2, and 4 plus the C, we'll get an equation where, given an input, it will be able to identify the output. It's as simple as that. How do we do for a continuous variable? The method remains the same. There is no change when we do for categorical or numerical. Perceptron is trained, and this is more of a graphical representation, right? So you get these bias, then you get an output. This error goes back to the input or the weights. This weight will get adjusted, bias also gets adjusted, then again you same thing happens in loop. Okay, so input, we initialize weights, bias, and threshold, calculate the sum and pass through an activation function, produce the output. If it's correct, we stop, else the error goes back to updating the weights. Okay, cool. Yeah, so again, some of the very simple benefits of using artificial neural networks. So organic learning, we can process nonlinear data. There is fault tolerance and self-repairing. So we'll see some of these. Some of these could be like very. These are like very at a very advanced level. For example, something like self-repairing could be a deep reinforcement learning and so on. But yeah, we'll come to all of these in a bit. Okay, now, so the rest of the folks, you guys have already worked 4 GB RAM. Just use Google Colab, Varun. Okay, I think 4 GB RAM should be enough, but it is better that you have 8 GB. Anyways, you can use Google Colab. Okay, so we'll move forward. So these are some of the most important deep learning frameworks, or libraries, so as to say, right? So this represents TensorFlow. Then you have something like MXNet. Then we have PyTorch, Keras, and DL4J. This is a Java-based library. Okay, so the first thing is that we have is TensorFlow. TensorFlow and Keras would be the two of the most important libraries our hands-on coding sessions would be based upon. So this is developed by Google, and that's why in Google Colab this will be like pre-installed. Okay, so then we have yeah, so TensorFlow is used for all of these natural language processing, forecasting, tagging, text classification, and so on. Everything is open source here. Everything that is listed here is open source. You can just do a download. You can just install it and start working. Yeah. So then, so inside TensorFlow, you have these two components called TensorBoard, which is usually used for visualizing your computations and graphs. Okay. Then you have something called a serving, wherein you can deploy all your trained models on cloud. Uh, okay, so these are a couple of concepts or a couple of components of TensorFlow that will enable data scientists for one for visualization, second for deployment of your deep learning models. So next is Keras. So it's again an more of a high level API. You can use TensorFlow as your backend while using Keras. So these guys have written certain kind of Python wrappers on top of TensorFlow to access certain methods, and top of it also, I mean, they've added certain features that were not present in TensorFlow. Okay, and yeah, so Keras is predominantly used when we start with RNN and CNN, recurrent neural networks and convolutional neural networks. So like I said, it's the library that anyways, coming back, so Keras has two types of this thing. One is called a functional API. The second one is called the sequential API. So stacks layer. So here it says stacks layers on top, right? Because if you look at the topology of the architecture of a deep neural network, it is one layer stacked on top of each other, right? So you have input, you have it is more sequential, right? Input, then you have hidden layers, you have first hidden layer, you have second, you have third, you have the nth hidden layer, then your final output layer. So all of these layers are basically, you can assume them to be stacked like this, or your hidden layers can be stacked like this. So Keras will help you do all of that. Next comes PyTorch. PyTorch is actually developed by Facebook. They own this library, but of course it's open source. It is typically, used for, I would say for developing neural networks and especially natural language processing with the help of deep learning. Okay. And PyTorch also offers these dynamic computational graphs, which will help you, structure your networks in a certain way. Then comes DL4J, basically a Java-based deep learning library written for Java. So all that we saw before was for Python, whereas DL4J is for Java developers. We'll not be using Java, we'll be using Python. Yeah, since it's Java-based, obviously it will have associations or integrations with Hadoop and Sparse. For big data processing, you can just consume all the big data and start training model using Java. So that's where your DL4J will help. And DL4J also has all of these features for image recognition, fraud detection, parts of speech tagging, text mining, natural language processing, and so on. Okay. So then comes MXNet. We have MXNet, which is developed by the Apache Software Foundation. Right. So you have a lot of softwares that come under Apache, for example, Kafka and so on. So it has integrations with Python, R, Scala, and Julia. Okay, so yeah, so coming back, MXNet can integrate with, you have MXNet for Python, you have MXNet for R. Some people I see usually prefer R for machine learning purposes. So these guys can also have access to MXNet. They can download it in R framework and they start using MXNet. It also has this ability to integrate with Scala applications, basically for big data processing, and then you have Julia. Similar to DL4J, MXNet also has this image, speech, and NLP forecasting. All of these, components are available for use. Okay, so that's it with the frameworks, and just reiterating, we'll be using TensorFlow and Keras going forward. Okay, coming back, right? So tensors are very similar. See, tensors are, they are not matrices, but they are more of a generalized way of see, guys, MXNet was more given as an example. So we'll install MXNet when the time comes. Okay, we'll not worry about MXNet for now. Okay, so coming back to tensors, these are tensors are a multi-dimensional array. Obviously, the inputs are stored in tensors for TensorFlow. That's why it's called as TensorFlow, right? Yeah, so tensors are more a generalized way of representing a matrix, right? So matrix, how matrix is represented using M and N, right? Matrix are always rows into columns, right? M represents rows, N represents columns.
If you want to make a career in data science, then Intellipaat has IIT Madras Advanced Data Science and AI Certification Program. This course is of very high quality and cost effective, as it is taught by IIT professors and industry experts.
So what would be the shape of a matrix? How many dimensions does a matrix has? How many dimensions do we? Yeah, 2D. Okay. Yeah. So exactly. So matrices usually are two-dimensional, right? Whereas tensors can, an array can have any type of dimension. So again, we'll be referring to we'll be using only tensors going forward. It'll in machine learning, people, you guys would have used matrices to represent your input data. Here it will be all tensors. So similar to matrix, you also have rank. Basically, a scalar is represented. Basically, if let's take temperature for that matter. Let's say I give today's temperature is.
Just a quick info, guys. Test your knowledge of AI by answering this question. In which of the following application does AI has its expansion? A. Planning and scheduling. B. Game playing. C. Robotics. D. All of the above. Comment down your answers in the comment section below. Whoever gets the correct answers will win 5000 points in Intellipaat wallet. Subscribe to Intellipaat to know the winners. Now, let's continue with the session.
Today's temperature in New York is 273 Kelvin. Okay, so basically 0 degrees Celsius. Okay, that 273 is a scalar, right? Because it doesn't have any direction. It just has magnitude for that particular parameter that we are trying to represent. Okay, so in that case, the tensor can, the magnitude can be represented as a 0 rank tensor. Okay, so rank one, you have like a very simple array, right? You have both magnitude and the direction. If it's rank 2, you have matrix. It will be represented in a table of numbers. If it's rank 3, it will be a cube of numbers. I already have like a example of visualizing it. So if it's a three-dimensional tensor, or if there, sorry, not three-dimensional tensor, if it's a rank 3 tensor, it will be something like this. So this is one input stacked on top of another input, stacked on top of another input. So this is more of a, think of this more like a image, right? So images are usually represented using this, right? R, G, and B. So you can so assume these are image pixels, and this is how the image can be represented as. So basically, you have 3 dimensions running, one on top of each other. Visualize this in a more of a 3-dimensional image. Okay. All right. So like we said, the tensor can have any rank. It could have like any rank depending upon the shape of the tensor that we give. So rank 2 tensors are matrices, but there is a catch here. All rank 2 matrices can all rank 2 tensors can be a matrix, but not all matrices are tensors, because one important property of a tensor is that the ability of it to transform. For example, I cannot reshape matrices in a certain way, because it has to follow certain transformation laws. Even tensors have certain transformation laws, but again, I can convert a 2-dimensional or a 2D tensor into a 4D tensor and so on. So there are certain properties will help tensor. For example, tensors are used if you are looking at a use case. Let's say you have a stress acting at a particular point, then you have like strain as well, then you also have the load at that point, then you also have the amount of curve it has got, right, because of the load and because of the stress and so on. Then you have this curvature of the load, then you have the fracture point and so on. If you want to represent all these kind of properties associated with a particular thing, we usually go for tensors. Okay. Again, in machine learning, people usually use matrices or n-dimensional arrays to represent. In deep learning, we typically go for tensors because of their ability to transform themselves given an input. Okay.
The other point also is that these frameworks, all these deep learning frameworks, one of the things that is very, very common in all of them is they all work on computational graphs. And when we say computational graph, basically it's basically like representing a simple mathematical computation as a graph. So as you could see here, in this case, A and B are two values, and they sort of flow into a particular mathematical operation. And then that flows into another mathematical operation, and there's another input. And then the output is basically H. So if you kind of convert this whole mathematical operation into this whole thing into a into a mathematical equation, it sort of becomes AB, right? Because we're essentially multiplying these two. So AB, and you're adding C to it. So AB plus C is what is H. So anyone quickly, what's the outcome here? A into B is 200 plus 30, 230. That's the basic outcome in this particular case. In the case of your TensorFlow, we call each of these computations as a computational graph, and each computation or every computational graph is executed inside a particular session. So it's called basically like a session. So every computation, this is a computation, and this computation is happening inside this particular session. For jargon's sake, it's not something that we should really worry about. But what we are saying is that all computations, when they happen inside a particular session, they have how the values can be they can be used internally. Across sessions, variables are not shared. Inside a session, variables are shared, or variables are accessible to each other. Across sessions, variables are not accessible. That's basically what you mean by session. So yeah, a node is a mathematical operation. Like for example, this is a mathematical operation, this is a mathematical operation, and the values that basically get passed, they are all tensors. So this is a tensor. Like for example, this is a tensor, this is a tensor, this is a tensor. These are all tensors. Popular programming elements in TensorFlow are you have something called as constants, placeholders, and variables. Constants, as you wanna are constant values, something that doesn't change. Placeholder values are values which are typically going to get assigned during an execution. They are like arbitrary constants. They're placeholders, as in they are not really, you know that there's a value going to come in there, but it's just that you haven't assigned any value to it right now. So the value gets assigned during execution. And a variable is, again, you simply say X or a Y. These are simple variables that you have. So we'll look at how they are very different as we go along. Like for example, in this case, constants are program elements whose values do not change. So you simply say tf.constant of 10. As simple as that. Placeholders, on the other hand, placeholder are, you simply say that, hey, look, there's a value that's going to come into it, but this value will come in at a later point. You're saying that there's a value that's going to come, but this value will come in at a later point. They are also actually a form of a variable only, but it's just that you're defining what type it is going to be. You're saying, hey, this is a placeholder, and expect a float 32 value coming through, or expect a string value coming through into this. Right? You're saying X and Y, and you're saying that expect a float or a string value to come through. So you're calling this as a placeholder value. So you're sort of booking that slot and saying this is what is going to come through. Then you have an actual variable. right? In this particular case, you have an actual variable. So right now what you're saying is that W in this particular case is a variable. So like, for example, right now TNA is called TF dot variable of 3 and TF float 32. What you're saying is that right now the value is 3. I can change this value later on. I can change this value to something else. Currently, the value of this particular weight is, or this particular W is 3. It can become something else later on. These values can change as they go along. That's what a regular variable, just like how we all know what a variable is. Let's quickly do a small, I just wanted to kind of show you how the whole variable things work, and then we'll dig into more depths. It's not that I want to kind of start using them right now because we really don't know how to use a TensorFlow library, but I just wanted to introduce you to those constructs. Yeah, okay. So if you see, my TensorFlow is now up and running. So I've done an import TensorFlow as TF, and as you can see here, if you observe here, I'm essentially creating these as constants. Right, I'm just constant 1, TF dot constant of 3, 3.5 Sparta, and then false. So these are our different constants that I'm assigning. And as you could see here, when I print what these constants are, TF dot tensor, this is an int32, TF dot tensor 0.45. There is no shape. Observe that there is no shape because these are single values that you see over here right now. If, for example, you do something like this, right now, if you observe, the first one is TF of tensor 1, 3, because I have two values and the shape is 2. 2, comma, just like your Python tuples. So 2, comma essentially means it's one-dimensional array, right? And if, for example, if I pass this as a list of lists, then this will automatically be a tensor 1, 3, 3, 4. The shape is 2 by 2. Simple, pretty straightforward, nothing very complex, just like a NumPy array, two-dimensional NumPy array. This is also a tensor. It's just that this is again shape of 0. I mean, no shape because it's a scalar in a way. Same is the case with the others as well. This is Boolean type. This is string type. Yeah, I mean, so basically, I've ended up installing a version 2 of TensorFlow, and that's essentially a reason why supported in the long term. TF. There you go. So yeah, right now what I've done is I've just created these 4 constants and I've just said session.run. But then I've essentially wrapped them inside a list, and I've asked it to simply do a run. So it has returned a list of all these values, nothing else. But look at this here. So I'm defining 2 methods over here, or 2 graphs. Think of these as 2 computational graphs that I'm sort of creating here. And I'm calling something called as addition, and I'm calling it as multiplication. And I'm doing a session.run, and addition and multiplication have simply been returned. So this is basically 50 plus 10 and 20 plus 20. 20 times 20, it has simply returned a value, as you can see over here right now. Now, the thing here, of course, is that when you talk about the same, similar stuff over here as well, as you can see, I'm just passing a couple of lists over here. These are 2 tensors with dimension 1, 2 constant tensors with dimension 1. And what I'm doing is I'm simply adding them and I'm simply multiplying them. And as you can see here, the values are simply being returned as, as simply the multiplications of corresponding values. 1 into 5, 4 into 2, 3 into 3, 4 into 2, and 1 into 5 again. So it's simply corresponding value multiplication. Essentially, 2 vectors are being simply multiplied right now. That's all that we see in this particular case. Nothing really out of the world. Here is where the interesting part comes in. Now I'm defining, let's say, 2 string values as constants, and I'm just running an addition on top of it. As you can see, a string addition, string concatenation typically takes place. Same stuff. Now here's where I'm defining a placeholder, right? Defining a a placeholder right now. So when I define a placeholder over here, I'm saying A, expect an int 32 value to come through. And now I'm saying B is equal to A into 2. But B is, let's say, another outcome. B is now, let's say, the output of A, whatever this A into 2 is. I'm saying B is simply nothing but A into 2. Oh, so this B is just Unicode, guys. Yeah. Okay, it's just saying it's a Unicode text. That's what it is. Again, so here if you see B is equal to A times 2, and I'm simply saying A session dot run. I'm saying run this particular thing, but along with it, what I'm also saying is that I'm saying assume the value of A as 10. Remember, A is a placeholder value. So I'm assigning the value of A during the execution. The value of A is in this particular case is being applied during execution. So when I run this, the value of A is assigned as 10 and the value of B is computed as 10 into 2 and the value is returned as 20 in this particular case. That's the beauty of the placeholder value. Again, if you ask me what is the value of A right now, the A value is still a placeholder. It is still an empty value. There is nothing inside it right now. It is still a placeholder value. It only assumes the value of A as 10 in the execution of this particular session. Yeah, when you run this, what essentially it is doing is it is simply executing B. B is simply nothing but a multiplication of A and 2. A value is 10, so it is simply running the value of B and returning the value of B. So in this particular session execution, the value of B is 20. That's all that it returns. I'm simply asking it to return B. Right. So when I say B plus B, it'll return it as 40. So it is executing this. I hope that makes sense. So it is simply executing this particular piece of code that you see. But when it has to execute this, it needs what the value of A is. So if, for example, if I don't pass this, it'll throw an error, invalid argument error. It says you must feed a value for a placeholder, tensor placeholder with type 32. Right. So I'm just going to pass that, and when I pass it, it just simply gets executed. Okay. Same thing here as well again. Again, I've assigned this as a placeholder value. Same thing, I'm executing name1, and I'm saying for this particular execution, assume the value as Sam. Okay, that's it. So now look at this here. Again, I'm saying variable 1 is TensorFlow dot variable of 30. This is a variable now. Global variables initializer. This is basically simply initializing all the variables. This what it does is whatever the variable I've assigned, it assumes it basically initializes that particular variable. It runs the initializer first, and then the variable 1 is sort of available for me everywhere. Moving forward, the variable 1 is sort of available for me everywhere. You can ignore these two for now. Just don't worry about this as much, because in this particular case, I've assigned the variable and I'm trying to access this particular variable, but this particular variable doesn't exist because it is uninitialized, so to say. According to it, it is uninitialized. So one of the things that you need to do is you need to basically initialize your variables before you start using them. And the way you initialize them is by running those few lines over there that you need to initialize the global variables initializer, and then you need to run the session. Okay. Again, this is very fundamentals of very basics of TensorFlow. The default TensorFlow that is installed in my library in my system is TensorFlow 2, but then this notebook is available in your learning management system, LMS. Please visit your LMS and then you will be able to access all of them there. Okay, great. Okay, now that we've sort of at a very high level sort of got ourselves introduced to TensorFlow. Not that we know what TensorFlow is. It's just that we, at a very broad level, we sort of know what this TensorFlow is. What we are going to do moving forward is that we're going to start leveraging again these fundamentals, very simple fundamentals that we just kind of that we just kind of learned right now, and then we're going to build on top of this. We're essentially going to start building neural networks. But of course, to start building neural networks, we need to know how to build a neural network in the first place. So right now, what we're going to do is we're going to go back to our fundamental concepts of neural networks, and we learn how to actually train a simple neural network, how to actually build a neural network. Forget about TensorFlow and everything. What we're going to do is we're going to first start to train a simple, extremely simple neural network, like how you see on your screen right now. This is a very simple neural network, guys. Right? Simple perceptron. Right? It's a simple perceptron model, not multi-layer, a single layer perceptron model that we have currently. Okay. And essentially, this is basically like y is equal to w1 x1 plus w2 x2. That's basically what we're training over here. Something like this. So you have so what we're essentially training is you have 2 x1 x2 w1 w2 and this is y. That's it. There is just a summation over here, and there is basically an identity activation function. That means no activation function. So in this case, y is equal to w1 x1 plus w2 x2. That's all that we are training over here. Given a specific value of x1 and a specific value of x2 and a specific value of y, I'd want to find the corresponding values of w1 and w2 in such a way that my model gives me the lowest possible error. Right? Let's say the x1 value is 10 and the x2 value is 20, and the y value is, let's say, has to be 30. W1 and w2 should be 1 and 1 respectively. Nothing very complex, right? Similarly, if I want this to be, let's say, if I want this to be, this is 10, this is 20, and if I want this to be, let's say, 29.8385, then what should w1 and w2 be? God knows, we don't know what those need to be right now. Right? There can be any numbers. We can assume them to be something, and then we can basically you can assume some value of w1 and you can compute the corresponding value of w2 and all of that. But if you were to do it the actual neural network way, how do you go about solving this particular problem? So we're going to come back, and the aim is going to be for us to actually start to train this simple model. Yeah, this simple, very simple model that you see over here. So for example, x1 is 2, x2 is 5, and I want a y as 31. So in this particular case, I want to simply train a neural network model, and I want it to build until the error is 0. So if you see at this particular value of w1 and this particular value of w2, almost at this value of w1 and this value of w2, the error becomes 0. That's what I'm saying. Similarly, if I have a x1 is, let's say, 10 and x2 is, let's say, 20, and I want my output to be 30. This is different values that we've tried. We still haven't been able to completely come to a solution, but we have a framework to come to a particular solution in this particular case. So these are different approaches of coming to an outcome, guys. So like, for example, 1 and 1, you see, right at word go, you hit the 0 because you're initially starting your w1 and w2 with 1. So you don't really need to optimize any further. You started with 10 and 20 and your y is 30, and you're saying w1 and w2 is 1 by default. So the error starts at 0. But if, for example, instead of 1 and 1, let's say you started at 2 and minus 1, that's where things become a little tricky. So you have to keep trying until you basically come to a particular point where you see that the error becomes 0. So we keep running it. Let's say in this case, I've run it 50 times. I can run it 100 times probably, and I can hope that it kind of the error sort of becomes close to 0. Still, the error is -7. The error is actually extremely high right now in this particular case. Okay, let's take this simple use case, right? So it's basically as simple as saying, hey, look, right now I have like, I essentially I have an e-commerce firm. I have multiple ways of reaching out for my products, and right now I'd want to do that. I want to increase traffic. The end goal is to increase traffic. But then if I were to increase traffic, one of the challenges that I have is I want to do my marketing, but I want to do my marketing via multiple sources, right? Like for example, you can do it via email, direct, paid ads, referral programs, social media, or organic search. You can essentially do this marketing via multiple ways. The problem here is that you can either use just one of the platforms for publicity or use a variety of them. You can basically use one of them or many of them. Basically, you can pick whatever. The point, of course, here is that you can right now, everything has its own advantages and disadvantages. Like for example, in the case of paid ads, there's money involved. In the case of referral programs, you have to reach out to existing people. For social media, you need to hire a digital marketing company. For emails, again, you need an email marketing team that can start doing it. So at the end of the day, you want to increase sales, but the thing is, you want to increase sales at the cost of there is some amount of money that you will have to invest into each of these different cases. So at the end of the day, if I were to sort of try and evaluate how much sales am I going to get based on the money that I spent on emails, or money that I spent on direct ads, paid ads, or referral programs, or social media, or organic search, what I need to do is, of course, upfront, I need to start projecting this. I need to make a projection. I need to make a prediction of saying, okay, if I invest X amount of money on email marketing, or if I invest X amount of marketing on paid ads, or if I invest X amount of money on, let's say, referral programs, how much sales am I going to get back? I need to make a prediction like that. I need to start making predictions of the sales that I'm actually going to get as an outcome, because I don't want to invest on everything. I mean, investing on everything is like basically burning money. So I want to invest in such a way that I can maximize my margins or maximize my sales in whichever form or shape. So to do that, one of the most important things that I have to see is I have to evaluate firstly which of these approaches gives me the most amount of benefit. Now, see, by the way, these are not the only ways, right? If each of these is, of course, again going to have its own subcategories. You will have multiple subcategories. You'll have multiple other ways of starting to market towards people. The point that I'm trying to drive here is when you're trying to solve a problem like this, right? If you think of it, it becomes like super difficult for us to sort of predict sales. And at the end of the day, I want to predict sales in this complete problem. I want to predict sales. So it becomes super complex because I have multiple parameters to look at. I have multiple inputs. I have money that is being spent on emails, referral programs, paid ads, direct social media, organic search. I essentially have multiple ways of targeting my customers and multiple ways of multiple ways of targeting my customers and of course driving sales. But at the end of the day, when I would want to solve, if it is, let's say, emails only, or if it is only referral programs only, then based on my historical data, I can tell you how much money to spend on referral program. Or if it is just direct media or direct marketing, or let's say if it is just social media, I can come up with some ways of based on historical information, I can make some kind of prediction using a simple linear regression or something. But when I have so many different parameters coming in and so much of interplay, like for example, your social media might also impact, let's say, your direct marketing, or your direct marketing may impact, let's say, your organic search, or social media may impact your organic search. So you don't know, and there's a lot of interactions that can happen between all of these as well. Like for example, somebody might get an email, but then they might some other time actually start visiting via some kind of an organic search. So there's a lot of interactions that happen between each of these features as well, or each of these inputs as well into predicting sales. So doing these predictions upfront on historical data with simple models is not possible, and that's exactly where we start requiring, the benefit of complex neural networks, or essentially your neural networks where you have multiple hidden layers in between, multi-layer perceptrons. That's essentially where your multi-layer perceptrons and your feed-forward neural networks are going to be coming very, very handy. Single layer perceptrons are good enough for, let's say, a single, when I'm making a prediction of my sales just on the basis of one or two inputs. But when I have multiple inputs, that's where things get very, very challenging. And that's where you require more complex approaches to solve problems. That's where multi-layer perceptrons can become more useful. Yeah. So yeah, before actually, let's talk about your fundamental differences between your multi-layer, single-layer perceptrons and multi-layer perceptrons. We all know this. We don't have to sort of redo this thing time and time again. Single-layer perceptron, of course, no hidden layers. Multi-layer perceptrons have more than one hidden layer. Except for one input layer and one output layer, there is at least one hidden layer. You have one input layer, one output layer, and you have at least one hidden layer in between. That's basically what is referred to as a multi-layer perceptron. Also, and if let's say this one hidden layer becomes, let's say, many hidden layers, 20, 30 hidden layers, that's when we start calling it deep learning models, because your network is like extremely deep. That's when we start calling it, instead of calling it multi-layer perceptrons, we start calling it deep learning models.
Just a quick info, guys. Test your knowledge of AI by answering this question. What is artificial intelligence? A. Putting your intelligence into computer. B. Programming with your own intelligence. C. Making a machine intelligent. D. Putting more memory into computer. Comment down your answers in the comment section below. Whoever gets the correct answers will win 5000 points in Intellipaat wallet. Subscribe to Intellipaat to know the winners. Now, let's continue with the session.
And by the way, each of these nodes that you see here is a neuron. And when you talk about a neuron, you have multiple inputs coming into the neuron, because if you see, just take this particular circle that you see here, or this particular neuron that you see here, there are multiple inputs coming in. And when multiple inputs come in, what you do firstly an aggregation, and then you apply an activation function, and then you give an output. Same is the case here as well. You have multiple inputs coming in, you run an aggregation, you apply an activation function, then you return an output. So every neuron is doing this. Every neuron is simply nothing but one circle inside your neural network. So every neuron is performing an aggregation and applying an activation function and passing the value to the next layer. So there is some kind of computation that's happening at every neuron, some kind of information that is basically getting generated at every neuron. So think of these as signals. There are signals coming in, and based on multiple signals that are essentially coming in, what you're doing is you're passing a few signals, you're transforming a few signals, you're applying some kind of changes to a few signals, and then creating newer signals. And in combination, all these signals put together again will create another signal. So think of what simple input of signals can actually achieve for us at the end when you run them through a multi-layer perceptron. The point being that multi-layer perceptrons are actually pretty good. That's the point that I'm trying to drive here. Yeah, I mean, broadly speaking, this is like the we've already spoken about this. For the sake of the slide, let's just go through this. You have an input layer, hidden layer, output layer, same thing. Yeah, just one point is that here, if you observe in this particular case, there's also a bias that's getting trained. Just like your constant, if you observe, the bias term is 1, but the weight is W0. So I'm training W0 because there is no input coming through. The input is always 1. The input is constant. Just I'm training a W0. W0 is nothing but a constant. So W0 plus W1x1 plus W2x2. So W0 in this particular case becomes like your intercept. So the weight in itself becomes like your intercept or your bias or your constant value, so to say. 1 W0 plus W1x1 plus W2x2 becomes the value in here. Okay. Same here as well. Again, I'm training another bias term in this particular layer as well. Yeah, so this is all straightforward. Yeah, there's nothing really out of the world in here. We all understand this pretty straightforward. So going back to that solution, what is going to happen is that at the end of the day, I want to predict if somebody is going to make a purchase or not. Or I can also predict, I mean, in this case, there are two outputs. You can also predict, let's say, sales. You're predicting if somebody is going to make a sale or not, or make a purchase or not. Or you can also predict, let's say, one single neuron, the amount of sales. So all these go in as inputs, and these inputs essentially will then make one single prediction for you, which is, let's say, you're predicting the sales or predicting if somebody is going to make a sale or solve it as a regression problem or a classification problem based on the scenario. Yeah, let's take this another example. Suppose you have the following data set, right? Let's say you want to predict somebody's final results. of if somebody's going to fail or pass. 0 is essentially fail and 1 is basically pass. And I have this information, the amount of hours that somebody has studied and the amount of midterm marks that somebody has achieved. So I want, based on this information, I want to predict if somebody is going to make it through their final term or not. So in this particular case, if you observe, again, based on the input that we have, I have two inputs, are studied and midterm marks, and based on this, I want to predict if somebody is going to actually make it through their final term or not, based on this information. Now, of course, I want to first learn that I want to learn the patterns that basically go through this. Firstly, this is what has happened historically. This is historical information that I see. I've captured this historical data set. But based on this historical information, what I would want to do is, if let's say there's a new kid who's studied for 25 hours and who has scored 70 marks in their midterm, I want to predict if the person is going to. I want to predict what is going to happen to this particular person. Pretty simple. This is a binary class classification problem where I'm trying to train my model on the historical data, and I'm trying to predict on this particular sample data set. That's all that I'm trying to do. Like for example, in this particular case, take this simple example. So what I have is, this is R studied and this is midterm marks. And let's say for whatever maybe the reason, I've decided that I'm going to go with a multi-layer perceptron that looks like this. And I have multiple weights, W1, W2, W3, like 3 different weights flowing in from different directions. And of course, based on the weights that I have over here, it's not just W1, W2, W3. This is, of course, this is my bias. This is X1 and X2, 2 inputs bias. I'm going to have 1, 2, 3, 4, 5, 6. Essentially, I'm going to have 6 weights in here because I have 2 inputs over here, 3 inputs from here, and then 2 inputs in here. So I essentially will have 6 inputs, 6 weights. And what I'm going to do with these 6 weights is, based on some random values of weights, I'm going to make a prediction to start with. I'm going to start with some random values of weights and I'm going to make a prediction. Let's say the target value is 1 and 0. Let's say I end up making a prediction saying the value is, let's say, the probability of passing is, let's say I make a prediction of 0.4, and let's say I make a prediction of 0.6. The value that somebody would pass, the value that somebody would fail. Probability of somebody would pass is, let's say, 0.4. The probability that somebody would fail is 0.6. So whatever may be the reason for that particular student, 35 marks and 67. So if you go back to the historical data, 35 and 67 is the first kid. This person has actually cleared the exam. This person has actually cleared the exam. But we made a prediction that from our model, we said that there is a 60% chance that he would clear the exam, and 40% or rather 40% chance that he would clear the exam, and 60% chance that he would fail the exam. So if you now look at it, there's a collective error that is associated to this particular model. I initially made a prediction. My prediction says that the person is only 40% likely to clear the exam. But if you compute the error, there's an error of around 0.6 error on this node and 0.4 error on this particular node. There's a significant amount of error in my model with my first record in itself. It's just simply this particular data point in itself. So now what do I do? My challenge right now here is that I made a prediction, but that particular prediction is incorrect. So now what I need to do is I need to perform some kind of a correction to my weights in such a way that my prediction gets corrected. So I can apply some kind of a change to my prediction. So that's change to my weights. So how do I change my weights? I'm going to perform these weight changes based on how much error is being contributed by each of these nodes. Based on how much error each of these nodes is basically contributing, that is the amount of correction that I'm going to make on those weights. Okay. So what does that mean? What do I mean by that? So when I say I want to make a correction, like for example, in this particular case, if I'm making a negative, if I'm basically getting a value of 0.4 over here, and if I'm getting a value of 0.6 in this particular node, the reason I have a 0.6 in here could be driven because of one of these three weights. Because I'm getting values from these three places, but one of the weights is significantly high, hence the value in this particular node is extremely high. So I have to reduce this and I have to increase this. For me to do that, I need to basically target that particular weight over here that is causing this value in this node to be very, very high. So I have to perform some kind of a magic over here, such a way that I propagate this error backwards into my network, especially in the direction where in that particular direction which is causing the model to make errors. Yeah, I have to pass that error back in such a way that I pass it back in such a direction which is actually causing that particular error. So that process of propagating the error backwards into the network in the direction of the error causing weight is what is referred to as backpropagation. Right? So the backpropagation essentially is there is an error that is at the last layer of my network. What I would want to do is I want to capture that particular error and then propagate that error backwards into my network and see which nodes are causing in that particular order, whichever nodes are causing the higher amount of error, I would want to pass the error backwards into my model. When I pass the error backwards into the model, firstly, I will know which nodes are causing higher amount of errors. Once I know which nodes are causing the higher amount of errors, then accordingly, I will change those weights to basically make sure that the contribution of those particular nodes or those particular weights is minimized in my final outcome. Yeah. So that process is what is referred to as backpropagation and weight updates. Okay. So once I, let's say, perform that particular step, once I, let's say, perform the backpropagation and once I do my weight updates, what is going to happen is, there is some math that goes on. We'll come to that math in a minute. But there is some amount of mathematics that goes in the background, and what that math basically causes is my errors now start to minimize because I have made some changes to my weights. The weights that were originally W1, W2, W3 or whatever have now become W4, W5, W6 because these are updated weights now. They are not the same weights. So these new weights, now if you observe, they are basically making a prediction that the person is now 80% likely to pass an exam and the person is 20% likely to fail the exam, which is much closer to what it was previously. Previously, we were making a prediction of 0.4% and 40% and 60%. Now we are saying 80% and 20%, which is much closer to reality because in reality, the person has actually cleared the exam. So now if you compute the error, which is 1 minus 0.8 and 0 minus 0.2, so the error is actually much lower than what it was earlier. Earlier it was 60% and minus 40. Now it is 20 and minus 20. So relatively the error has now gone down. But to again still perform the same step, to still make this model more better, what I would do is that I'll again perform the same step. Now I still have the error. I'll again identify which nodes are causing the higher error. So I'll propagate the error backwards and identify which nodes are causing the higher error. Now, until where am I going to propagate this error? Am I just going to propagate the error until the previous layer? No, I'm going to propagate the error all the way until backwards, all the way until the first layer. And then based on which nodes are causing the high error, accordingly, I will change those corresponding weights. Because when I change the weight, automatically the contribution of that particular node becomes smaller. The moment the contribution of that node becomes smaller, automatically what will happen is that it will directly impact my outcome. And that way my outcome will become more closer to reality, more closer to the actual prediction. But what we did to the exactly, so Prashant, that's exactly where I'm going to come to. What we did to the final to actually update the weights is what we're going to talk about in a minute. I'm just kind of telling you the life cycle of this particular problem, right? So we'll talk about the back propagation right now, right? So I make a prediction. The prediction is incorrect. I want to basically pass this error backwards all the way until the beginning. But how do I do it? Right. So let's take a simple example. Let's not worry about all of this as much. Let's actually talk about, let's take this simple network. Let's start working with the actual data in itself. Okay. So right now what you're seeing in this particular case is you are seeing two inputs. Actually, let me actually copy this. So yeah, this is our network, right? These are my trainings. Training data is, let's say, 0.5, and my 0.5, 0.1. 0.5, 0.1 basically meaning the input 1 and input 2 are 0.5 and 0.1. The weights are like how you see here right now, the 0.15, 0.2, 0.25, 0.3. So these are the weights like how you see the way they are right now. And what you also see in this particular case, you also basically see is that the biases are 0.35. That means bias contribution of weights is both 0.35 and 0.35 in both cases. Similarly, 0.6 and 0.6 in both cases. So you have the weights and everything. You have the network. H1, H2 is the hidden layer. O1, O2 is your output. And what you're saying is for an input of 0.05 here and 0.1 here, the actual output should be 0.01 and 0.99. That is what the actual output should be. For 0.05 and 0.1, we want the neural network output to be 0.01 and 0.99.
If you want to make a career in data science, then Intellipaat has IIT Madras Advanced Data Science and AI Certification Program. This course is of very high quality and cost effective, as it is taught by IIT professors and industry experts.
Now, of course, two steps: forward pass and the backward pass. Forward pass is where you actually go through and compute the error and see how bad the model is, or how close it is to the actual predictions, the actual values, and then compute the error and pass that error backwards into the network. So what's going to happen right now? By the way, the other point that I forgotten to mention over here is that the hidden layer has a sigmoid. Let's say we're applying, let's say, a sigmoid activation in the hidden layer. Let's say we're applying some kind of a sigmoid activation in the hidden layer. Okay. So the first one is the forward pass, right? So if you look at the H1, this is why I kind of copied this here. Yeah. So right now what you observe is here is that you want to compute H1. H1 is nothing but this value. H1 is nothing but, if you observe, it is I1 into W1, because you have a line going from I1 to H1. So I1 W1 plus I2 W2 plus B1. So it's I1 W1, I2 W2 plus B1. That's exactly what we're saying. So I1 W1, I2 W2 plus B1. That's what we're seeing. So I1 W1 plus I2 W2, I1 is 0.15 and W1 is 0.05, I2 is 0.2. Sorry, W2 is 0.2 because W2, this line is 0.2, and then the value is 0.1, and then we have B1, which is 0.35, so the value is 0.3775. That's essentially what we get here as H1 output. So the H1 output is 3775 in this particular case. So W1, W2, W3, W4. So these are the values that you see over here. Okay, brilliant. Similarly, this is the value at H1, but mind you, that's not the output at H1. That is the value which is computed. The half of H1 is that, but the output from H1 is going to be a sigmoid transformation. Remember, I'm applying a sigmoid transform. So all that I'm going to do is whatever is the net H1, which is 0.3775, I'm simply going to apply a sigmoid transform. The moment I've applied a sigmoid transform over here, the value simply become 0.59, because 1 by 1 plus e to the power of minus 0.3775, it is 0.59. So the output to H2, carrying out the same process for H2. Similarly, even if you compute the same for H2, if you want to simply do the same for H2, you can actually do it for H2. H2 is going to be same one. So W3 H2 plus, sorry, similarly for H2, you have values coming in from here and here. So it is going to be I1 W3 and I2 W4. There's going to be I1 W3 and I2 W4 and plus B1, or rather in this case plus B1. It's simply B1 because it's the same value that's going to come through in this case. So if you do the same computation and then you apply the sigmoid transformation, the output of H2 is going to be 0.5968. 0.5932 and 0.5968 are the values from output of H1 and H2. So the values that are going to come out from H1 and H2 are 0.5932 and 0.5968. Now comes the next step. The next step is another pass. There's another forward pass. The forward pass is where I'm going to pass the value of H1 and H2 and then compute O1 and O2. Great, let's go ahead, let's do the same. So if you do this here, net O1, again, so net O1 and out O1, same process. So W5 into O1, W5 into H1 that you see here, and W6 into H2, W6 into out H2, same values. So 0.5932 into 0.4 and 0.45 into 0.59, 0.45 into 0.59 plus B2. This line, you also see this line going through it. So this is B2. B2 is 0.6, 0.6 into 1 because the value is by default 1 here. So you have 1.1, and then you again apply the sigmoid transformation because again, even the outside layer is also a sigmoid transform. This is a classification problem. So the outer layer also is applied in, we are also applying a sigmoid transformation here. So when you perform a sigmoid transformation, again, you get a 0.75 at the end. Same for out 2, it is 0.7729. Yeah. So right now, forget about everything else. We are not applying any kind of softmax or anything. We just applied a sigmoid transformation. Forget about doing softmax or anything, just for simplicity purposes. Ideally, what should have happened is we should have applied some kind of a softmax. If it is a classification problem, we should have done some kind of softmax at the end to sum up the values to 1. But that's okay. In this case, we are not doing anything. We're solving with something like a regression problem, so it's okay. Let's not worry too much about it. So you have output 1 and output 2. They are supposed to be 0.01 and 0.99. We've got output 1 as we've got output 1 as 0.75 and output 2 as 0.77. Nowhere close to what they're supposed to be. Yeah, nowhere close to what they're ideally supposed to be. So now what do I do next? I made a prediction with the current weights, and mind you, these weights that you see are randomly initialized. They are not initialized with any rocket science. They're randomly initialized. Okay. So now there is an error. Then the error that we are seeing, if you were to compute the error, is, if you observe the error, the way that we are computing this particular error is we are not simply computing a actual minus predicted value. We are doing a mean squared error. Look at this. Mean of the squared error, actual minus predicted whole square divided by 2. Right? So 1 by 2 into actual value minus predicted value. So error at O1 is going to be whatever was predicted at O1. O1 was 0.75. So 0.75 minus 0.01, the whole square divided by 2. We don't care even if there's a 2 or not. There's no 2, it doesn't matter because this is just a constant anyways. So 1 by 2 into 0.01 minus 0.75, the whole square. Similarly, at error at O2 is going to be 0.99 minus I think that was also 0.7513, 0.77. 0.99 minus 0.77 the whole square divided by 2. Same error. And this is 0.27. This is 0.023. This is relatively smaller. The error in this particular case is much smaller because this is for O2 the value is actually much closer than O1. The O2 value was supposed to be 0.99 and we made a prediction of 0.75. So the O2 value is much closer than O1, hence the error contribution via O2 is much smaller than O1. So the overall error is a summation of these two, which is 0.29, right? The overall error in this particular case is 0.2983. Great, wonderful. Now what do I do from here? Now what we do from here is I need to pass this error backwards into my model. So when I say back propagation, I'm not going to literally pass the error back, but what I'm going to do is I'm going to basically I'm going to pass this error back in such a way that I'm going to pass it more towards the nodes that are contributing to the error most. Now comes the tricky part. So now what I'm going to do is I'm essentially going to find a way to pass this error backwards into my model. Now you tell me, we've been doing all this computation, right? You tell me, between O1 and O2, which is contributing to the error more? Is O1 contributing to the error more, or O2 contributing to the error more? Yeah, O1 is contributing to the error more, because O1 is much far away from the prediction. O2 is much closer to the prediction. Clearly, see, O2 is 0.023, O1 is 0.27. So O1 is contributing more to the error than O2. So what that means is, whatever correction that I have to make, the correction will have to be primarily in the O1 direction, because O2 is okay. O2 also I will have to make a correction, but the correction that I have to make on O2 side is going to be much smaller than the correction that I'm going to make on O1 side. O1, I'll have to make a drastic, or rather larger change on the O1 side than on the O2 side. That's the exact mindset that we're going to carry from here. Right now, you're able to say that O1 is contributing more error than O2 because the numbers are pretty straightforward for us to understand. The moment I say, okay, now we've decided that O1 is contributing more to the error. So now between H1 and H2, that is contributing values to O1, which of these two is contributing more? Is W5 contributing more error, or W6 contributing more error? W6 has a higher weight, but is W6 actually contributing more error? That depends on what are the values of H1 and H2. Because we need to go back and check what are the values of H1 and H2. Because net output of H1 is 0.3775 and net output of H2 is 0.59. Also, the H2 weight is also very, very high. So between W6 and W5, the error contribution by H2 is actually much higher than H1 towards O1. Does that make sense, everyone? So what I will have to do is, between W5 and W6, W6 will have to be reduced significantly than W5. For us to individually track each of these weights all the way until the back, imagine how complex it could get. I mean, if you were to manually do it and individually do it, it'll be super complex. So, and you're like spot on. So right now it is like just one hidden layer, so I'm able to do it manually. But what if I have, let's say, like 20 hidden layers or 10 hidden layers, and in each hidden layer, if let's say I have like 40 nodes or 20 nodes, then life's going to be like super difficult because I cannot manually track them down. That's exactly where we need to take the help of math, right? That's where we need advanced mathematical concepts. That's exactly where derivatives come into picture. What derivatives and derivatives give you is partial derivatives basically give you the gradient, or rather the contribution of the impact. So when I take the gradient at O1, gradient of error at O1, it will show that the contribution of W6 is much higher than W5. Similarly, when I take the contribution of H1, it will say that W2 contribution is much higher than W1. So the point simply being that when I start taking more and more when I start bringing in concepts of derivatives, and when I start bringing in concepts of computational graphs, things can become much more easier to handle. We can start representing all of this as mathematical equations, and that way things become more easier. computationally they become easier, not from an understanding standpoint. Understanding standpoint, things becomes a little more complex for us, but computationally things become easier. Let's actually look at it. Let's actually look at what we are doing here. Cool. So I just hope before we get into the actual math, I just want your intuition to be at the right place. Intuitively speaking, we are going to go back and correct those weights which are contributing higher. That's the sole purpose of this exercise. Now we've computed the complete error. Now comes the actual part. So let's take this O1. Let's take O1, right? There is an overall error. This is basically an enlarged diagram. So the diagram that you see in this slide is essentially an enlarged diagram of the O1 neuron that you see here. So if you see, there is an total amount of error, and that error is contributed by firstly O1, and O1 is basically contributed by net O1, because net O1 is simply nothing but, again, which is contributed by W5, W6 and B2. So if you think of it, what is causing what? If E is high because O1 is high. O1 is high because net 1 is high. Net 1 is high because net of O1 is high because either W5 or W6 or B2, one of these is high. So I have to start tracking back what is causing this error, and that's essentially what backward pass is going to be all about. So the way that I'm going to look at it is, at the end what I want is, I basically want, how much is E, what is the rate of change of error with respect to first W5, what is the rate of change of error with respect to W6, and what is the rate of change of error with respect to B2. Yeah. So what I want to understand is,
Just a quick info, guys. Test your knowledge of AI by answering this question. In which of the following application does AI has its expansion? A. Planning and scheduling. B. Game playing. C. Robotics. D. All of the above. Comment down your answers in the comment section below. Whoever gets the correct answers will win 5000 points in Intellipaat wallet. Subscribe to Intellipaat to know the winners. Now, let's continue with the session.
between W5, W6 and B2, I want to understand what is the rate of change of error. When I say rate of change of error, that means which of these weights is actually contributing the highest. Okay. So when I say rate of change of error, it's typically represented by a derivative. So what I'm saying is that I want, in a lot of ways, what I am essentially asking for is, I'm basically saying, so we've computed an error over here, right? So this error term, I want to compute. So DE, D or dou doesn't matter. Dou is basically a partial derivative because there are multiple things that are coming through. I cannot make a complete derivative. So I'm going to simply say dou E by dou W5 is what I want to compute. Similarly, dou E by dou W6 and dou E by dou B2. So the error contributed by W5, error contributed by W6. Let's for the moment, let's not worry about this too much. The computation of this is very similar to the other one. I want to compute dou E by dou W5 and dou E by dou W6. But you have to remember something, that if you look at that diagram previously in the previous slide, dou E by dou W5, if I have to compute dou E by dou W5, I cannot compute it directly. So the way I'm going to compute it is, A is first directly dependent on O1. So what I'm going to do is, I'm going to make use of a concept called as chain rule in differentiation. Simply put, what I'm saying is that dou E by dou W5, or the rate of change of error with respect to the W5 weight, is nothing but rate of change of error firstly with respect to output of O1. So I'm going to say simply out O1 multiplied by rate of change of error at output O1, rate of change of output O1 with respect to net O1, because this is changing as a dependent of net O1. Okay, so then this is going to be dou output O1 divided by do net O1, similarly multiplied by do net O1, or rather do net O1 by do phi, do net O1 divided by do W phi. That's essentially how I represented the whole thing. This is basically from a concept called as chain rule in mathematics, in differentiation, partial differentiation. If you're not fully aware, it's okay. All that I'm simply saying is that, hey, look, I want to compute how badly the error is being contributed by W5. Similarly, I want to compute how error is being contributed by W6. But how do I do that? The best way of doing it is I compute do E by do output O1, do output O1 by do net O1. So I want to identify how output is getting contributed by net O1. Then again, similarly, how net O1 is being contributed by W5, or how net O1 is being impacted by W5. And when I multiply all of that, I'm going to get how do E is getting, or rather how my total error is getting impacted by W5. That is what this is simply going to be. Similarly, I'm going to do the same thing for do E by do W6 as well. Yeah. So if I were to put it into actual math, this is how it's going to look like. So don't get terrorized by it. It's not very difficult. It's the same thing. So do E total by do out O1, do out O1 by do net O1, do net O1 by do W5. Same exact thing that we just did. This is the same exact equation that we kind of put together over here. Nothing very complex. So we are simply calculating the rate of change of error with respect to change in W5. So when W5 changes, how much does the error change is what I'm trying to compute. Because if I know that if W5 is contributing heavily, then I will change W5 more. If I see that W6 change in W6 is contributing heavily to the outcome, then I will change W6 heavily. So to make that decision, which one has to be changed with how much, I first have to identify which one is contributing how much, and that's what I'm currently doing right now. I'm just trying to firstly compute how much is the error being implemented. So now here is where I'm going to start computing each of these terms. So firstly, do E total by do output O1. So for that, what we need to start doing is I'm going to start computing each of them separately. So firstly, how do I compute my error? It is 1 by 2 into the actual values, whatever my actual values were in the previous case, which is nothing but target O1. Let's call it target O1 minus the whatever my predicted O1 was. Predicted O1 is simply nothing but output O1, the whole square, plus 1 by 2 into target O2 minus output of O2, the whole square. Guys, this is exactly the same as computing the error here and computing the error. I just put the equation together. Earlier, this is how we computed the error. So now what I'm saying is I'm going to compute do E by do output O1. I just have to partial differentiate this whole thing with respect to this. That means everything else will remain constant. So basically this term will simply vanish, because target O2 and output O2 are, I'm assuming these are constant. So this whole thing will vanish. This whole thing will become 0. And I have to simply do a partial derivative over here. So 1 by 2. So 2 by 2 is what it is going to become into target O1 minus output of O1. And this will simply get cancelled. And I have to differentiate this one. And that will be minus 1. So simply put, minus 1 of target O1 minus output O1 is what is going to simply be. So that's as simple as that. Minus of target O1 minus output O1. That's what this is, as simple as that. Okay. And I simply substitute the values and I can compute what that one is. Target O1, I know what the value is, and output O1, I know what the value is. I can simply compute what that is. That way I've completed do E total by do output O1. So I've computed this one. This one is complete. Okay, brilliant. So let's move forward. So the second one is do output O1 by do net O1. So for me to firstly compute this differentiation, the first thing that I have to do is I have to first understand how output O1 is being computed. If you go back and see, firstly, the output O1 equation is simply nothing but a sigmoid transform. If you go back and check this one, see, output O1 is a sigmoid transformation of net O1. It's exactly a sigmoid transformation of net O1. So let's go back. This is going to be simply 1 by 1 plus e to the power of minus net O1. That's essentially what output O1 is. So now I have to differentiate output O1. So do output O1 by do net O1 is going to be a partial differentiation of this whole thing. So when you do a partial differentiation of this thing, especially your sigmoid transforms, there is a pretty straightforward way of doing a sigmoid transform. So a sigmoid, sigmoid into 1 minus sigmoid. Basically, that is what your sigmoid differentiation of sigmoid transformation. Let's say you have a sigmoid of x, and you want to compute a differentiation of this. It's as simple as sigmoid of x into 1 minus sigmoid of x. That's essentially what the output is typically going to be. So partial differentiation is going to be. And I think to compute something like that, as you observe here, it's the same thing. So output O1 into 1 minus output O1. You simply do a output O1 into 1 minus output O1, which is basically a sigmoid into 1 minus sigmoid. And then when you compute, you're going to get basically a value for your net O1, your do output O1 by do net O1. That will be basically a second term. So this term is also done. This is going to be output O1 into 1 minus output O1. When you do the actual partial differentiation, you're going to get output O1 into 1 minus output O1. So two terms are done. The last term is net output O1 with respect to W5. So if you see how net output O1 is getting computed, which is nothing but, W5 into H5 plus W6 into, I think, W5 H5. Oh, sorry. When I say H5, what I mean is H2. Let's go back one step. So W5 into H2 plus W6 output H2 plus W6 into output H1. W5 into, this is going to be output H2, W6 into output H1 plus B2. That's what your net output O1 is. So net do output O1 by do W5. Again, when you see a do W5, this is going to get cancelled. This will all get cancelled. What you will simply be left with in this particular case is going to be simply output of H2. That is all that you're going to be left with in this particular case, because everything else simply gets cancelled because you're doing a partial differentiation with respect to W5. And that value is as simple as this one, output H1, which is 0.5932. So that's basically a third term. Once you have all these three terms, then you can simply do a multiplication of these three terms and you'll get a simple value out of this. This, my dear friends, is just do E total by do W5. Do E total by simply do W5. Similarly, you'll have to do E total by do W6, do W7, do W8. For all the errors, basically W6, W5, W6, W7, W8, you'll have to basically do an error correction for all these four weights to start with. Okay, but yeah, basically just like how we've kind of updated 5, 6, 7, 8, similarly we will have to do something very similar with W1 and W2 as well. Similarly, do E total by do W1, just like how I've computed do E total by do W5, I will do E total by do W1 and do E total by, similarly it's the same thing but multiple components in here, right? That way what will happen is, right now all my values will simply get updated. All my weights, not the I1, I2 value, they will remain constant, but my weights will now get updated. With the new value of weights, Ignore all of this. So this is W1, W2, W3, W4. They are also now updated. With the new value of weights now, I'm going to go back and rebuild my model. So basically, these are my new weights. W1 is now 0.14. W1 is instead of 0.15, it is now 0.14. Similarly, W2 is 0.19. W2 is 0.19. W3 is 0.24. 0.24. And this is 0.29. W4 is 0.29. So all the weights have reduced a little. Okay. So last but not the least, of course, now that the errors have now all these values have now been updated. So now what would you expect? You computed an error, and based on the error you updated the weights now. So now you're going to run through the model. You're going to run the forward pass again. So when you run the forward pass again, what would you expect? Would you expect the error to be high or low? Error to be reduced? Absolutely right. So with the updated weights, when you run your forward pass again, previously the forward pass gave us an error of around 0.2983, but with the updated, after the first round of back propagation, the total error now has become 0.2910. It has become 0.2983 to 2910. Now you may ask me, dude, this is not a significant reduction. Absolutely yes, this is not at all a significant reduction. But if I run this 100 times, but if let's say I run this 1,000 times, do you think the error will then significantly reduce? Absolutely yes. If you run the same process 100 times or 1,000 times, the error will then significantly reduce. So point being, when you run multiple back propagation, forward pass and back propagation steps, that means your model is basically learning continuously, learning and updating weights, learning and updating weights, learning and updating weights. When this continuously happens, what happens is that almost after around 10,000 times, the error almost drops to around 0.40354 or 50, I don't know, 4 zeros almost 0.4035. It's almost as close to zero, right? So when you run this like 1,000 times, 10,000 times, that's where things become much closer. Things get much closer to your actual predictions. Great question, Deepak. How much time will it take to run 1,000 predictions, 1,000 more times? If you implement it with simple Python, with simple data, like this example, this small example will probably take a few milliseconds, probably a few seconds, maybe 3-4 seconds maybe, to run it 1,000 times or 10,000 times. But imagine you had, let's say, instead of one data point, imagine you had, let's say, 1,000 data points or 100,000 data points, and your network had like 20 layers, and your each layer had like, let's say, 30 neurons. Then in that case, training that could take anywhere between a few hours to probably even a day at times, depending on the infrastructure that you have, depending upon the data that you have, depending upon the size of the algorithm. Training a deep learning algorithm can take anywhere between a few hours to a couple of days. And if you have, let's say, the compute you have, let's say, for example, instead of using a CPU, if you have a GPU compute, that means if you have a graphic card in your system, and if you instead of using regular TensorFlow, if you start using TensorFlow GPU version, then things can be much faster. You can accelerate things a little more. So that triggers us into a different line of conversation altogether. But the point being that deep learning is a time-taking affair. It's not something that's going to happen in like a jiffy, like a decision tree classifier.
In today's session, we'll be talking about some common machine learning algorithms. Okay, so let's dive in. Okay, so we will be discussing some popular algorithms that are useful for machine learning purposes. So basically, as you can see here, in machine learning, we are having two kinds of learning. Okay, the first one is the supervised learning, and the second one is the unsupervised learning. So what does supervised and unsupervised means? As the name suggests, supervised learning means that we are supervising our model. Okay, we are training our model on top of some data set. Okay, and after training our model, then we will try to predict, we will try to test our model. Okay, and we will see if our model is able to predict the future outcome or not. Okay, And if you talk about the unsupervised learning, so in unsupervised learning, we, as the name suggests, unsupervised means we will not supervise our model, we will not train our model. The model will get to know about the data set itself only. Okay, if you basically here we don't provide any learning to the model, to the machine. Okay, we will just provide a data set to the model, and after providing the data set, the machine, with the help of some algorithms, it can able to understand what the data set is trying to say. Okay, basically we will be analyzing the data. Okay, so let's discuss supervised and unsupervised in detail. So first, let's talk about the supervised algorithm. Okay, so in supervised algorithm, the first set of algorithm that we will talk about here is linear regression. Okay, so what is linear regression? See, basically in supervised algorithm, we are having two kinds of problem. The first problem is the regression problem. Okay, the second one is the classification problem. So what is regression and classification? If you talk about the regression problem, then regression basically deals with some kind of, you can say, continuous set of data. Okay, let's take an example here. If you're having some data set, okay, and in that data set, you are having some like a list of houses, okay, and then I want to predict what is the retail price of those houses. Okay, so the price there will be a continuous set of numeric values only. Okay, so here we are talking about some regression problem because we have to predict some numeric value, okay, of those houses. So that is why that problem come under the linear regression problem. Okay, so here we will talk about like we have to predict some value. Okay, some value that is not categorical. Okay, categorical means like if you're having some yes or no kind of value in your data set. Okay, let's suppose let's take an example. If you talk about some like if that particular customer is churning out of any company or not. Okay, so this is kind of a categorical set of values. Okay, but here in this linear regression problem, we will only deal with the exact values. Okay, the salary of any person, or you can say the price of the houses. Okay, so this is what we talk about in linear regression. Only like they are having continuous set of values we have to predict. Okay, now if we talk about the other algorithm, that is the logistic regression. So as the name is have the logistic regression is having the name as regression, but in logistics we always work with classification data. Okay, the regression name is only present in the logistics part, but we always work with the classification problem. So what is classification here? Let's take same data set only. Okay, the data set that is having list of houses. So in logistic regression, we will try see there will be some retailed price of that particular house. Okay, let's suppose there is a house and that house is having a retail price as $10,000. Okay, so if with the help of logistic regression, we can calculate, or you can say the model can predict that that particular value, that particular house has been sold at a higher price or the lower price. Okay, if you talk that particular house is there. Okay, let's say house number 1 is there. Okay, and in house number 1, you want to like I want to predict, okay, that particular house has been sold at a higher price or a lower price. Okay, so this is what a categorical value is there. Okay, if it is sold at a higher price or a lower price. If you take another example, let's take heart disease data set. Okay, we are having heart disease. So there are many set of customers, many set of patients, the values, the data sets that is having all the value of the customers. Okay, so uh, for that data set, for the heart disease data set, we have to predict, okay, if I'm having these kinds of symptoms, then that particular customer is having heart disease or not. So this is also a kind of classification problem. Okay, because we have to calculate that either that particular customer is having heart disease or not. So this is a categorical value. Okay, so this is what we talk about in logistic regression. We always talk about the classification problem. Okay, that is the categorical values. Then again, our next set of algorithm in supervised algorithm is decision tree. Okay, so if we talk about decision tree, so as you can say, the decision tree means we will be talking about some tree structure here. Okay, so basically a decision tree is also a kind of, in decision tree we can work with classification problem also and regression problem also. Okay, if we want to calculate exact value, or we have to calculate the categorical value, that either that particular customer is having heart disease or not. Okay, so these things we can calculate in decision tree. So let's take an example for explaining the decision tree. So let's suppose there is a bank, okay, and that bank, like I want to build a decision tree so that how my model can able to like there are some customers that want to have their loan approval. Okay, so I want to build a model so that my model can able to analyze, okay, if this particular customer is coming to me and that particular customer wants to have a loan. Okay, so if I give loan or not to that particular customer. Okay, so it will build a decision tree. Okay, like it will see their past loan credentials. Okay, it will see, okay, that particular customer has paid the previous amount of loan or not. Okay, if he has paid, then okay, I will go to the yes part. Okay, I will go to the yes part, and then it will see, okay, if I'm having higher loan or lower loan. Okay, higher means like if that particular customer wants higher amount of loan or lower amount of loan. If yes, if that particular customer is having higher amount of loan, then it will not give the loan. If the particular customer is having lower amount of loan, then it will give the loan. Okay, so this is what decision tree is. It will make some decisions regarding the past history of the data. Okay, it will see the past data of those customers. Okay, so this is what our decision tree is. Then if we talk about our fourth algorithm, that is the random forest. So again, in the random forest, I'm having multiple sets of decision tree. Okay, so if we talk about the random forest, so basically random forest combines the output of multiple randomly generated decision trees. Okay, and it will give our final output. So basically random forest is a group of decision trees. Okay, in decision tree we will only build one tree only, but in random forest we can make 100 trees or 300 trees or 400 trees, and with the help of all those trees, with the help of the combination of all those trees, we can able to predict, okay, if I want to give that particular customer a loan or not. Okay, so this is what our random forest is. If we talk about our naive bias, so basically guys, in naive bias we will be dealing with some kind of like you can say data set that is having we can say okay, so if we talk about the naive bias, so in naive bias is also a kind of the classification problem. Okay, so naive bias basically deals with some probabilistic classifiers. Okay, so if I want to you can say talk about, basically in naive bias we deals with some text classifiers. Okay, we will deal with some text kind of data. Okay, here in the linear regression, logistic regression, if you talk about decision tree and random forest, we work with some kind of data frames. Okay, but in naive classifier we always work with some kind of text categorization. Okay, we are having some text kind of data. You can take all those texts in Excel format, and you can work with that data set, and you can able to predict your the whatever task you are having in your text data. Okay, so these are all kinds of common algorithms that we use in supervised learning. Okay,
so, suppose you are a computer vision engineer and a client has approached you with a problem statement in which you have to detect the faces from a set of images that they will be providing, and you have taken up this project, and these are the following steps that you have to follow while building up this project. So, these are the images that they have provided to you. These are some of the images that have taken from their dataset, and here we'll be working on Python with OpenCV. In this project, we will be using the Haar cascade classifier for detecting the faces from multiple images. So, firstly, you have to perform the downloading part for the Haar cascade system. So, here I have written download Haar cascade frontal face default.xml and this raw GitHub code. These are the raw datas for the Haar cascade. You have to just simply save as, and you can save it as desktop, and you have the Haar cascade classifier. So now next we will be just importing the CV2 and glob. So now we will be practicing it in the Jupyter notebook. So firstly you have to import the CV2 library and glob. So I want to tell you that glob is the function which returns us the array of those file name which we will write in the next line. Like we just have to perform face detection on those images which have .jpg extension. So for that I will be writing gimage equals to glob dot glob. So here I am calling the object glob and with the function glob, and here inside the function I will be writing the star dot jpg. So it will take up all the images that have extension .jpg.
If you want to make a career in data science, then Intellipaat has IIT Madras Advanced Data Science and AI Certification Program. This course is of very high quality and cost effective as it is taught by IIT professors and industry experts.
So after that we will detect after getting the glob images. Now we will create cascade classifier so that we can, so as it helps us in getting the face detection. It contains all the features of the images like nose, ears, face, object. These are some of the features of the image. So here we will be writing detect equals to cv2 dot cascade classifier.
Just a quick info, guys. Test your knowledge of AI by answering this question. What is artificial intelligence? A. Putting your intelligence into computer. B. Programming with your own intelligence. C. Making a machine intelligent. D. Putting more memory into computer. Comment down your answers in the comment section below. Whoever gets the correct answers will win 5000 points in Intellipaat wallet. Subscribe to Intellipaat to know the winners. Now, let's continue with the session.
Classifier. Then inside the braces we will be writing which classifier. We have downloaded the Haar cascade frontal face default classifier. So we will be mentioning the same name, Haar cascade. Okay, Haar cascade frontal face default.xml. So now after creating the Haar cascade frontal face default XML file, then what we will do, we will now traverse the glob images so that we can detect the faces. So for traversing, we will be creating a for loop for traverse, or you can also write t image for traversing the image, t image in g image, the glob image. Okay. So now it will take one image at a time. Now in the for loop, we will read the image, a particular image. So for just reading the image, we will write like I have taken image equals to cv2 dot I am read. And what is this reading? The t image. Okay, so after reading the particular image from the G image, now we will convert the images. These are the colored images. The image that it has read, it is the colored images. So in this phase detection, we will first have to convert the colored image into the grayscale image. So it is easier for the classifier to handle the image and detect the faces from it. So for converting the image from converting the colored image to grayscale image, we will write gray image. I have written this gray image equals to cv2 dot cvt color, and in the braces it will have this image that you have to convert it into grayscale. This image, comma, we will write cv2 dot color and underscore bgr to gray gray. Okay, so after converting it into grayscale, now we will detect the faces from the images. So for detecting the faces, I will be writing the face equals to detect. I am calling this object here, and with the function detect multi-scale, and it has 3 parameters. So the first one is in which image you want to detect the face. So we will be writing this gray image here, and the next parameter is the scale factor. So we have to see the value of the scale factor, as the scale factor is that value which decreases the volume of the whole grayscale image by 5% until the face is detected. So it basically what does, it decreases the value of the image so that it can find the face from the image. So I am writing 1.25. The smaller the value is, the greater will be the accuracy. So I am writing 1.25, and the next parameter is the minimum neighbor. So we don't have to bother this value. Now after that, after detecting the face, now we will be describing the rectangle shape for the face. So for that, create a for loop for. Now in this braces, we will be writing all the dimensions for the rectangle like x, y, w, h, length, breadth, height and width. Okay, so after the parameter, now in face, we are actually we have detected the face, but now we have to define that face with a rectangle shape. So for that, we will be using the dot rectangle function. So here I am writing cv2 dot rectangle. Okay, rectangle. Now in this we have 4 parameters. The first one is the image that you have to detect the face image, this image that we have read it here. Okay, the second parameter is the RGB value. RGB value means the colored value. So here I am writing the x, y, and then the other parameters for the rectangle. We are basically defining the parameters of the rectangle, how it will look on the image. So we will be writing x plus w, y plus h. Okay, so after defining the parameters of the rectangle, now we will be look at the color of the rectangle. So here I am just taking the green color. So this is the code for green color. Okay, 0, 0. Okay, so now after that the last parameter is the thickness of the rectangle. So I am giving 2. So now after defining the rectangle, now we will just show the image. So for displaying the image, cv2 dot imshow, in the parenthesis we will be writing detect. Any message you can write like detect images. Okay, and comma, which image? This image. So image. Okay, so after displaying the images, now we will be defining the wait key function. What does wait key does is we will define some intervals between the images. It's just a time period that what will be the intervals between the images. So cv2 dot wait key, and how many? I am taking 200 milliseconds, sorry, 2000 milliseconds, and we will be writing cv2 dot destroy all windows. So destroy all windows will closes all the windows based on the wait for key parameter. So here I am writing the 2000 milliseconds, so it will destroy it for that. So here, okay, so I am running this code. So here you can see that all the faces have been detected.
So now we finally come to scikit-learn. So what is scikit-learn? Scikit-learn is a free open source machine learning library that contains generic implementation of common machine learning algorithms. So as we've already discussed, there are a lot of algorithms that you can use in order to build a machine learning model. But writing those algorithms from scratch on yourself by yourself is going to be really difficult. So using instead of that, what we do is we use scikit-learn. Scikit-learn allows us to allows us to import the algorithms ourselves after understanding the data, and we can just use those algorithms that have already been pre-written for us to implement our model instead of us having to implement the algorithms ourselves. Since they are common algorithms, they have been implemented by people already. Okay, so now the thing that we have to understand is that it contains a lot of functions to perform commonly used operations. So it doesn't just contain the machine learning algorithms that we want to use. It also contains a few functions that we use a lot. So for instance, if we have some data set and we want to split it into a 70-30 ratio, it has a function for that. If you want to figure out if you want to validate our data set against different distributions of data, it has a function for that. If you want to generate a confusion matrix, it has a function for that as well. So there are a lot of things that it covers. It doesn't cover everything, but it has a lot of functionality out of the box that we can use. All right. So with that, I have another question for you guys. Hopefully, if I show it to you on the polls, you'll be able to see it. Okay. So now I think you can see the question. For those of you who are unaware, the question is, can you build a machine learning model by only using scikit-learn and no other library? So if you are not using any other library other than scikit-learn, can you build a machine learning model? When I say no other library, I mean you are not able to use Python as well you are not able to write, you are not using any other thing other than scikit-learn. So for all the tasks involving machine learning and everything, can you use scikit-learn only? So the answer that options that we have is yes and no. So I'll wait for the answers, and once I've gotten all the answers, I will tell you the correct answer. So I encourage everyone who's participating in the all right. Majority of you have answered, and the options that were available were yes and no. I'd like to tell you the correct answer, which is for the question that can you build a machine learning model with only using scikit-learn and no other library. The correct answer is yes, you can. The people who have answered no, I'm assuming that you guys were thinking that because we have to use NumPy or Pandas or other libraries like that, we could probably not be able to use build a model without using those libraries. The thing is, you can build a model without using those libraries, but you would have to do a lot of coding yourself. You would have to import the data, parse it, split it, and then use it inside the library of scikit-learn. But only using scikit-learn, you can build a machine learning model. It's just going to be really difficult, and without using scikit-learn on any library, it's going to be even more difficult. So the correct answer is yes. For those of you who have answered yes, you were correct. For those of you who answered no, you were incorrect. But depending on how your thought process went, you were really close. All right. So now let's move ahead. I've closed the poll, and now let's take a look at why should you use scikit-learn. First of all, it's very easy to use. Scikit-learn is extremely easy to learn and use, and it makes the task of implementing mathematical algorithms really easy because it contains all the implementation with it. We just have to understand how to use the classes and the functions available in the library. It's very well documented. It's got an extensive documentation that contains information about how to use every available feature in the scikit-learn library. And using that, we can take a look at that. Then it's been created by experts. So scikit-learn is a library that has been created by expert data scientists who have been inside the data science business for a long time. They have written these algorithms themselves, and these people have been writing algorithms that are relating to data science from their hand for a long time. So they know how to make a generic implementation that many people can use. And finally, it's very well tested. It's been used by several developers across the world who contribute patches and bug fixes. Scikit-learn is an open source library, so if you want to take a look at the code underneath the hood, you can just go to GitHub, search for scikit-learn or sklearn, and you can get the library code yourself. If you find some problem of want to help scikit-learn grow and add some features to it, you can use GitHub to add some features in the code that the scikit-learn has, and then suggest a revision to the developers and maintainers. Because it's open source, many people have already found a lot of bugs and submitted a lot of bugs, so that means it's battle tested as well, and it has seen a lot of issues already. Now let's take a look at steps in building a classifier. This is an important concept, right? So now let's take a look at steps in building a classifier. So there are 5 steps in building a classifier, but there are several steps in building a classifier. 5 to be exact, but depending on how you're training a model, it could be more and could be less. Usually these are the 5 generic steps that are used. The first thing is we import the libraries. So if you're using sklearn, numpy, pandas, you import it. Many people import it throughout their code, so as soon as they need something, only then they'll import it. I like to import everything at the top of my file so that everyone who's using my application knows, or looking at the code that I've written, knows what are the libraries that my code depends on. So you can firstly import all the libraries needed to train and build the model that you need, and these libraries can perform tasks ranging from numerical manipulations such as numpy and testing the accuracy that we'll be using scikit-learn for. All right, and then what we do is we import the data set. So data set is the data that we will be training our model on. It's important to understand what data set we'll be using and how we'll be using it. So that's how we firstly need to import the data set, or we can, after importing the data set, we view the data set, we load it, we manipulate it so that it's clean and it's in a state that we can use it to train our model and do the following steps. And after that, we can use it in machine learning models. After that, what we do is split the data. So when we get the data set, its X and Y variables are right with each other. So the thing that we are using to make the prediction and the prediction itself are right inside the data. First, we split that, and then we split our data into a training and testing set. Training set is used to train the model, testing set is used to test the model, and using that we understand what is how the model has learned and what is the accuracy that it's giving us. Then comes training the model, which is the task of the scikit-learn library. It creates an algorithm and allows us to feed it data so that it can learn from the data. And after learning from the data, it can do the classification or regression tasks that are needed. Finally, we test the model. We give it the data that we had set aside for testing. After giving it the data, we ask it to make the classifications, and depending on how many were correctly classified, we give it a percentage from 0 to 100. Higher percentage means our model is more accurate, lower percentages mean it's less accurate. What is the max percentage of a model accuracy? The max percentage is 100%, but no model can be expected to have 100% accuracy. If your model, when training or testing, it gives 100% accuracy, it could be that your training set is too small. That is, it either contains only 10, 20, 40 or 100 values, or it could be that your training set is overfitted, which is the variance issue that we have talked about recently. So splitting the data set is basically the task when we get the data and we want to set aside some data that our model can be trained on, and the remaining data is used to test whether or not our model is giving us correct accuracy. So as in supervised learning, we already have the data and the output that it should map to. Once we feed in the data and we take a look at the predicted output and the correct output, the percentage of outputs that match are the ones that are correctly classified, and the ones that are correctly classified are the outputs that lead to higher percentage of accuracy. So someone has asked to explain some example on training the model. Training the model basically means just taking the algorithm from the scikit-learn library, feeding in the data, which is the X and Y variables that we have splitted for training. Then that data, that algorithm learns from the data, and after that we can make predictions using it. We'll take a look at that in the demo. All right, hopefully you can see the question. The question, So the question is, which set is used to validate the performance of the trained model? So once the model has been trained, which set is used to check whether or not our model's accuracy is good? So I'll wait for a few moments and you guys can answer in the poll and submit your answers. Whether it's training set or testing set. Training set is the first option, testing set is the second option. All right, in the meantime, people have asked a few questions. I'd like to answer those. Someone has asked, what is the ratio to split the training and testing set? So for training and testing, you can split the data into, depending on how large your data set is. If it's really large, like you have millions or billions of rows, then you can just take 1% or 10% of your data. If it's a small data set, then 70-30 is a good ratio to split your data on. It's testing set, which is the correct answer. The training set is used to train the model. The testing set is used to figure out whether or not the answer is whether or not the model is performing well, which is why we use it. And let's have our hands-on. We'll have a demo here. So I already have prepared a Jupyter notebook for you guys in which we perform all the 5 steps. So let me just first explain what we're doing. We're using the iris dataset that contains information about flowers. It contains information about the sepal length of a flower, sepal width of the flower, petal length of the flower, and petal width of the flower. Using these 4 features, we're trying to predict the kind of flower that it contains, or kind of the iris flower that it's containing. There are 4 kinds of flowers that our dataset has. 3 kinds of flowers that it has: Virginica, Setosa, and these are the different kinds. So what you do is, firstly, we import all the libraries. As you can see, the libraries were easily imported, so it works fine. And from sklearn, I'm importing the load iris function that will get us the dataset. It's a very common dataset, and so that you can follow along with me and you don't have to wait to load the data from some remote data source, you can just use this code that I'm showing you on my screen right now. And then we are using the train test split function, which we'll use to split our data set into the specified ratio. Someone has asked, can we try it on Google Colab? Yes, you can try it on Google Colab. That's a very good use case for Google Colab, actually. So if you want to use Google Colabs, or if you want to use your local notebooks, you can use those as well. Okay. With that, we have train test split, which is the function that is used to split the data. We'll be using the logistic regression model, which we can import from sklearn.linear model. And finally, we will be taking a look at the accuracy score as well. And scikit-learn already gives us a function that does it for us. I'll be more than happy to answer you on the questions that you ask about the code that you're watching. If you want to follow along, you can type in the code in your Jupyter notebooks if you have it. If you don't have Jupyter notebook, then it's going to be difficult for you. You can use Google Colabs. That's a really good option for you to try if you want to follow along. So now let's take a look at it. So someone has asked that they need to import the data set. Should they need to import it with its name? So we're using the load iris function, and using that you can just import it. You don't need to specify any name. If you have a CSV file on your local system, importing that, you would need pandas library and need to know the file and the example. Okay. So now we load the data set. But now let's take a look at what the shape of the data set is. As you can see, it's a dictionary. Dictionary is a key value pair. It's a common Python data structure. It contains a key of data that contains all the data. And it's 5.1, 3.5, 1.4, 0.2. These are individual rows in our data set. Now, we don't know what these values mean. So taking a look at the data, we have targets as well. Targets ranging from 0, 1, and 2. Now let's take a look at the target name. These are the different types of flowers that we'll be predicting. These are the categories that we'll be predicting: Setosa, versicolor, and virginica. So 0 means Setosa, 1 means versicolor, 2 means virginica. The reason why we have encoded them into numbers is because machine learning algorithms only understand numbers. They don't understand words or strings or letters or sentences. So we need to first convert those numbers into letters in classes into numbers, and then we can make the prediction. And now for our columns, we want to be able to understand what are the different columns that we have. And what we get here is we get the sepal length, sepal width, petal length, and petal width. So it's given us the example of what we have. So feature names are: the first column has sepal length, second column has sepal width, third column has petal length, fourth column has petal width, and all of them are in centimeters. So that helps us understand the data. Now it's time to split the data. We'll split it in X and Y. We'll be using these features and using those we'll be predicting these targets 0, 1 or 2 which map to setosa, vesicular or vaginica. So with that, after splitting the data, I try to split it into 70-30 ratio. So let me just explain what that means. Using the data set that we have, the data, the data key inside it contains all the data that we need. So let me just show you what the size of the data is. If I insert a row below and look at the length of X, we have 150 rows there. Now, if I split it into a 70-30 ratio, right? And now if I insert a row and I print the length of X train, we have 105. So 70% of 150 is 105 and remaining 45 are for testing. So we will use 70% of our data for training, 30% for testing. And with that, we create a logistic regression model. This is a class in sklearn. It just takes in the logistic regression model and creates an object of it. We use the fit method to fit our data. Fit basically means train our data. We pass in the training X variable and training Y variable. So the 105 rows that we have created for testing, we pass it inside our training and testing set. If you're following along, if you want me to scroll up to help you look at the code, this is what the first line, first things we import is. Then we load the data set. You only need to write this code. This is just for explanation. This is markdown format, so you don't need to copy that. After we have trained our data, since our data set is small, it trains in a few milliseconds. Now we make the predictions. And after the predictions are made, we take a look at the accuracy, and accuracy is 88%, which is quite good. Because machine learning models use statistics, these accuracies could change. So if I train it again and then I check it again, it's giving me 100% accuracy because our data set is too small. And now it's giving me 91% accuracy. So it's giving us high accuracy, but the accuracy is variable. The reason why is because depending on how data is split. When we split the data using train test split, it splits it randomly. So it takes a look at 45 values randomly and splits it into another 45 and 105 random values from the entire data set, and then we can train the model. So someone has asked, is face recognition classification or face recognition is a supervised learning problem. It's a classification problem, but it takes a look at very different technologies that are not just part of classification. It takes a look at computer vision, handling the data. There are many other different kinds of things. Face detection is a classification algorithm. Face recognition is a system that uses classification algorithms along with other algorithms as well. Is computer vision in area of ML? Yes, it is. Hyperparameter tuning, as the name sounds, is used to tune the hyperparameters of a model to make it increase its accuracy. So what are hyperparameters? So for instance, let's take the support vector machine model as an example. Now, when you're training a support vector machine, you need to set a lot of parameters. These parameters determine how your machine learning model will get trained, for how long it will get trained, and how it will begin with the training session, and how the training session will go on, and how long it will go on. So these are the kind of things that the hyperparameters are responsible for. To give you a quick look, let's take a look at the sklearn libraries documentation for support vector machine. This is the support vector classifier, also called SVC, and as you can see, there are these many parameters that you need to change. As you can see that these are the default parameters, and you can take a look at all the options that you can take. So for instance, the parameter named C, parameter named kernel, you could say the default is RVF, but you could change it to poly or sigmoid or pre-computed or any other value. As you can see, there's also degree, there's also gamma, and there are a lot of other parameters that you can set. Now these parameters are responsible for you to understand how your model works, and these parameters also take care of how your model will take care of the data interaction and how it will train itself and figure out the classification problem. For instance, if you have a data set and you want to use it to classify your algorithm, to train it on a classification problem, this algorithm, if you don't set any of these parameters, these are the default parameters that will get set automatically. And all you would have to do is train your model and you will get some sort of an accuracy. It might not be the best accuracy you get, but it will be the accuracy you get by the default parameter. So if you're not satisfied with the accuracy that you have with any of the models that you have trained, one thing that you can do is called hyperparameter tuning. That is, you could change the parameters to different values and see how it affects the accuracy of your algorithm or the trained model. So for instance, if you have trained model with the default parameters and you change it and you get a better result in the accuracy score, that means that that model is better than the previous model and you need to pick that model. Now, all of that is good, but since you can see that there are so many parameters that you need to think about, and what's even more difficult to understand is that since there are so many parameters and all these parameters have so many options, which ones do you choose and how do you go about choosing one of those? Now, since machine learning is based on statistics, probability, and calculus, there's no fixed answer. There's no way to determine which one to choose right off the bat. So if you want to learn how to choose one, you need to try a lot of combinations. Now this is where the hyperparameter tuning part comes in. So in hyperparameter tuning, what we do is we take a list of all the possible or all the options for the hyperparameters that we are choosing, and we choose a lot of combinations in those hyperparameters, and then we pick the ones that lead us with the best result. So to give you an example, since in SVC, let's say these are the parameters that we're concerned with: C, kernel, and gamma. As you saw in the documentation, C, kernel, degree, gamma, all of these are parameters that you could set to the different values, and you might get better or worse results depending on how your data set. Now the thing is that there's no fixed answer that you choose these parameters together and you will get the best answer. A lot of it is based on experimentation, so you would have to pick a lot of parameters and do this. So the two options that we have to do this are called random search and grid search. So we have a grid search algorithm and we have a random search algorithm. So what do these mean? Well, let's say that these are the options that we want to test our or tune our hyperparameter on. We want a combination out of these options and we want the one which gives us the best result. So let's say we have a data set and we train our model on default parameters. Now, if you take a look at the documentation, the default parameter for C is 1.0. Here it is, 1.0, which is this. The default parameter for kernel is RBF, which is this one, and the default parameter for gamma is scale. However, the options you could choose a numeric option as well, and this will give you different results. As you can see, it says here if gamma is scale, the default value is supposed to be this. If auto uses 1 by n features, when 1 by n underscore feature, n underscore feature means that we have n underscore feature means the number of features or the number of columns. So if we set it to auto, then it will automatically determine the scale. However, we can pass in the scale as what we want as well. So if we want...
Just a quick info, guys. Test your knowledge of AI by answering this question. In which of the following application does AI has its expansion? A. Planning and scheduling. B. Game playing. C. Robotics. D. All of the above. Comment down your answers in the comment section below. Whoever gets the correct answers will win 5000 points in Intellipaat wallet. Subscribe to Intellipaat to know the winners. Now, let's continue with the session.
If you want a model to be trained to its max accuracy, considering all these parameters, one thing that we can do is we try all the combinations or all the different permutations and combinations of these options. So let's say we start with 1 linear and 0.1. We get the accuracy of, let's say, 68%. Then we go with 1 linear and 0.2, and we get the accuracy of 69%. Then we go with the accuracy of 1, we go with the parameters 1, linear, and 0.3. So C will be set to 1, kernel will be set to linear, gamma will be set to 0.3, and we will again train the model and test the model and figure out its accuracy the normal way we do. Let's say we get the accuracy of 58%, and we try it for all the possible combinations. So we, after getting through all of the gammas, we go from 1 RBF, and we train on all of these. Then we go through with this process again with 10, with 100, 1000, and we try out all the combinations. Now, when we do that, we keep track of the combination that gave us the highest accuracy. So if the highest accuracy we got was 88% with the parameters as one linear and zero point 0.6, then we'll choose that. So this is what grid search algorithm does. Now, as you can see that this could be an exhaustive search. We're trying all the possible combinations and permutations. And the real problem here is that since we're trying all of the permutations and combinations, and if the data set is large, then training it will take a lot of time. And to be fair, hyperparameter tuning does take a lot of time. So if you don't want to spend a lot of time, or you don't have the resources to train such all of the combinations, or to try out all the combinations on the size of the data set that you have, you could try random search. Now, random search, as the name sounds, is that it chooses values at random. So it might choose one linear 0.4, 1000 RBF 0.2, so on and so forth. And it randomly chooses these values and picks the best one that it gets after a number of iterations. Now, this number of iterations is unknown to us because it's implemented in the algorithm. We don't have any control over that, and that's how that works. Now, intuitively, you might think that since it's randomly selecting these things and there could be number of possibilities, we might not get the best answer. And you're right, we might not get the best absolute result when we're choosing random search CV or the random search hyperparameter tuning. But the thing is, even if we don't get the best, we'll get somewhere around the best. So let's say the best attainable score using these hyperparameters was 95%. We would get somewhere around 88 to 93%. Now, this is, by the way, mathematically proven. There's a research paper on this as well. I don't know the link of this, but you can search it online and it will show you that random search CV performs much better on large data sets, mainly because it's not exhaustively trying to find out all possible permutations and combinations and trying to figure out how to get things done. So if you don't have the luxury of having large computational resources, or you don't want to spend a lot of time on training your model, you could choose random search CV, but with the understanding that random search CV might not give you the best, most optimum result that you want, but it'll give you somewhere around that. So that's good enough. Now that's done, we can understand that these two techniques are quite different. One focuses on a lot of time. So grid search will take a lot of time, but will give you a great result or the most optimum result attainable using the hyperparameter grid that you give it. And one is a little pragmatic. It might not search all the possible permutations and combinations, but it will do good enough and give you a good result. So you can try that as well. Now, this mainly depends on the size of your team, the resources that you have, the size of the data set that you have, and a combination of all of that will determine which algorithm you choose. Now, for instance, if you're training your model on a cloud computing platform, let's say the Azure ML Studio, that these studios have other algorithms as well. So I don't remember the name of those algorithms, but they are there as well, and you just have to change some settings and click a few buttons and you'll get good results. Also, they allow you to write code to do that as well, so you could read through the documentation of their SDK and then provide you with that as well. But for normal tasks, if you're doing it on your PC, or even if you're offloading these computations to a cloud computing cluster, these tasks are better performed, and grid search and random search will give you good results. So if you are using a service like the Amazon SageMaker or the Azure, I think ML Studio is called, Machine Learning Studio. So you could use those technologies, and they depending on the data set and the technology you're using, it will give you some graphical tools as well to train or hyperparameter tune your model. So, and again, they give you options to save that model, deploy it, create a web service out of it, all of that using a graphical. So if you want to take advantage of that, you could use cloud computing for that as well. But if you just want to train a model on your local computer, grid search CV and random search CV are great examples for that. So you could use that as well. So as we have seen, grid search CV will try out all popular or all the possible permutations and combinations of all the options that you've given it. Do make sure that it will only try out the permutation and combination of all the options that you have given it. So for instance, for C, it won't try out 1, then 2, then 3, then 4, then 5, to 1000 because we are only allowing it to use a value out of these four for C. And similarly for kernel, it will only try out either linear or RBF. Similarly for gamma, it will only try out 0.1 to 0.9. So that's how it's supposed to work, and that's how it does work. Now that that's done, let's take a look at the code and understand how to get it done. So we'll be using a support vector classifier, and we'll be using a data set that we have. The data set is quite small, as I'll show you, but first let's import pandas. So pandas is used to load data and data sets from our local computers or any other format using CSV, XLS, and so on and so forth. And it's loaded. Now let me load it and read CSV. The name of the file that we'll be using is called dataset.csv or no data.csv. So I type data.csv and the file is loaded. Let's take a look at the file. So I think that's too much information. Let me just take a look at the head of the file. Head will determine the first 5. Okay, so this is the data set. Here's the user ID, here's the gender, here's the age, here's the estimated salary, and here's the purchased. So these are the, you can think of it as the records from a store, and this is a record for a particular product. So let's say it's the record for an iPhone. So these are the user IDs and the information stored about the person's name, person's gender, age, and estimated salary, and we check whether the person has bought this or not bought this. So 0 tells you that okay, the person did not buy the iPhone, and 1 would determine that the person did buy iPhone. So this is what the dataset looks like, and we'll be training a support vector classifier using a SVC, and we'll be using the support vector classifier that is provided inside the sklearn library, and we'll take a look at how to tune it using the grid search and the random search algorithm. So let's start doing that. Let's first import. Okay, I will be using now, by the way, sklearn comes with all of these pre-installed, and if you don't know how to use them, we do provide courses on that as well, so you could take a look at that. But I won't be teaching you how SVC works internally, but I'll show you how to get it done in the Python Jupyter notebooks, and you can understand how to do hyperparameter tuning, since this is the goal of this this session. So let's take a look at that. So we'll go from sklearn.svm import SVC. SVC stands for support vector classifier, and since this is a classification problem, a classification problem mainly means that we're trying to figure out the output in categorical format. So we don't have a continuous format where we are trying to figure out whether we have only 2 labels. Let's say the customer will either buy the product or won't buy the product. So if we have a limited number of outcomes, that's what's known as classification problem. Regression problem basically means that we're trying to predict something, and predictions could have an innumerable number of outcomes. So let's say that I'm trying to figure out the price of a house. That would depend on the house, and you can't keep it in a category that it will be this much. Let's say it's a continuous number. It could be 1,000, 10,000, millions, or possibly billions as well, or 1,000,000, 11,000, something like that. So it works like that as well. So since we are using machine learning, we'll use the train test split function in the sklearn model or the sklearn module. So from sklearn dot model selection, I think it's called. Oh, my sklearn app. So model selection, we import train test split, and we also import the grid search algorithm while we're at, and it gets imported. I usually like to import everything that I wish to use in a particular notebook at the top cell, so the cell which is at the top. Now that that's done, let's take a look at how we're going to do it. So for this classification problem, we'll be taking a look at the age and the estimated salary. We are discounting the gender and the user ID because these, in our opinion, does not have any effect on how the person whether the person buys something or not. So let's split the data into X and Y columns. X is the data that we will have, and Y will be the data that we will try to predict. So we will extract the age and the estimated salary from the data set that we just loaded from the data.csv file. And since we're using pandas, we could use the ilog. Now ilog, for those of you who don't know, ilog stands for integer location. Basically, we pass in an integer list which slices up the data and gives us only the subparts or subrecords of the entire data set that we want. So we want all the rows. However, we only want age and estimated salary. So 0, 1, 2, 3. In pandas, the columns start from the 0th index. So user ID is the 0th index, gender is the first index, age is the second index, estimated salary is the third index. And we want age and estimated salary, so we want 2. And y is the column that we're trying to predict. So we are trying to predict the purchased column. For that, we will be using, again, ilog will be used, but here we only have to pass the, I'll just copy it and I'll show you. I don't have to pass in a list since I'm not choosing multiple columns. All I have to do is press enter, and now the data set is split. Now I have age and estimated salary in one data field, and y would contain whether the customer has purchased or not purchased. As you can see, we have it here as well. So now that that's done, quick sanity check. Let's take a look at the size of the data set that we have. So data dot. So you can take a look at all the columns that we have. What are the data types of each of the columns? And finally, we have 400 entries. So the index ranges from 0 to 399. As I've already told you that in pandas, the indexes start from 0. So this is what it looks like. Let's change it back to head so we have an idea of what our data set looks like. I misspelled it.
If you want to make a career in data science, then Intellipaat has IIT Madras Advanced Data Science and AI Certification Program. This course is of very high quality and cost effective, as it is taught by IIT professors and industry experts.
So this is what it looks like, and let's remove that. So now that that's done, the first part we'll do is we'll train a support vector classification model. To do that, we will just train, test, split our algorithm. And since we've already split the data set into X and Y columns, we'll be taking a look at that. So let's name our functions X train test, Y train, and we will use the train test split method to do that, and we will use the train test split method. So for train test split, all we have to do is use the X and Y methods. So we pass in the X and Y columns, and then finally all we have to do is specify the we have to specify what the name of the train test size. So if the testing size is 0.25, let's say test So now the dataset is split. Let's take a look at the size of the dataset that we have. Strain shape. So we have 300 records in the X strain, and for X test we have 100. So as you can see, we have split the dataset into 25 and 25 and 100% of the dataset. So now let's take a look. So let's take a look at that. Now that that's done, we have split the dataset, and now all we have to do is train our model. We'll be using the SVC algorithm, as I've already discussed. So for that, all I have to do is use the SVC, and I will use the default methods. So it's done, and all I have to do now is fit the dataset. So to fit it, all I have to do is pass in the training parameters. So we are training it, the X value, the Y value, and these are, as I've already told you, the default parameters. Check it with the documentation. All of this is completely as it was supposed to be inside the documentation. Now that that's done, let's take a look at how our model is performing. we will make a prediction with dot predict, and we will use the x test. So the predictions are made. Now we have to take a look at whether those predictions are right or not. Now these predictions can be taken using the or the accuracy could be checked using the sklearn package. We'll use sklearn dot metrics, and we will import accuracy score. If you're not worked with accuracy score before, so now we're taking a look at the accuracy score. We have the white the training. Okay. Okay. White train, it's white test, and it's done. So right now, as you can see, the accuracy is only 0.58%, and it's very, very bad. So now let's take a look at how we can use the grid search algorithm and get better score. So we have already imported the grid search algorithm, so it won't take a lot of time for us to get started with it. All we have to do is first create a grid of all the possible values and all the possible parameters that we want to tune it to. So we will create a grid using a dictionary in Python. So I will call it a grid. I will create a dictionary, as you can see, and inside that dictionary I will create some so key would be the name of the parameter, and the values would be an array of list of all the possible values that we want it to work on. So for C, I want it to work on, I think, from 1, 10, 100 and 1000. So let's do that. So 1, 10, 100, 1000. Similarly, there are other parameters that I want it to be trained on as well. One of those parameters is the kernel. And you can take a, if you want to figure out how these parameters are being chosen, you can take a look at the documentation and it will tell you what are all the parameters that you could use. So we use kernel. Inside the kernel, I would use RBF. RBF is used by default used in the SVC, and I will use something called linear, LINEAR. So we are using RBF as well as the linear kernels. And now finally I will use gamma, GAMMA. And for that the list would go from 0.1 to 0.9. So I will, so let's take, if I'm not make any mistakes, it works, and yeah, it works. So now all I have to do is create a new instance of the grid search CV class that I imported above, passing a new support vector classifier that has not been trained on anything, and the grid search will take a look at the rest of it. So to do that, all I have to do is firstly create grid search CV. Grid search CV. Inside this, I will take a look. I will pass in the parameters. Now the first parameter would be the classifier that I want to use, or an instance of the classifier. I can't use CLF mainly because it's already been trained and it won't be trained again. So to do, I have to pass in a fresh classifier. Now I have done that. Now what I have to pass in is the grid that I created, and it's called, I believe, param grid, and I've called it grid, so I am passing it in. Next, I want to pass in the scoring method. So what is it that I want to score it on? So scoring would be, I want to score it using the accuracy. So there are different parameters for, let's say that you are using it to train a, not a classifier, but a regressor. So regressors usually use something called R2 score, or the R squared score, in which we are trying to reduce the error. So it's not concerned with the accuracy, but the error produced by the regressor. So we can choose that. And now that that's done, let's take a look at it. And it's created. Now it's created, but we have to fit it. Fit it basically means that the algorithm will be run on the data that we pass in. So grid search CV dot, and we pass in the same data that we pass to train our model, and we pass in the training data, and it will take some time, guys, because as I've already told you that there is a lot of options that, or a lot of combinations that it could take. So it will build up all of this and it will take some time. So let's wait for it to finish. So as you can see, it's taking a lot of time. Just wait for a few minutes. We'll see if it works. Most probably it will. If it doesn't, then we'll have to tweak some parameters as well. This is the problem with grid search, that it takes a lot of time, so you do have to wait for quite some while. Okay guys, so it is taking a lot of time. So what I'll do is I'll interrupt the kernel and I'll restart it. And since it's taking a lot of time, what I'll do is I will rescale the data and make some changes. And this will show you how this works. So let's take a look at that. Rescaling the data will make our data a little smaller, or the magnitude of our data a little smaller, and it will allow us to work perfectly with the configuration that we have. So it won't take a lot of time. So let's see how that works. So I will rescale the data. Hang on a bit. And if you ever come across a problem like this, you can rescore. You could use other functionalities as well. I'll be using the sklearn pre-processing standard scaler. You could use other methods as well. So sklearn dot pre-processing. Yeah. Import. Rerun it. Works. Rerun it again. This is done. I will remove it since it's taking a lot of time, and I will rerun it again because I've closed the kernel. So run again. Now, as you've already seen, I will firstly insert a new cell below, and I will try to rescale the data. And for that, we will use the same standard scaler that we have used right now. All I have to do is create a new method. Scalar is equals to standard scalar. This is the instance of the scalar that we'll be using, and we will be scaling the xtrain and the xtest variables. So xtrain is equals to, we will be using the scalar to fit and transform. Now it's going to take some time. So hang on a second. I think it's doing this because we have not run it here. So I'll just type it in and we will fit it. Let me create a new variable, scaled. And here I won't be using the fit and transform. I will just use the fit. Now the difference between fit, transform, and fit is there are a lot of internal variables that need to be set for the scalar to fit the data, because it depends on the mean and the standard deviation of the data. So it takes the xtrain method, xtrain variables, or the variables inside the xtrain data frame. It will fit itself, and it will and then transform the data based on the variables that it set on the xtrain data set. So I would be using x test here, and now that it's done, let me just use the xtrain scaled and the ytrain. Oh, I don't have to use the scaled versions because it does matter. And it's done. And here x test scale and y test and y spread, and we get a score of 93%. So as you can see, scaling increases the algorithm's performance massively. But now let's take a look at how to get it done with the grid search algorithm. 93% is actually a pretty good score. So if you might not have to do this on the SVC algorithm, but let's say that you do. Let's say that you have an algorithm that's performing very low. It's giving you a score of, let's say, 60%. You could use the same performance tricks that I've used right now, and you could get a better result. But just make sure that when you are, after you have trained the data on a scaled data set, the next time when you make predictions, you have to scale that data as well. So just make sure that you're doing that. And now that that's done, we have the parameter, and let's just change some few parameters so that it uses our maximum CPU capabilities. Now sklearn provides us with some of the functionalities that allows us to use the maximum CPU capabilities. If you want to take a look at that, just type shift space in any method. Inside any method, we will be using the CV and the njobs method. So what do they do? If you want to take a look at what any of these do, they have the doc string with them. Just take a look at CV. It means cross validation generator. So it will create 10 buckets of the data to create the validation data. So we could use that. We don't have to use it if you don't want to. The main one that I am interested in the end is the end jobs one. The end jobs method, end jobs would allow us to use the all the processing power that our computer has to offer. So if it's a multi-core processor, we will use all the cores. So for that, let's try n underscore jobs, set it to -1, so it will use all the processing power that's available on our PC. If you know how many cores that you have, or if you don't want to use all the cores, just the cores that you have, like you have 4 cores and all, you only want to use 3 or 2 of them, then you can use n jobs equals to and set it to the number of cores that you have. So now that that's done, let's just try it out. Grid search CV dot, and as we've already used before, we will be using the fit method. Let me just use fit method. I will pass in the scaled data, TRAIN. Training data is passed, and believe I have to pass in bytrain. And now it's run off again, and let's see if it works. And as you can see, it works in a couple of milliseconds actually. So you can see scaling of data actually increases the or decreases the computational complexity. So now that the data set is scaled and we have used all the possible combinations, let's take a look at the score that we are getting. Oh, I'm sorry, it's not a grid search. And we're getting 90.33. So it's actually a pretty good score. The reason why we're getting different scores is because the number of times there's a lot of randomness involved in our data set. So if you train it multiple times, you get different accuracies. But as you can see, we're getting a score around 90%. Now, if you want to take a look at what the parameters that they use, you could use the best params method. So not the method, but the property.
Just a quick info, guys. Test your knowledge of AI by answering this question. What is artificial intelligence? A. Putting your intelligence into computer. B. Programming with your own intelligence. C. Making a machine intelligent. D. Putting more memory into computer. Comment down your answers in the comment section below. Whoever gets the correct answers will win 5000 points in Intellipaat wallet. Subscribe to Intellipaat to know the winners. Now, let's continue with the session.
So C was 10, gamma was 0.5, and kernel was RBF. So we're getting quite close to what we already had. And the C was 1, kernel was RBF. And yeah, so these are the methods that we used, and we're getting a score of 90.3%, which is quite good. Now let's take a look at what happens when we use the random search CV. So if you want to use the random search algorithm, firstly you will have to import it, and importing it is not that difficult. It's in the same package that we already have. Import grid search from, you just have to type in random search CV, run it again. Now using random search CV and grid search CV are quite similar because we'll be using the same almost the same things. So we have the same parameters that we'll be using. We'll be using the support vector classifier as well, and we'll be using the scaled data. So it would be quite similar. So in order to not make mistakes, I'll just copy it, paste it. I'll type in RDM or search CV. Now that that algorithm is done, let me take a look. Randomized search. That's what I was wondering. So let's name it randomized search. Again, I'll be passing in a fresh instance of SVC. The parameter grid is the param grid. This is the grid that we created earlier with all the possible parameters that we'll be setting. And inside this one, we need to change it from param grid to param distribution. So because these are different methods and we won't be using a grid, we have to change it to param distribution, and we'll be passing in the grid that we created earlier. It will take a look at this and choose randomized random parameters and figure out the best one that you have to use. Now that that's done, we probably could get away with not passing in accuracy, so it will use accuracy by default. And this is done. Now let's random search CV and we fit it. We use the scaled data and we pass in, and as you can see, it ran actually quite faster than the grid search example that we had. And now that grid search is done, we will be using the same attributes, and we'll be checking how much it improved our performance. So we'll be taking a look at random search best score and best params. So let's take a look at that. So random search CV, best score. And as I said, that it will take somewhere around the best score even without trying all the possible combinations. The best score we got was around 90%, and we got around 89.66%. So as you can see, that works. Random search CV, and we take a look at the best and RBF and gamma and C. So just the gamma parameter was set a little differently, otherwise it shows RBF and C exactly the same as the grid search parameter. And there's not a lot of difference between the gamma that's chosen by the random search and the gamma that was chosen by the grid search. So as you can see, both of them are giving us the right answers, and we are getting the right answers, and we are getting an accuracy of around 90%. So in conclusion, you should use the scale the data to get better answers. Just make sure that when you scale the data, you understand that you are scaling it, and the data that you get from any other source for prediction in the future, you would have to scale the data again. So if you use unscaled data in your production environment, then that would give you incorrect results. So even with 90% accuracy, you will be giving it the wrong data and you'll be getting the wrong answers. So with that in mind, we had how much? 93% of accuracy. Now, I'm sure you're wondering, why did we get 90% here and 93 there? So let's again just run it again. I'm running all the parameters again. Earlier we got 93% of accuracy. Now let's take a look at this. We got 92. Let's run it again. So I create a new support vector classifier, fit it again, split the data, train it, make predictions, and 92%. So we get around 90% of the accuracy. You can see again we get 93%. So there's a lot of randomness that's involved here, and when you get some accuracy score from the data set, it's not going to be set in stone. It's going to take some time, and when it does, it'll give you different results. So when you run the random search algorithm again, or the grid search algorithm again, you'll get different results. Let's take a look at that. So as you can see, now you're getting 91% of score, and the estimators are these. So if you wish to use the random search or grid search algorithm, do know that there's a lot of randomness involved, and as you can see, kernel, RBF, and gamma 0.2, and we are getting a good result. So the accuracy that you'll be getting is going to be around 90%. Scale your data, pre-process it, make sure it's easy to digest by the computer, and make sure that you are using the correct tool for the correct job. If you have a lot of data, don't use grid search because it's going to take a lot of time, even with the scale data. And if you have you use the randomized search, you could probably get away with it using smaller data sets. For larger data sets, random search is quite good. You could get around the same accuracy score, and you would get it much faster.
So let's start this KubeFlow video by taking a quick look at some facts that you might or might not know. See, for example, did you know that Kubernetes has a huge community presence online just because it's open source, it's extremely powerful to use, and it's pretty easy to go about working with it as well, right? So one, it's open source. Two, it has a very, very, very supportive and a huge community to go with that as well. And then, when you think about the Kubernetes logo, right, it is always the ship, it's the anchor, and it consists of 7 spokes. Well, there is a meaning for that, and the 7 spokes in the logo actually refer to the project's original name. Before it was called Kubernetes, it was called as the Project 7 of 9, and that's how it's got the 7 spokes in the logo. And then when we think about anything open source, right, there's a lot of companies that come into collaboration to see if they can pitch out and come with a common solution. And here in this case, that was the same too, because Red Hat actually worked with Google to go on to develop Kubernetes even before it was actually officially announced or launched as well. So in that particular case, KubeFlow or Kubernetes in general being open source adds a lot of value to the community and of course to the people who are willing to use the technology as well. Now, coming to the introduction to KubeFlow. Well, what is KubeFlow, right? See, when you think about it, you have tools such as Adobe Photoshop for photographers out there, people who want to edit photos and all that. And then when we're talking about architecture and civil engineers, these guys have the AutoCAD tool, right? Now, what do machine learning engineers have when we're talking about using a machine learning pipeline which is hosted in a clustered architecture? Well, that tool itself, the entire platform is KubeFlow. So when we talk about what KubeFlow exactly is, you have to understand that it is one of these very, very popular open source platforms right now that will help us make use of setting up machine learning pipelines where we can run very complicated, very complex programs and have it run on Kubernetes clusters very easily as well. So by doing this, we can make use of the computation power, the resources, and a lot of other things, a lot of dependencies from multiple machines in a cluster at a time, and this can exponentially speed up a lot of complex things. And of course, whenever you talk about artificial intelligence, machine learning, or deep learning, you already know that it takes a lot of memory, it takes a lot of processing power, and it's going to take more than this, it's going to take a lot of time to go on to provide a solution. Right now, think about, you're on a website, you have a chatbot that you're talking with, right? Or it's your favorite food delivery service and there's a chatbot on the other side and you're very hungry, you're asking where the order is and all of that, right? So in that case, if you send a message across to the chatbot and if the chatbot takes 3 or 4 minutes to just put out one single reply with a basic reply, it doesn't make sense. So you need that kind of a speed. And it's not just you asking where your food order is, there's probably thousands of people who are doing that at that very second as well, right? So it has to cater to all of these people at once. Now when you consider of a situation like that, when you're thinking about the practical usability and the possibility of how overloaded a machine learning model's implementation can get, in that particular case, I believe KubeFlow is definitely something that helps a lot, especially we're talking about Kubernetes, right? So Kubernetes is one of those tools that is extremely easy to work with. It's very, very powerful, right? So do not be carried away by the fact that it's easy to use, just that it is extremely powerful and it can achieve a lot of things with you doing a lot less. Now, why do I say this, right? See, what is Kubernetes first of all? Kubernetes is one of these tools where we can, create applications, deploy them, and operate them in a microservice architecture, right? So, but then how do we go on to do this? Like, we know what it is, but how do we go on to do this? So, what we try to do is we have a couple of hosts where we make use of the computation power of the hosts, but here we create an abstraction layer on the top, so we are in continuous touch and control with all of these hosts that we have, and you can work with it. You can deploy your applications very, very easily without you having to do many things, as I just mentioned, right? So when you think about Kubernetes, it's going to give you an ocean worth of control when it comes to deploying your applications and when it comes to continuous delivery as well. So in that particular case, it can get a little complex for beginners to get started with Kubernetes, but then worry not. With a good certification program, with good training, you guys can become experts in DevOps and of course in Kubernetes as well. So after understanding what Kubernetes is, how it works, and of course why we have to prefer Kubernetes, you really have to check out how KubeFlow came into the picture, right? See, so we're talking about machine learning and its orchestration on the Kubernetes platform, but then who are the people who brought this into existence? Well, to answer that question, you have really 4 big names you have to talk about. One is Google, of course. Google is the key player in Kubernetes and everything that has to do with it. We have Cisco, we have people of IBM, and of course we have the experts at Red Hat as well. So these 4 guys, it's not just 4 people from this company, it's probably hundreds of people from each of these companies. They came together, they realized that they want to make use of the power of operations to make sure the machine learning pipeline is simplified, right? A developer should really not break his or her head about deploying the application. Their job is to make sure they solve the problem using code and they write it and they're done. Now, to go on and take it into a production environment, you need the operating side, right? This is why we require DevOps. DevOps actually bridges the gap in between development and operations. So the people at development can worry about development. The people at operations can worry about, actually going on and taking all of these code and scaling it to production pipeline. And of course, you have DevOps engineers and developers and architects who have the capability to bridge these gap in between as well. So with this, you might have a question that states, how will KubeFlow help in today's world, right? See, whenever we talk about KubeFlow, the main thing you have to talk about is its performance, is its ability to work with machine learning pipeline, to host it, and of course to give you that kind of a power of making use of machine learning and orchestrating it very easily at the end of the day. So what KubeFlow actually does is it'll help you build machine learning models. You're going to get all the tools, the frameworks and everything as we're going to check out in the components in the next couple of slides. So you're gonna have everything foundational enough where you can get started working with the top machine learning frameworks out there, and you can in fact start working with machine learning and get it across ready to production as well. So you can do all of that just with the help of KubeFlow. And then it's not always about just building your model, right? See, building your model is one thing, but the second thing is to see how well the model actually performs. Now, to do all of that, you're going to require certain tools, you're going to require certain skills, and of course, you're going to have a platform that will support model testing too, right? So with KubeFlow, yes, you get features where you can help yourself and of course help the product development team in a way where you can actually analyze the model performance in depth to see where the model where the machine learning model is going wrong, what it's doing right, why it is doing the things it's in the way it's doing, and a lot of these things. So the primary aspects of using KubeFlow is to build machine learning models and of course to analyze to see whatever you have built is either working fine or not. And then talking in terms of in the depth of machine learning, there's so many things that are involved, right? See, with KubeFlow you can actually tune out hyperparameters, you can fine tune the model, you can make sure your model is extremely accurate and that it achieves the solution in the best way possible. In terms of time, in terms of efficiency, in terms of computing power, all of these come at a price whenever you're in a production environment, right? So you have to count for all of these. And if there is one problem, right, you can probably have 3 or 4 ways a machine learning model can solve that problem. Now it is your job to make use of the analysis and to make sure you find the top way to go on to actually solve the problem using that. That's where tuning comes into the picture, and with KubeFlow you can do just that. And then when we talk about version controlling, right, see, in a production environment especially, right, in an official environment where you're working with a team, where you're working on building a product, it's not like you wrote a piece of code and that was the end of it until you close out sales or close down your company, right? So you will have version 1, version 1.1, 1.2, version 2, version 3, version 4. So you're going to have a lot of versions that will be coming out, and it's not just literally these versions being pushed out to production. It's just that you will probably have 100 people behind you who's working on the same piece of code. They're trying to achieve something, a part of the code that you might be working on, a part of the entire project that you might be working on, and everyone is trying to achieve their own subtasks to achieve the goal. Now, to keep a track of all of the changes that gets made in the code, to keep a track of who did what and what changes it had on the production pipeline, be the development pipeline or the production pipeline, and to track all of this actively, to roll back if there's any mistake, to update it to the latest versions, whatever it is, right? Version controlling is important, and KubeFlow is going to help you guys in a way where the use of version control is actually very foundational to the use of the tool itself. And then, as I told you, right, the next set of points we really have to talk about is your ability to control the computing power that you require for your model. Now, sometimes there is a very good chance that you might be running a very simple classifier, right? It can be a binary classifier, or it can be a very simple linear regression model, or whatever it is that might not require a lot of compute power. In that case, if you have and in that case, if you have a cluster which really does not have the latest or the fastest machines, well, yes, definitely you can get away with that. But what if you have extremely powerful machines and you're still using very simple programs out there, right? Of course, it doesn't hurt, but at the end of the day, if you have the ability to dial down the computing power or dial it up and throttle it out as and when you require, depending on the complexity of the machine learning model, well, that's going to save you a lot of time, money, and effort because there will be no bottlenecks that get created in case if the demand is more than the supply, right? For that particular case, KubeFlow is definitely helpful in controlling computing power. And then the next important thing we have to talk about is how we can take model prototypes into production. See, whenever you go on to develop and design a machine learning model, and if you guys are from a machine learning background, I'm sure you guys will relate to what I'm saying now. You will write a piece of code that will achieve almost, let's say, 80% of the task that needs to be done, and you call it a prototype. And now this prototype can go through multiple stages of being redone, being polished, and everything else to take it and make it production ready, right? So you have a piece of code that works, but then at the end goal we want a product that works. So to take this piece of code into production and to make sure it's being implemented actively, be it on a website, be it a chatbot, or wherever it's required, right? So to do that, to bridge the gap between taking it from prototyping to production, KubeFlow definitely helps here too. So the next thing that you guys might be curious about at this point of time in this KubeFlow tutorial is the name itself, right? See, KubeFlow comes from Kubernetes itself, but then what are we talking about? What is the connection to Kubernetes out here? And of course, whenever we're talking about KubeFlow, right, Kubernetes is the basic foundation on which it works. So you really have to know Kubernetes to work with KubeFlow. You really do not have to know Kubernetes in complete depth to be a machine learning programming person who's using Kubernetes. But at the end of the day, it'll always pay well if you are a KubeFlow developer that you know Kubernetes and machine learning well. Now, coming to the actual talk about how the name came about, what does the name mean, right? Let's consider two things here. On the left side, we have cube. On the right side, we have flow. Now, what we're trying to signify with the name cube here is that it runs these machine learning models run on Kubernetes clusters, right? It's this orchestration platform that we make use of. We have multiple clusters, we have multiple devices in each cluster that we can use to run our machine learning programs on. In that particular case, we're using Kubernetes, hence the name cube. So what we're trying to do here is we're trying to train multiple machine learning models across a lot of computers, as I told you, to leverage their speed, leverage their compute power, leverage their resources, and a lot more. Now, why would you want to do this? It's pretty simple, and I'm sure you already know the answer to it right now, because we want to exponentially speed up the execution. Now, if you have one computer that can run a machine learning model and it's going to take maybe 5 hours to train, but now you have a very powerful Kubernetes cluster that can do very similar tasks probably in 1 hour, which would you pick? 1 hour or 5 hours? Well, 1 hour, right? Similarly, now this 4 hours that you saved probably for your pet project it's simple, it's okay. But then if you save 4 hours in a production environment, you're saving a ton loads of time in a way where it'll either make or break your business in many of these cases. So it's very, very important to speed up execution and keep it as fast as possible. So now coming to talk about the flow part of it. See, with the flow part, what we're trying to understand here is whenever we say flow, it's basically a short for workflow, because we're trying to signal how the model should work, its training life cycle, testing life cycle, and all of that from its start, right? So from the ingestion of data all the way till we have results and we verify that the results work correct. This workflow scheduling is very important, and the flow part of KubeFlow talks about that. As I just mentioned, it helps in the complete machine learning lifecycle completion and working. And of course, what this does is, at the end of the day, the developer only has to sit and work on the machine learning code and not break his or her head about how they have to scale it into production and all of that. So this means it's effective and efficient development that's going to save a lot of time and of course a lot of money for the organization as well. So to do all of this, right, so what are some of the components of KubeFlow that will help us do all this? There are many components in KubeFlow depending on your level of expertise, depending on your level of requirement. But then the four most common things that you will use in KubeFlow is pretty simple. You have the central dashboard, you have metadata, you have Jupyter notebooks, and you have the machine learning frameworks that you will actually use to train the model. So let's check out each of these for a second. Now, whenever you talk about a central dashboard, well, this is how a KubeFlow dashboard will look like. However, there's a very old screenshot from the build version 0.7. We're going to talk about the latest version in a couple of slides as well. But then as you can see, right, so you have a lot of notebooks here. You have a couple of documentation things that will help you get started with it. You have a lot of shortcuts where you can create a new notebook server. You can view the pipeline. You can see what's running. You can check out the activities. You can do a lot of things at the click of a mouse button. So having this kind kind of a user interface and a very easy and a nice to use user experience, right? This is what drives the success of KubeFlow in my opinion, because at the end of the day, if you have to look at code all the time to think about operations, leave development. Of course, for development you're going to need code. Now for operations, if you have to keep doing this, it's a major headache, right? So that headache is completely solved by making use of a very elegant, very concise, very pithy dashboard, in the case of KubeFlow with this. And the second thing is, whenever you're working with machine learning, there's going to be a lot of data that gets generated even before you run the model, and of course a lot of data that gets generated into information after you've run the model. So there is data that actually is used to help understand what the all the components mean and all the data mean, and that data is metadata. Metadata basically describes data. Now in a machine learning scenario, you will have a lot of lot of data, such as how many executions were conducted, what was the epoch times in each of these runs, how many training sessions you had, and there's a lot of things whenever we just talk about execution as well. So considering the data just that gets generated out of execution is large, and then of course you'll have the model data, you'll have input output components, where of course if you have a model, it means it has a data set. You have to describe the data set. The data set has to be understood by the machine learning model. So all of these individual files that we talk about will have sub dependencies among them, right? There are many files that's required to run a machine learning model. There's many objects that you'll have to consider in terms of input output components. You have data sets, you have the actual model training files, post training files, and there's so many files that you have to talk about. In the case of KubeFlow, right, so this is one important component that KubeFlow provides, where you can simply analyze all of this, manage all of this, and of course at the end of the day use it to see what your model is doing as well. So you have something to describe what your model is doing, and that is metadata. And the third thing that we'll have to talk about is the Jupyter notebooks. See, whenever you're writing a program in Python or in a notebook online, it's a good chance it's a Jupyter notebook, right? Now, in the case of Kubernetes, where you're running a Jupyter notebook across a server, where the server is orchestrated across a Kubernetes cluster, you're gonna need one common place. You're gonna need one notebook where you can work with all your data, right? And of course, with KubeFlow, you can make use of your regular Jupyter notebook, and I'm sure all the developers that we have out here have been comfortable with using Jupyter notebook. It's very simple to use, and it's one of the preferred ways of how a lot of us developers write code as well. So in that case, this actually helps in a way where you can completely concentrate on using Jupyter notebooks for writing code. And the next important component we'll have to talk about is the machine learning frameworks that we can use. See, there are four main machine learning frameworks that that act as a serving that we can kind of use to deploy all of our models through and work with it as well. You have the MXNet, you have PyTorch, you have Chainer, you have TensorFlow serving, and you have a lot of other machine learning frameworks that are supported by KubeFlow too. So this mostly is what you would require to go on to solve a problem with machine learning. And down the line, of course, whenever you're talking about machine learning, it's an ever growing field, so you can definitely expect to have more of frameworks come into the picture with KubeFlow, and with thousands of people actively contributing to the world of open source, it should come as no surprise to you that there'll be complete support of making use of all of these in the Kubernetes architecture as well. So that is something really important, and that you really should know about. So now, on the next section, we can actually talk about how machine learning works with KubeFlow. See, machine learning is done by whom, right? Who is the person who's responsible for achieving machine learning? Either data scientists, or they are either machine learning engineers, right? So these guys have the complete power to make use of powerful computers around them, and to use these computers to the best of their efficiency, to make sure that that the computer is working in an optimum way, where it's providing the maximum performance possible. Now, if you're thinking about the same scenario in a cloud computing environment or on a Kubernetes environment, that's going to take some time and skill, right? So this is actually what happens when people go on to implement KubeFlow in their existing machine learning chain. You have data scientists that will create the machine learning models for you, or of course machine learning engineers as well. And once the models are actually created, right, there is an ops team that sits in the picture, where they're going to take all the machine learning models that get created by data scientists and machine learning engineers, and then they take it into production, as we discussed before. Prototype to production. On the left you have prototype, and of course you're going to get the final production code on the left side itself. But then to take it to production, to bridge the gap that exists between development and operations, we have people to do that, and these guys are experts, and they're called as ML ops experts, because machine learning operations is what ML ops stands for. And this is very much required in a production environment too. And to check out the next set, on this tutorial, you might be wondering about what is so complex about machine learning that, even with KubeFlow, sometimes people find it difficult to use. See, there's three main things, right? See, when we talk about machine learning, first of all, you guys learning machine learning and providing a solution for a problem that's out there is going to take a bit of time. So it's not just time that it's going to take; it's going to take equal amounts of effort, because hey, let's face it honestly here. You're using a machine and you're trying to ask the machine to replicate human intelligence. Human intelligence, in a way, is probably the most intelligent thing right now. But so if you're asking a machine to do it, so even though the machine has extremely powerful computation power, probably quicker than humans, it has a lot of things that, but it doesn't have a lot of things that we do, right? That's what makes machine learning complex to achieve in the first place itself. So it's going to take a good amount of time, it's going to take a good amount of effort, and of course, at the end of the day, the result that you will see is worth the time and the effort that you put into machine learning, is what I wanted to convey. Now, when you're talking about the complexity of what goes on in a machine learning pipeline, right? See, the first step involves data collection. This is probably the place where it's going to take most amount of time, because you need a data set, you need to pre-process the data set, you need to clean the data set, and you need to find out the problem, you need to find out the data set that solves the problem. So collecting data is one of the most important steps when we talk about machine learning. And then of course we have feature extraction. Feature extraction is when you'll keep whatever is required and throw away what's not. This feature extraction, is a place where you filter out things and you understand what's required for your model and what's not required. This is a very important step as well. And of course, I just put it on in a very simple way, but actually implementing it will take some effort. And then we have model configuration. Model configuration is where you have to understand what type of machine learning should you use to solve the problem. Once you understand that, you must have a model which will make use of the types of algorithms that you think is right for the solution. Be it supervised algorithm, unsupervised, it can be reinforced. It can be reinforcement learning and a lot more as well, right? So you need to find what model to pick, and you need to configure it to at least have the bare bones of it working. And once you understand what you need, all the tools that you have, all the data that you have, and you're ready to actually put it all into code, well, yes, here is where you will require a machine learning engineer or a data scientist to put all of these into effect by converting and typing out the code in multiple programming languages, be it R, be it Python, be it Java, or any other language that supports machine learning as well. And after that, you have something called as workflow monitoring. With workflow monitoring and process management is a way where we're talking about the operations side of machine learning.
If you want to make a career in data science, then Intellipaat has IIT Madras Advanced Data Science and AI Certification Program. This course is of very high quality and cost effective, as it is taught by IIT professors and industry experts.
Once the code is written, once the model is working, once it's verified that yes, this is a solution to the problem, you will have to keep on monitoring it to see how it moves around through the life cycle of the problem. Can it be made better? Version control, how many people are working on the project? Is the project actually complete? Have you met all the all the requirements from the client, and a lot of other things, right? So to monitor all of this easily, the operations part of it handle all of these too. And then process management, right? See, it's not just that you're done as soon as you write the machine learning code. It's all about getting this code ready as a product or an application to the people who are willing to use it, or the people who have paid you to build it. Now, this is another very important thing that follows workflow monitoring, because there's a lot of things in each of these steps, right? See, for data collection, I can probably tell you 10 steps, and for feature extraction, another 10 more steps. So we can talk about 100 steps before we come to the process of workflow monitoring. Now, to break, manage, and make effective use and keep a track of all of these 100 steps, you're going to require a person who's going to sit and manage the life cycle of a machine learning model, right? That is where process management always takes center stage. And then coming to the talk about how KubeFlow came to the picture, even though KubeFlow has been in testing for a while now, there's a lot of beta tests available. The official version 1.0 of KubeFlow actually launched in March of 2020, right? So it wasn't very long ago, but then now there is complete support for KubeFlow. And a lot of people, a lot of companies, in fact, thousands of companies have realized the power of KubeFlow, and everyone wants to use and jump on it to see how best they can use it. One, because it really doesn't cost any money because of its open source nature, and two, if it's open source, it means that there is just thousands and thousands of enthusiasts, people, developers, and a lot of other people with interest who will be developing the product as well. Now, if I was a person who was contributing to the open source community for KubeFlow, let's say I use KubeFlow, I find that something is wrong or something can be made better. What do? I basically, fix something or suggest changes, or actually go on to roll out the changes and tell people saying, hey, this is how I've done better. Now, do that 1,000 times over with 1,000 different people. You have a product which will be polished very nicely with, I'm just giving you a random number here saying 1,000, but there'll be, of course, a lot of other number of contributors out there as well, right? So each of these guys bring about their best to develop the software, and in an open source nature, that will help a lot. And one thing is that the entire KubeFlow project that's happening right now, right, be it from its launch to every single day, the progress these guys make in the community, it can all be tracked on the official KubeFlow GitHub as well. So if you head on to that GitHub, you can check out, right from the inception to where they are now. And I think that in your journey of learning KubeFlow, you really have to understand where these guys came from, what the product was when it officially came out, where it is now, and of course where it is headed as well. So when you're talking about making use of KubeFlow, right? See, KubeFlow is one of these platforms that you can use across a wide variety of cloud computing platforms that are out there. Be it Amazon Web Services, be it GCP or the Google Cloud Platform, be it Azure, be it the Red Hat OpenShift, be it IBM Cloud, and many other clouds as well. So if you are a person who's using any one of these cloud platforms, or if your company is using it, or if you plan to doing it, understand that you can actually go on to implement KubeFlow without you having to put much effort as well. So in that particular case, if we were to show you saying, hey, this is how it works on Azure, or this is how it works on the IBM Cloud, and if you're a person who's using Amazon Web Services, it really won't make sense to you, right? I mean, of course, at the end of the day, you will find out the basics of it, but to understand it in depth, you really have to first find out what cloud platform you want to use. And after that, once you know what cloud platform you want to use, understand that KubeFlow supports everything. So with that in mind, you just start to see the official documentations to see how you can get started with KubeFlow for that particular cloud platform, and then begin working on it as well. And then the second biggest advantage we have to talk about is the TensorBoard support, right? See, we already spoke about how you guys can use TensorFlow and how well you can implement it using the Jupyter Notebook in the cloud computing platforms too. With TensorFlow comes one of these beautiful visualization tools called as TensorBoard, and TensorBoard is completely integrated into use whenever you guys are going to use KubeFlow with all the single features that it brings. So with this kind of a support for TensorBoard, what you can do is you can tune out all the model parameters, and you can work with the performance checking and analysis of your models, and tune it based on your requirement, right? At the end of the day, it's going to save a lot of time, it's going to save a lot of effort, and if you have saved time and effort, it means you're making more money in a production environment, and it is as simple as that. It's not just saving time and money. When we talk about TensorFlow, you have to understand that this kind of a data visualization that we get, it's extremely aesthetically pleasing to use. It's completely functional in a way where if you probably see a lot of data in charts, you might not pick up a fault in the data, but then as soon as you put it out and lay it on a graph, that'll stand out to you like a sore thumb. So in that particular case, using TensorBoard is something which is very effective too. And then when we talk about model deployment, right? See, with model deployment, it is extremely important that you understand that TensorFlow it's ready to use with TensorFlow. Of course, you can use PyTorch, you can use frameworks such as Scikit-learn as well. And with this case, you have to understand that depending on your model complexity, you're going to require resources, right? So in this particular case with Kubernetes, you have something called as auto-scaling that happens, right? So it will go on to assign these resources automatically based on the level of computing power your machines need, and it's going to start scaling from maybe 1 machine in a cluster to 10 machines in a cluster, 100 machines in a cluster, to go on to actually have the best performance possible too. And then when we have to talk about the KubeFlow serving as well, right? So this is one of these tools that will run locally and on the cloud premise as well. So it is not that you have to have a compulsory cloud setup to make use of KubeFlow. If you have a local network architecture where you'd want to use this, of course, you can use that as well. So that kind of a flexibility is really one of the big advantages that comes whenever we talk about model deployment. And then with model deployment, with this kind of a ease of use, it means, of course, efficiency goes up again. When efficiency goes up again, you save time and money. You save time and money, you're making more money to the organization itself, right? So guys, now let's take a quick look at the GitHub, and of course take a look at the KubeFlow website as well. And now, coming to the GitHub, as I told you, you can track their entire project here, right from what's happening right now, all the pipelines that they have, the manifest, the websites, their entire community and everything. So they have a huge GitHub profile, where they have a huge GitHub profile where you can check out a lot of things here. So make sure at the end of the day, before you start working, or as and when you start working towards learning KubeFlow, right, understand what they're doing in a way how best you can use it, right? So you can there'll be all the top languages that they've put using. You can see JSON.NET, people are using Go, TypeScript, Python, and a lot of others as well. So if you just click on these repositories, you will see a lot of things. And of course, whenever you talk about all the dashboards that go on to use it, and all the tests that go on to see if these dashboards are functional, the updates are working or not, you can find a plethora of information on this particular website. So I would really suggest and urge that you guys check it out. And after that, coming to the actual KubeFlow website, to get started with, to get a quick start, you can of course take a look at the documentation to get work with, right? It's one of the biggest machine learning toolkits out there right now. We have to work on Kubernetes. And one important thing, as I mentioned in our session, before you start working with KubeFlow, right, you need a basic understanding of Kubernetes. And of course, you're going to need something called as Kustomize as well. Kustomize is one of these configuration management tools that will give you a template free way on how you can work with the tools as well. So in that particular case, you really wouldn't require a lot of customize, but of course the knowledge on Kubernetes is definitely something that's needed. So you can see how you can go on to choose a KubeFlow deployment option as well. Do you want a single node deployment where you're going to run everything in one particular node on a cluster? You can do that. Do you want to have a cloud deployment based on all the types of clouds that we discussed? It is possible. So do you want on-premise installation? Do you not want on-premise installation? So based on all of that, right, it's going to give you a lot of flexibility to go on to get started as well. But then, as I just mentioned, to go on to use all of these on a cloud platform, guys, you really have to follow certain basic rules. And of course, it's not just rules, certain installation steps that are out there. See, for GCP, these guys have a deployment guide. For AWS, they have another one. If it's Microsoft Azure, what we call as AKS, then of course they have another one. IBM Cloud, there's another one. If we have more documentation for OpenShift as well. So to deploy all of these, what's the first step? You really have to go on to install it, right? So these guys will give you the complete steps that you need to basically get started with it. Of course, you're going to need a lot of training to use it. You're going to need a lot of head start, a structured way of learning to understand, first of all, what this is, why it is used, all the things that we already checked out, and then actually using it, right? So in this particular scenario, depending on where you want to deploy KubeFlow, they're going to give you install instructions. They're going to tell you how you can uninstall it, how do you create a cluster, how do you use the ICRs, or what we call as the IBM Cloud Registries. There's so many different things, and of course they provide all the basic documentation to do this, and that's what makes me very happy about it. And then once you are ready to, let's say, go on to use it, now you want to make use of KubeFlow on the IBM Cloud, they're going to give you in depth about how you can first of all deploy it, and how you can install it, how you can secure it, and all of that, right? So with each of these tools, it's basically a very simple command line interface. You're going to need a command line interface where you log into the cloud, and once you log into your cloud, be it AWS, be it IBM, you just have to run a couple of commands there to make sure you can get all of your storage up, everything, and you can work with the deployment process. Well, you're going to have to build the code, you're going to have to allocate the resources, deallocate the resources whenever it's not required. You have to configure auto scaling, multi-user mode, version controlling, and all of that, right? So you have all the code, all the documentation basically that's needed to get you guys started. So if you just click on the documentation Intellipaat on their website, you should have the basic understanding of how you can go on to use this on any cloud platform of your choice that these guys support as well.
The problem statement. So the problem statement is here. Your client is a large MNC and they have 9 broad verticals across the organization. So one of the problems your client is facing is around identifying the right people for promotion and prepare them in time. So it is only for manager position and below. So currently the process that they are following is, first one, they first identify a set of employees based on recommendations and past performance. Then the selected employees go through the separate training and evaluation program for each vertical. These programs are based on the required skill of each vertical. Then at the end of the program, based on various factors such as training performance, KPI completion, employees gets promotion. So talking about the KPI completion, so only employees with KPIs completed greater than 60% are considered. Now, this is the actual problem statement. Now, let us look at the scenario that is provided by the company. So the final promotions are only announced after the evaluation, and this leads to delay in transition to their new roles. Hence, the company needs your help in identifying the eligible candidates at a particular checkpoint so that they can expedite the entire promotion cycle and they can speed up the process actually. So the first thing is they have provided multiple attributes around employees' past and current performance along with demographics. Then they have provided multiple attributes around employees' past and current performance. Now the next and the second point is the task that we have is to predict whether a potential promote at checkpoint in the task set will be promoted or not after. Sort out this thing also for making the model more accurate. Then comes KPI metrics, that is key performance indicator. So it denotes and it indicates the metrics for the performance of the employee. So 0 over here denotes that the performance is not at all good for giving them promotion, and 1 indicates that the performance is decent enough to give the promotion. Then comes awards 1. So this is 0, 0, 0, and here it is 1. So award 1 is 1 over here for a particular employee whose ID is 77981. And now average training score. So this is the training score of an employee while pursuing a training for the company. Here it is 85, 73, starting from 49, 60, 50, and so on. So it can be a major factor for predicting the promotion for the employees, that is how well they perform in the training and what is their score in the training. Then comes is promoted. So 0 means that they are not promoted and 1 means that they are promoted. So in this data where the promoted thing is 1, so this is the average training score, and here this shows the KPI metrics, that is also 1. Then the next one is the length of service, that is 6 years, and so on. So these are the parameters and the data set on which we'll be working on for making an AI model to resolve the business problem. Now let me go to the training set. So this is the training set and it consists of, go to this part, okay. So this also consists of employee ID, then department, region, education, gender, recruitment, number of trainings, age, previous year rating. Then comes length of service, KPI metrics, awards 1, and then average training score. So these are the parameters over here. So we have divided the data set into train and test set so that we can train the model using the train set and we can test the model using a separate data set, that is HR_test. Now the reason for using the test and the train data for the model is that we do not want our model to overfit the data. So in future it may get different sets of data and it may face issues in giving accurate results because the model is overfitting the data set that it is having. That is why we are using a separate data for training the model and a separate test data for testing the model. Now we have understood the data, that is trained data and the test data. Now let us move on to the steps that we'll see further. So the next step that we'll be going through is pre-processing and feature engineering. So in this we'll pre-process the data with using the different types of pre-processing. That is, we will manipulate the data, we will remove the null values and the missing values from the data set, and before that we'll use various and we will import various types of packages that are required for the implementation, and we'll see the info of the train and the test data set as well as the description such as the standard deviation, the mean and the average of the values. Then we'll perform feature engineering for the model and for the dataset values. Then we'll build the model using various algorithms that are used to build AI based applications, and we'll apply feature scaling so that all the values comes in the common slot and the prediction becomes more. And finally we'll evaluate the model that is created using various parameters and metrics of model evaluation, and then we'll visualize it using models visualization. So further, let's go to Google Colab for the implementation part. Now this is our Google Colab. So first thing you have to do is just go to this folder option, click on this upload session storage button and upload the training and the testing dataset. So I have already uploaded it, so I'll just show you. So I'll scroll down and here is the data, that is train and test data that I'll be using. So whenever you open Google Colab, so the first thing you have to do is you have to load the dataset. Otherwise you cannot work with Google Colab and create algorithms and AI based applications. So also one thing more, if you load the dataset now, so it is for this instance on which you are working. If you will close the tab, then the dataset will be deleted. So again and again you have to load the dataset. Now I have written the code over here, the entire code. So I'll implement and I'll explain every code, what it is actually built for and how it is working. So first I'll import warnings and use this warnings.filter warnings ignore. So this is used to ignore the warnings that are displayed by the interface or by the Python library while implementing the program. So I'll run this and now you can see it has been successfully executed. Now the next thing is the scientific and data manipulation libraries. So I have imported pandas, I have imported numpy, then import math, gc, os and the sklearn package. So we use pandas basically for data analysis and data manipulation, and it provides various features for the analysis of data. Then comes numpy, so we can work with multi-dimensional data and matrix arrays using the numpy library. Then comes importing of maths that help us to implement various mathematical operations. After that, import gc for the garbage collection, and then importing os so that the packages and libraries are imported so that the application which we are building using the various modules and libraries of Python, so it gets added according to the operating system. Then importing scikit learn, that is sklearn. So scikit learn basically help us to implement classification, regression, dimensionality reduction and many other machine learning algorithms we can implement using the sklearn or scikit-learn library. So I'll run this and now the installation of the scikit-learn is done. So I have already done it. May take a while for you to get this. So I'll run this pip install scikit-learn to install the scikit-learn library. So it will take a while and it will get loaded. So these are the basic steps that you need to implement before data pre-processing. So these libraries and packages are the first thing that you have to load and install or download for working further with the data pre-processing task or creating algorithms. Then comes more libraries. So in sklearn we have pre-processing, model selection, tree, ensemble, and metrics. So from sklearn library, we import the packages for pre-processing and model selection, tree, ensemble, and metrics. So why we do that? Because we have to use label encoder, one hot encoder. We want to use min max scaler, normalizer, robust scaler. Then comes max absolute scaler, and then we used model selection thing for using k-fold, stratified k-fold, train test split, then cross validation score. After that comes the tree package, for which we have to use decision tree classifier, random forest classifier, and then voting classifier using the ensemble package of sklearn library. Then comes the metrics package of the scikit-learn library, using which we'll evaluate, or first we'll load F1 score, then confusion matrix and classification reports that help us to implement the functions for F1 score, calculating confusion matrix for accuracy, and the classification report. So we'll use this from sklearn.preprocessing, import standard scaler, min-max scaler, normalizer, robust scaler, and for loading all these modules from the library, we'll use these commands. So let me run this. So it shows that it is successfully executed. So before moving ahead, let me explain you the standard scaler, min max scaler, so all these, why we are actually using it. So starting with standard scaler, it actually removes the mean and scales each feature or variable to unit variance, and this operation is performed feature wise in an independent way. So standard scaler can be influenced by outliers, so the values lying beyond the common slot of area where the actual values are lying, so it can be influenced by the outliers, and it involves the estimation of the empirical mean and the standard deviation of each feature. So it scales it, so it helps the model to predict in a better way. Then comes min max scaler. So min max scaler rescales the data set such that all the feature values are in the same range from 0 to 1. So actually there are too many values and it can have different values from 1 to any of the value. So we need to rescale the value in a common slot such that we can create a plot out of it and gets a better visualization. So min max scaler helps in this way. After that comes the normalizer. So the normalizer rescales the vector for each samples to have unit norm independently of the distribution of the samples. Now then comes the robust scaler. So unlike all the other scalars, the centering and scaling statistics of this scalar are based on percentiles, and therefore they are not influenced by a few number of very large marginal outliers. Then consequently the resulting range of the transformed feature values is larger than for the previous scalars, and one of the most important thing to note is that they are approximately similar, and for both features and for most of the transformed values they actually lie in a range of -2 to 3. Now coming to max ABS scalar, so it differs from other scalars and such that the absolute values that are mapped, they are in the range of 0 to 1. So they are the absolute values, and on the positive data the scalar behaves similar to min max scalar, and therefore it can suffer from the presence of large outliers. Then comes the voting classifier. So the logic behind the voting classifier is creating a separate dedicated model and finding the accuracy for each one of them. So we actually create a single model that is trained by the other models and predicts the output based on their combined majority of voting for each output class. So that is the logic behind the voting classifier, and we'll use this voting classifier for our project. So I hope the importing of the libraries and packages is clear. Now we'll move ahead and we'll import class and we'll install the cat boost. So I'll click on it. So you have to use this command pip3 install cat boost, as we'll be using the boosting algorithms such as xgboost, lightgbm and cat boost for preparing our model. So it will just take a while to load, and I have already loaded this and I have downloaded the packages. related to cat boost. That is why it is showing requirement already satisfied. Then I'll import the XGBoost and use an attribute that is XGB for it. Then light GBM and then cat boost. So I'll click on it and it is successfully executed. So why do we actually use XGBoost, light GBM and cat boost? So XGBoost is a scalable and accurate implementation of gradient boosting machines, and it has proven to push the limits of computing power for boosted trees that are used for implementing the algorithms for the sole purpose of checking the model's performance and improving the model's performance and the computational speed. So that is why we use XGBoost. So also XGBoost is used for supervised learning problems where we use the training data to predict a target variable. So that is why XGBoost is used for building the AI models. Then coming to light GBM, that is a gradient boosting framework that uses tree-based algorithms, and it is designed to be distributed and efficient with the following advantages, that is faster training speed and higher efficiency. Also, it has support of parallel and GPU learning capable of handling large-scale data. So that is why light GBM is used as a classifier. Then coming to cat boost algorithm, so it is an algorithm for gradient boosting on decision trees. So it is basically used for search, recommendation systems, personal assistant, self-driving cars, weather prediction, and many other search tasks. So one of the major benefit of using cat boost is it can handle missing values internally. Also, by default, cat boost uses one hot encoding for categorical features with a small amount of different values in most of the modes that we use. And so coming to one hot encoding, we use it for all the categorical features with a number of different values less than or equal to the given parameter value in a specific range. So we'll use all these algorithms for our AI project for building our model, and I hope you are clear with the algorithms that we are using. So let me run this and you can see it is being successfully executed. Now I'll run this. That is, from XGBoost we are importing XGBoost classifier. So it is also successfully loaded. Now comes the data visualization libraries. So we will use matplotlib, seaborn and plotly package for the data visualization. So I'll run this. Okay. Now comes the randomness of the data that is being selected. So we'll use np.random.seed. So it is actually used to save the state of a random function so that it can generate same random numbers on multiple execution of the code on the same machine, or it can be on different machine. So the seed value is the previous value number generated by the generator. So that is why we'll use this np.random.seed. After that, we have to set the location path from where we'll use the dataset. So we have already loaded the dataset, and you have to do it again and again for the Google Colab if you are using Google Colab. So now I have already imported OS. So it is just written over here from Google Colab import files, then train pd.read csv is used to load the dataset. I'll run this and let us see. Okay, so it is being successfully executed. Now we'll display the dataset of train and test. So we use this display function to display the values. So I'll run this and it will display the training values and the testing values. So let me scroll down. So the first one is training value and the second one is the test values. The second one are the test values. So this shows the index. Now employee ID, department, region, education, gender, recruitment channel, then number of trainings, age, previous year training, length of service, KPI metrics that is greater than 80, and awards 1, average training score, and is promoted. So as we have already discussed the training dataset, and the KPI metrics should be greater than 80% to get the promotion. So here it is. Now let us check out the test data set. So again, these are the index, employee ID, department, region, education, and it will not have the is promoted column because this is the testing data set. That is, these are the independent variables using which we have to predict whether the person has to be promoted or not. That is the variable is promoted. Now further, let me go to the exploratory data analysis that we have to perform. So for this, first we have to look into the information of the training set. So for this, we'll use train.info to display the information of the trained data. So let me implement this. And now we get the training data. Along with it includes the non-null count and the data type. Also, the count of the types of data type, that is float 64 is 1 time for the corresponding column, and it is previous year rating, and integer is 8 times and the object is 5 times. Also, it shows the memory usage, that is over here it is 5.9 plus MB. So this shows the information related to train set, and then let me display the information related to the test data. So here it shows that there are 23,490 entries starting from 0 to 23489, and data columns total there are 13 columns, and non-null count along with data type and the count of data type over here, and the memory usage is 2.3 plus MB. So this is the information regarding the test and the training data. Then comes displaying the descriptive statistics of train data. So just talking about exploratory data analysis, so it is a part of the data pre-processing where we actually gather the information related to the data. So we check the info, we check the description of the data such as the average, the maximum and the minimum values, along with the mean or the standard deviation, the type of data, memory usage, and the non-null count, and many other factors. So we look into that in this data pre-processing step, or you can say the EDA, that is exploratory data analysis. So let me run this train.describe. So it shows more information related to the training data set. So it shows the count, it shows the mean for all of these columns, then comes the minimum value, maximum value, and the interquartile range. Now let me check the description about the test data. So I'll run this, that is test.describe. Again, it shows the count, the mean, the standard deviation, minimum and the maximum value, and the IQR, that is interquartile range. So this shows us the description of the train and the test data. Now further we'll display the number of unique values and the actual values. So we have to first define a function, def for defining the function, that is display unique, and it will take the argument as data. So here we have passed the argument of train data. So display unique, we have called the function. Now what does this function do? So for column in data dot column, that access the columns present in the data set. So we have to print the number of unique values in the column, that is the column corresponding to the trained data set that we are accessing to. Then the columns are then using the str function data, then column dot n unique. It will fetch the unique values from the data set or from the column. Then the actual unique values in column. So again, now further to get the actual values, so here we use again the str function and then the sort values function that sorts the data in the ascending order, because the ascending is set true over here. So for getting the actual values, we have to use this sort underscore values function, and this na underscore position takes two strings, input last or first, to set the position of null values, and accessing this unique function gives the unique values from the data set. So it shows the number of unique values simply, and using the sort values function we can access the actual values in the column. So let me execute this, and now here we get the output. So number of unique values in employee ID are 54,808. So starting from 1 and it goes till this index. So these are the actual values, and then comes the number of values or unique values in department column, that are 9. But the actual unique values in the department column are analytics, finance, HR, legal, operation, procurement, R&D, sales and marketing, and technology. So the actual values are shown over here. So these are the actual values. So this is how we actually access the actual values using the sort underscore values, and we can keep descending also over here, but we have kept ascending order. So these are the actual and the unique values for all of the columns of the train data set. So we can check it for test, but we'll leave it for now. And now we'll move on to displaying how each feature is related to the target variable in a flow. So for this we will use a plot using the parallel categories diagram. So the parallel categories diagram actually it is also known as parallel sets, and it is a diagram, or you can say a visualization of multi-dimensional categorical data sets, and each variable in the data set is represented by the column of rectangles where each rectangle corresponds to discrete value taken by that variable. So here we pass in the columns. So the columns are department, education, gender, previous year rating, KPI, metrics, then recruitment channel, and is promoted. And color is based on the is promoted column. Then we use the continuous color scale. So using this sequential.agrenil, so we plot the figure using multiple colors. So this figure.show help us to show the figure. Now let me implement this and let us have a glance at the figure that we get. So it will just take a while to load. Till then you can just wait. Okay, this is the figure that we had. So this figure is very descriptive and it shows you the data. So let me show you how you can actually read this figure and how actually you can understand the various dependent or independent variables from this figure. So there are columns named department, then education, gender, previous year rating, KPI metrics, recruitment channel, is promoted. So is promoted is shown over here. So it consists of the value as 0 to 1. So hence its scale is from 0 to 1. And then comes the individual categories of the columns. So in department, there are multiple departments such as sales and marketing, operations. So this section is the operations one. So you can see when I have kept my pointer over here, so it shows the relation, actually the data relation from other columns such as education, gender, previous year rating, KPI metrics, recruitment channel, and is promoted.
Just a quick info, guys. Test your knowledge of AI by answering this question. What is artificial intelligence? A. Putting your intelligence into computer. B. Programming with your own intelligence. C. Making a machine intelligent. D. Putting more memory into computer. Comment down your answers in the comment section below. Whoever gets the correct answers will win 5,000 points in Intellipaat wallet. Subscribe to Intellipaat to know the winners. Now let's continue with the session.
So the count it shows is 11,348. That is, there are 11,348 employees for the operations department. When I kept my mouse pointer for sales and marketing, it shows the count as 16,840. And then comes the count of this sales and marketing, and then technology. So the count is, let me click on this. So the count is, you can see over here. So this shows the count as 7138. Then comes analytics, that is 5352, R&D, which is the least, and then procurement, finance, HR, and legal. Now coming to education. So when I kept the pointer over here. So it shows the count for the master's and above degree as 14,925. So here the category is written over here. Then when I came to this bachelor's, it shows the count as 36,669. Then coming to below secondary, it is 2409. And then the final one is the below secondary one, and this last one is the below secondary one, that is 805. Now coming to gender, then the count is 16,312, and the count for the male employees is 38,496. Now previous year rating starting from 5. So the employee who are having the rating as 5 are 11,741. Then 3, rating of 3 is 18,618 employees are having a rating of 3. Then 1, it is 6223. Then rating of 4 is of 9877 employees. After that, the rating of 2 is 4225. Now the KPI metrics greater than 80. So for 1, that is the metric, KPI metrics is greater than 80, the count is 19,291. And for the employees for whom the KPI metric is less than 80% are 35,517. Now again, the recruitment channel is sourcing, other and referred. So for sourcing, the count is 23,220. Then for others, the count is 30,446. Then for the referred one, it is 1142, that is the least. Now I'll come to the is underscore promoted column. So the count it gives is 50,140 people are not promoted, that is the value is 0, and the promoted people's count is 4,668. So you can see over here the structure of the figure. Now for the next one, we will have a heat map. So we will display the correlation between the features through heat map, and lighter color higher correlation, and if close to 1. So lighter color shows the high correlation. So for this we use sns.heatmap, and as we are making the heat map for the train dataset, so we'll use this train.corr for correlation, and this annotation or annotate is true. So I'll run this and we'll get the heat map. So here are the employee ID. So these are the columns: employee ID, number of training, age, previous year rating, length of service, KPI metrics greater than 80%, awards won, and then average training score is promoted. And this scale shows the is promoted thing starting from 0 and 1. So the values are only 0 and 1. Now the x-axis of the figure, so it is not actually x-axis, but it is the other side of this figure. So it has again employee ID, number of trainings, age, and previous year rating, length of service, KPI metrics, then awards won, and average training score, and is promoted. So a heat map is a two-dimensional graphical representation of data where the individual values that are contained in a matrix are represented as colors. And the Seaborn library, we have imported it for this purpose, and the Seaborn Python package allows the creation of annotated heat maps, and which can be tweaked using the matplotlib tool as per the creator's requirement. So we are creating this for the correlation, finding the correlation. So this color shows us the correlation between all these parameters that we are evaluating. So this is the heat map that shows the people who are promoted, or not the people who are promoted, but the correlation between these columns. Now let me go to the next part, which is finding the duplicate rows from the trained data if it is present. So we have to check for duplicate rows to remove them. So we will create a method that is remove duplicates that will have an argument of data. So in this we'll print before moving or before removing duplicates the number of rows, comma data dot shape. We'll give the argument as data dot shape. Then we have to implement the logic or the action, that is data dot drop duplicates. To drop the duplicates, keep equal to first in place equal to true, and then again we have to print after removing duplicates the number of rows. So again the argument is data dot shape. So actually this data dot shape returns the data in the form of array, and then we'll return the check duplicates. And now I'll just implement this, run this, and now I'll call the remove underscore duplicate and give the data or the argument as train. And now I'll click on this. Further, after the successful execution of the code, we'll get this. Before removing duplicates, the number of rows are 54,808, and after removing the duplicates, the number of rows are again 54,808. Now it will return the checked duplicates. After that, we'll handle the missing values. So remember that still we are in the data pre-processing or the manipulation part. So we have to deal with the missing values. So missing values are present in the previous year rating and education columns in both train and the test data. So here I have just written for the reference why is data missing in column previous year rating. So data was not entered because those employees were fresher. So as I have already told you when we were discussing and when I explained you about the data set, so data was not entered because those employees were freshers, that is length of service is 1 is equal to 1, and they did not have the previous year rating. So the no data would have been there in the data source itself for these employees. So logically we are imputing with 0 as freshers with 1 year experience and may not have previous year rating at all. So filling the missing values in train and test data. So what we'll do is we'll use this train data set and the test data set, and in this bracket we'll give the column name, that is previous year rating, and what we'll do is again to access the previous year rating. So we are actually accessing the previous year rating, and then we'll use this dot fill na with 0. So it will fill those values with the 0. So the next thing is we'll access the column of fresher for the train data set, and then we'll use this previous year rating and apply function, and then we'll use this lambda. So here we'll put the condition. So if x is equal to 0 is equal to 0, then the employee will be a fresher, otherwise the employee is an experienced professional. After that we'll display the fresher column with the value counts, and again the previous year rating, length of service, and this fresher tag that we have used using the condition that is applied over here for marking the tag as a fresher. Again we'll use this display function to display this previous year rating, length of service, then fresher for the first 25 values and for this we'll use this head function. Now I'll run this, and here we get the output. So these are the columns and they are replaced by values as 0, 1 fresher. So this is the fresher column and this is the fresher tag that we have displayed using the display function and putting the condition over here. So the experienced professionals are 50,684 and the freshers are 4,124, and the data type is integer again. So we have used the previous year rating, length of service, and the fresher column for displaying the data. Now again we have displayed the data for previous year rating, length of service, and this tag I should have changed it to experienced. So okay, so I have put a condition over here. So let me go to that one. Okay, so here if x is equal to 0, then it will be a fresher, otherwise experienced. So that is why it is showing data over here for experienced as well as for fresher, and the length of service, previous year rating. So this is actually about the removal of the missing values and sorting out the missing values that were there in the data set. So we actually saw some empty blocks in the data set. So we filled in with the values as 0. So for that we used fill NA and filled with 0. So this is done. Now next what we'll do is we'll display the missing values in the train and test data. So to display that, we'll use this display function, and this will give the text as train corresponding to the missing values in train set. So we'll use this train.isNull.sum. So isNull for counting the for getting the null values, and sum function to sum all those. And to display it, we'll use this display function. Same for the test. So I'll run this.
If you want to make a career in data science, then Intellipaat has IIT Madras Advanced Data Science and AI Certification Program. This course is of very high quality and cost effective, as it is taught by IIT professors and industry experts.
So for training set, so this is employee ID, department, region, education, gender, recruitment channel. So for all other columns, the null values, so there are no null values, there are 0 null values, but for education there are 2409 null values present. And for the test column, the employee ID, department, region, and all other columns are not having any null values. The count is, or the sum of those null values is 0. The count is 0. And for the education, it is 1034. So as the test dataset is less than the training dataset, so it is showing less. So we have counted the null values over here. So now after executing this, let us handle the null values. So for this we'll use ffill, bfill. So I have written this for reference, so you can read this. So talking about ffill, so this is forward fill, that fills the missing values with previous row value. And if previous row value is null, then it moves to the next element without filling. That is why we use ffill and bfill both. So what does bfill do is, so it is backward fill, that fills the missing values with next row value. And if the next row value is null, so it moves to the next element without filling. So what actually happens is, for example, for just explaining you, if the system goes to 4th and 5th row and the 4th one is empty, then it iterates to the 5th row and fills the data of the 5th row into the 4th row. So this is actually the backward fill. And in forward fill, what happens is it fills the missing value with the previous row value. For example, if 4th row is having a data and 5th row is empty, the data is not present, then the value present in the 4th row will be added for the 5th row data. So we use both forward fill and the backward fill to fill in the data. Also, filling with mode and new category called others are most commonly used technique which didn't work here. So we are not using that. So we can assume that while collecting data relevant members, data were collected close to one another. So it is not too fluctuating, that means. So talking about the training, now we'll fill in the values for the education column. So here we have used this train, inside it we have given the argument inside the square brackets as education. Then we'll use this dot ffill for forward fill, and we give the argument in this way, that is access is equal to 0 for all of the train and the test data. And finally, we display the data and we try to actually calculate the sum of all the null values that are present in the training data set and the test data set using the isNull and sum function. So I'll run this and let us see the output. So it will just take a while to load. So here we get the output for the train and the test data set. So employee ID, department, region, education, gender. So you can see over here, so we have implemented it on the education column by using the forward fill and backward fill. So the count has come down to 0 for the education column. Now after this, we'll work on feature engineering. So based on the age distribution, most of the employees are in the range 20 to 40 who will be also waiting for a promotion. And so we have created 2 bins, 20 to 29, 29 to 39, and remaining 1 bin for 39 to 49. So we have used dist plot, so plot a univariate distribution for the observations. So I have written this for the reference so that you can refer it in future if you have any doubt and all. So you can see the description of this. Okay, so moving ahead, we'll use this sns.distplot and we'll give the train as the data and this age column, and after that we'll use this train and inside this square brackets we'll give the age. We'll use this pd.cut and give in the argument as train and the age column. So the train data set along with the age column or for the age column, and bins will be 20, 29, 39, 49, and labels that would be given to these bins are 20, 30, 40. Same for the test one. For age column, pd.cut, bins will be 20, 29, 39, 49, and the labels will be given as 20, 30, and 40. So let me run this, and now we'll get the plot like this. So feature engineering is nothing but extracting the feature or the properties from the dataset and the expertise and the knowledge that we have. So this is the plot that we have after plotting the age column. Now after this, we'll split the train data into predictors and the target, that is independent and dependent variables. So this is the step that we have to do before creating our model. So here we'll split train into x underscore train, that is features, and y underscore train, that is target. So in x train, we'll select all of the columns, that is department, region, education, gender, recruitment channel, number of trainings, age, previous year rating, length of service, KPIs, metric that is greater than 80%, awards won, and average training score. And in this y train, we'll select the is promoted column, that is the separate column that we have to predict using the test dataset. So we will add this in the y train section, and then we'll convert the y train into a frame using 2 underscore frame because it is a single parameter and the output is expected to be in data frame. So we'll use this to convert it to a frame. Now comes the x test. So we'll use this x underscore test, and inside it we'll give the argument or the number of columns, that is department, region, education, gender, till average training score. So now we have successfully splitted the train and the test data. So after running it, so it has no error, that is it has been successfully executed. Now as we have splitted our data set into train and test, now we'll perform the data encoding using the label encoding and the one hot encoding. So what does it actually mean to perform these operations? So actually label encoding refers to the converting of the labels into numeric form so that to convert it into the machine readable form, and the machine learning algorithms or the AI algorithms that we are using for building our AI based application can then decide in a better way on how those labels must be operated. And using one hot encoding allows the representation of categorical data to be more expressive, and many or the various machine learning algorithms cannot work with categorical data directly. So the categories must be converted into numbers. So this is required for both input and output variables that are categorical. So we use one hot encoding for that. So we'll define a function that is data encoding, and given the parameters, the arguments, that is encoding strategy, encoding data, and encoding columns. So let me go down and check where I have called this. Okay, encoding data encoding. So I'll check where I have called this function. So this is data encoding I've called over here, then encoding strategy, and then the data, then the columns that we have to give. Now I'll go back over here. Now what does this function do? So if encoding strategy is label encoding, then we have to print if label encoding, and the encoder we have to put in the label encoder because we are using label encoder. And then we will put a for loop over here. So for column in the encoding columns, we have to print column, then encoding data, and in this encoding data the column will be inserted, and then this function has to be executed. So encoder.fit transform, and then the argument must be given. So tuple encoding data, again we'll use the column as the argument. After that, if this is not true, then we put in elif condition where encoding strategy is equal to one hot encoding. So if this is the scenario, then we have to print elif one hot encoding, and then encoding data we'll use pd.getDummies for encoding data. So this pd is the instance of the pandas library, and this getDummies will give us the categorical values, the dummy categorical values. And after that comes the dtype list that we have to define for float 64, float 32, int 64, int 32 for the data type. So this is the data types list. Then encoding data as type we'll use, and then data types list, and then we'll access the data types. So after implementing if elif, these two lines of code will be implemented which shows the data type, and then return encoding data. So using these condition we'll implement the data encoding technique. So here for description I have added this quote and many points related to it. So let me read it for you. So applied one hot encoding, it will be applied to object categorical columns only, and it's most common to one hot encode these objects columns since they can't be plugged directly into most models. Then pandas offers a convenient function called getDummies to get one hot encodings. So using this getDummies we get a dummy variable or a dummy value for the categorical or for the encoded values. So get this using getDummies. And many machine learning algorithms cannot operate on labeled data directly, then they require all the input variables and output variables to be numeric. This means that categorical data must be converted to a numerical form, and a one hot encoding can be applied to the integer representation. Finally, this is where the integer encoded variable is removed and a new binary variable is added for each unique integer value. So you can go through this description for the reference. So I'll run this. So it has been successfully executed, and you will get the result in the next code when we'll implement it. So just for reference or example, I have added the data encoding for this color, that is red, blue, green, red, blue, green. And I have created this df as the data frame, and then pd.data frame. I have given the data over here columns as color. Then I'll print before one hot encoding and call the function as display df, and then I'll print after one hot encoding and display pd.getDummies. So for the first one, so we get the result as before one hot encoding. It is displaying the data frame, and in the second one we get the result after one hot encoding. So I'll run this in one go. So let me explain this one also. So encoding columns, encoding strategy. So I'll go in this code. So we have created a function data encoding, and the parameters are encoding strategy, encoding data, encoding columns. So over here are encoding columns, encoding strategy. So encoding strategy is label encoding, one hot encoding, and the encoding columns are region, age, department, education, gender, and recruitment channel that we have to encode. So while implementing this, we have to just give in the index. So here I have called the data encoding function that we have defined earlier. So xtrain encode, xtest encode, and we have called data encoding and data encoding strategy. So index is 1 and the data is xtrain and encoding columns. So it will take the entire column, so all of the columns, and then the second one is encoding strategy xtest on xtest and encoding columns, so it will take all the columns. Then for displaying the encoded train and test features, we'll use the display function and we'll display the first few values using the head function. So xtrain encode, xtest encode. So let me run this, and the first one gives the color data frame, that is red, blue, green, red, blue, blue. So these are encoded in 0, 1, 2, 3, 4, 5. So we have performed one hot encoding, and after performing one hot encoding we get the following results, that is color blue, color green, color red. So these three are the colors, red, blue, green, and these are the indexes, and the encoding that is done is, so this is the data frame. So we have converted it into a data frame, that is why it is showing a data frame over here. So color blue, color green, color red. So this is these are the encoded values for it. Now let me go up and let me check. So this was the color part, and then we defined the encoding strategy. Then we have called data encoding 2 times for train and test, and it is showing one hot encoding, one hot encoding. So it has performed one hot encoding. So why it has performed? Because the index that we have given over here is 1. So here it is 0, label encoding is 0, having an index of 0, and one hot encoding is at the index position 1. So one hot encoding will be performed. So for performing one hot encoding, first it will print elif one hot encoding that shows that it is performing this type of encoding, and then it has performed the one hot encoding using the pd.getDummies. So it is displayed over here. So these are the result for the encoded rows, the columns that are over here. So you can check it out, the encoded values. So we have encoded it for region, and then it shows various region and the values, then for gender, recruitment channel, and so on. After that, after the encoding has been performed, so our data is encoded, and now we have to perform scaling. So we have already discussed about the scaling types, that is robust scalar, standard scalar, min max scalar, and max ABS scalar. So I have told you about these type of scalars. So we will directly create a function using this data underscore scaling, and we'll give the argument name as scaling strategy, scaling data, scaling columns, and we'll give in the condition as if scaling strategy is robust scalar, then the scaling data will be, and inside this square brackets we'll give the scaling columns that we need to scale, and then we'll use the robust scalar dot fit transform to scale the values using the robust scaler, and then the scaling data which we have used and we have passed in the argument, and the scaling columns that we need to scale. Same with the standard scaler. So we'll give in the condition as LF. So scaling strategy, if scaling strategy is equal to standard scaler, then we have to use this standard scaler dot fit transform, and again the scaling data along with the scaling columns, or you can say the corresponding scaling columns.
Just a quick info, guys. Test your knowledge of AI by answering this question. In which of the following application does AI has its expansion? A. Planning and scheduling. B. Game playing. C. Robotics. D. All of the above. Comment down your answers in the comment section below. Whoever gets the correct answers will win 5,000 points in Intellipaat wallet. Subscribe to Intellipaat to know the winners. Now let's continue with the session.
That we have to put in over here. After that, again LF scaling strategy is equal to min max scaler. Now same with the min max scaler and max ABS scaler. So scaling data, then scaling columns, then again using the fit underscore transform method and given in the parameter as scaling data with the corresponding scaling columns that we need to scale. And final else condition consists of the robust scaler. So if any other scaling sent by mistake, it still performs the robust scaler. So we'll use the same line of code that we used for robust scaler, that is scaling data, corresponding columns, and then robust scaler function dot fit underscore transform, and finally we'll return the scaling data. So I'll run this and let's check. Okay, so it has been successfully executed. Now the next one is where we will call the data scaling function or the method. So this is the data scaling method that we have created over here. So this is the description that I have given for reference. So let me read for you. So robust scaler is better in handling outliers. So standardization of a dataset is a common requirement for many machine learning estimators, and typically this is done by removing the mean and the scaling to unit variance, and the outliers can often influence the sample mean variance in a negative way. So in such cases, robust scaler, which uses the median and the interquartile range, often give better results. So here we have defined the scaling strategy. So that is robust scaler, standard scaler, min max scaler, and max ABS scaler. Now we'll use this x train scale and x test scale as the variable or the instance, and we'll store the values after calling this method, that is data scaling. We'll pass the argument as scaling strategy, that will be 0 in the first one and 0 in the second one. So 0 indicates that it is calling the robust scaler. So we have created the scaling strategy and we can call any one of this. So we have called the robust scaler. Then here we have given the x train encode and then x train encode columns. So what it actually shows is we are scaling the encoded values of train and the test dataset that we have encoded in the previous steps. Okay, then we'll display this x train scaled value and first few values of it for the train and for the test. So it should be test over here. Now let me run this and let us see what we get as the output. So this is the number of training, previous year, length of service, KPI, metrics, award won, average training, department. So now we have successfully scaled the values using the robust scaler. So what actually is robust scaler doing over here? So you already know. So it is handling the outliers and it is making the model more accurate and helping us to create such a model to give more precise results. So this is done. Now comes the most important step, that is creating baseline ML model for binary classification problem. So we will use some machine learning algorithms and you can also say that AI algorithms. So we have already looked around it earlier, that is XGB classifier, then cat boost, light GBM. So here we'll create a dictionary, that is key value pairs for ML model name, and then ML model functions with hyperparameters. So these are the hyperparameters. So we'll given the name as classifier, and at the 0th index we'll give the XGBoost. First will be cat boost, second will be light GBM. So using this XGB classifier, we'll define the hyperparameters, that is learning rate, n estimators, max depth, subsample, verbosity, scale, position weight, updater, base score. So the learning rate over here is 0.1. The number of estimators are 494. Maximum depth is 5. Subsample is 0.7, that is 70%. Then verbosity is 0. So what actually verbosity is? So verbosity in keyword, it arguments, and it usually means that showing more wordy information for the task. So actually giving the more description. Then the scale, position, weight, that is 2.5. Updater is grow, hist maker, then base score is 0.2. So we'll see the plot which will be plotted. Then it will be same for the cat boost classifier, learning rate, number of estimators, subsample, max depth. Then for light GBM, the importance type come in for extra. Then verbosity is -1. So you can see over here the verbosity is -1. Here it is 1 or 0. Sorry. So here it is 0. Here it is 1. So the more is the verbosity, the more wordy or the descriptive is the model, or you can see it is more adaptive and it shows the more information. So here it is -1, so it is low. Then maximum number of bin is 60, number of leaves 300, boosting type is Dart, learning rate is 0.15, number of estimators are again 494, max depth and other things are same as the cat boost and XGBoost. Now after creating a dictionary, after creating baseline ML model for the binary classification, we'll print. So we have to use this list, then classifiers dot keys and classifiers dot values for it. So after implementing it, let us see what we get as the result. So XGBoost, cat boost, light GBM, and this is what we get. Now our model is created and there are so many parameters to evaluate it. So base score, booster, column sample by level and so many others, but we need to improve our model as no model is perfect in AI or machine learning. So what we'll do is we have to improve the machine learning or the AI model. So as we have used this machine learning algorithms, so it is same for AI also. So I have written over here the ML model. So to improve the ML model with voting classifier, with model evaluation metric, we'll use this F1 and predict target for S promoted. So we'll evaluate the F1 score. So actually what voting classifier is, we have already discussed in the previous section while importing the libraries, modules and packages for the voting classifier. So we'll use the instance or the variable as voting model, and then we'll use the keyword that is reserved by the library or the package, that is voting classifier, and the estimators will given as the XGBoost, and then the second argument will be then list classifiers dot value to fetch the values, and for 0th index is the 1 for XGBoost, and the 1 or the first index is for cat boost, then light GBM. Then we have given over here as soft voting, and the weights are given over here 5, 5.2, 5, 5 and 5.2. So actually in soft voting the output class is the prediction based on the average of the probability given to that class. And you can consider an example Suppose you are given with some input for the three models and the prediction probability for class 1 and class 2. So if the probabilities are 0.1, 0.2, 0.3, and for the next one it is 0.2, 0.3, 0.4. So obviously the average of the second class is greater. So the winner is the second one. So this is the soft voting that we call in machine learning. So it is given over here. So then we'll use this voting model that we have created and use this fit method, and inside it we'll give the parameters as xtrain scale for the scaled values that we have created in the data engineering process, and we'll give in the y train for training the model. Then we'll evaluate the predictions of the voting using the voting model that we have just now created dot predict probability, and we'll give the x test scale for checking the performance of the model on the basis of test dataset. So we'll take the entire test dataset. So let me run this, and it will just take a while to get executed. So now get the output. So you can see over here, so the learning rate and the total time, remaining time. So you can see it is still executing. Now again it will take time, so let me tell you the next part that we'll implement. So next we'll work on the result, we'll see the result and try to improve the F1 score. So for this we'll, okay, it is completely executed. We see the values. So it took a total of 10.4 seconds to predict the outcome or to learn the features of it. Then the next part that I was talking about is the result and the improving of F1 score. So for this we have to round off the probability results, and for this we'll simply use an instance as prediction, and we'll give in the round function, and before it we'll use the integer that converts it to the integer, and then we'll have a for loop. So for value in predictions of voting that we have just now implemented for the voting model or the voting classifier, so predictions of voting will be counted over here, and then we'll create a data frame table for this result, and we'll store it in the result promoted section. So we'll use this pd.dataframe, and we'll give in the employee ID and is promoted, and it will have the predictions and the test set of the employee ID. Then this thing you need not to take care of. These are again the classifiers, and then you have to print list classifiers keys over here. So this will be same as previously we have used the classifiers over here. So this is the same thing. Now let me implement it and let us see the results. So list of classifiers, so XGBoost, CatBoost and Light GBM. Now next we'll print result promoted. So I'll type in print, then result, and now I'll run this, and you can see employee ID and is promoted. So these are all the IDs of the employees who are being promoted. So here you can see that the ID number 5973, so employee corresponding to this ID has been promoted. So this is how we implement it and get the result using the round of probability. Now next we have used the classifiers, that is classifier 1, classifier 2, classifier 3 for XGBoost, then Light GBM and CatBoost. So we are fetching the values and the index as same. We have used 0, 1, 2, and then we have used the array from the NumPy library and given the index over here, and then finally use the voting classifiers, and we have given the estimators as XGBoost, CATBoost, and then LGBM for classifier 1, classifier 2 and classifier 3 represented by CLF 1, 2 and 3. Then voting again is soft. Then we will predict the class probabilities for all the classifiers using the predict underscore prob function and giving in the argument as x, and using the classifiers for the XGBoost, CATBoost and light GBM along with the voting classifier that we have built over here. So all this we are using for predicting the probability. Now to get the class probabilities for the first sample in the dataset, we'll create two classes and then we'll create a 2D array and put a for loop where we'll use the probus instance that we have used for predicting the probability for the model using various classifiers. So these two has been created, and now we'll plot what we have created or what model we have created. So we'll plot. So we'll use n equal to 4, that is number of groups, then ind instance for np.arrange, so arranging these groups, and these are the group positions, and width will be 0.35, that is bar width. Then we'll use figure and ax as the instance for the subplots. So we'll use the plotly package. So plt.subplots is the function that we have to use, and then bars for classifiers 1 to 3 and bars for voting classifiers. So for classifiers 1 to 3 we'll use the instance of p1 and p2 and use this ax.bar function where ax is the instance and bar is the function taking the parameter as ind, that is the group's position, np.hstack that takes the class probabilities that we have created, and the index -1 shows that it is taking all the values. Then the width is 0.35, then color h color, and same for the second one, that is p2, where we'll use the second class that we have created. And for the bars for voting classifier, we'll use the p3 p4 instance, we'll create it, and ax.bar, where bar is the function that we are using and ax is again the instance, and here the parameters are quite different, that is ind is same, but here we are giving 0 0 0. So instead of hstacks, that is np.hstack, we just given the values as 000 because it is a voting classifier and we cannot use hstag in it for this scenario. So the color is quite different, and now we'll set the plot annotations using the axv line. So it takes the argument as the value 2.8, color equal to k, line style equal to dashed, and then ax.set underscore xticks with ind plus width. So it is a matplotlib function that ticks when the values are true and a minor tick when the values are false. Then set the xtick labels for XGBoost, CATBoost, light GBM voting classifier, and the rotation will be 40. And now we'll give the y limit, that is 0 to 1, plot title, that is class probabilities for sample 1 by different classifiers, then plt.legend, that creates a legend for any plot, so for p1 and p2, and the values given over here is promoted no and is promoted yes, then location is upper right, then plt.tight layout that helps to automatically adjust the subplot parameters according to the padding. Then finally, we'll use this plt.show to show the plot. Now, let me run this. So this is the final step of building our AI model and optimizing it using various feature engineering processes, classifiers, and encoders. So this is the class probabilities for sample 1 by different classifiers. So here the dark green color shows the people who are not promoted and the light green color shows the people who are being promoted. And this is the voting classifier and its average probabilities. So this is the visualization of the probabilities for the employees who are being promoted and who are not promoted, but the actual values we already saw using these classifiers over here. So there are 23,490 records of 2 columns consisting of employee ID as it is unique. So it shows the corresponding ID and the promotion status of the employees. So I'll just go up. So here we have created the model and we saw that the model took 10.4 seconds, and this is the learning of the model we have created. The model using the voting classifiers and XGBoost, CATBoost, Light GBM, gradient boosting or extreme gradient boosting instead of that. And after that we have the results and we worked on improving it. Then we get the result of promoted, and finally we have visualized using the plot our results. So this visualization of the data is just for our understanding, but how actually is the code implemented using the algorithms in real time is by integrating it using other softwares. So company will not use this code directly. So what they will do is they will create the model using the code that we have built, and then what they will do is they might have another application that shows the information of the employees and their various parameters such as age and other things that we saw. Let me go to that section where we have looked around the data. So employee ID, number of training, age, previous year rating. So they might have an application that show the data. So there they can add a feature that predicting the promotion, and whenever they click on that, so this code is added in the backend. So before it shows the prediction of the employees or before it shows the list of the employees, this code is being implemented and the results are shown on the interface. So this is how artificial intelligence or machine learning algorithms helps the company to resolve the issue for their various business problems. So here it is the status of the promotion, whether the employee has to be promoted or not. So it is not about this problem. There are many real life business problems that can be resolved using artificial intelligence and machine learning. So these algorithms and these methods are added in the pipeline of a static software or an application, and it gives the output and the result that is the best prediction according to the analysis using the algorithm along with using the data set that is being provided by the organization, and it makes that software or the application as AI based application. So this is how we implement various scenarios using artificial intelligence.
Just a quick info, guys. Test your knowledge of AI by answering this question. In which of the following application does AI has its expansion? A. Planning and scheduling. B. Game playing. C. Robotics. D. All of the above. Comment down your answers in the comment section below. Whoever gets the correct answers will win 5,000 points in Intellipaat wallet. Subscribe to Intellipaat to know the winners. Now, let's continue with the session.
And then we need to understand why we require artificial intelligence. Guys, again, head to the comment section and let me know your top reasons of why you think we require artificial intelligence around us. I mean, human beings are the most intelligent species out there as of now. I mean, sure, that's debatable, but as of now, that's how it stands. Well, so why do we need artificial intelligence then? Well, let me tell you, humans are the most intelligent beings, but then there is only so much that we can do. For example, consider handling a huge amount of data, right? So in this world we live in, basically we live in a world which is a big data problem. So we have terabytes, we have hexabytes, we have petabytes worth of data coming in from each and every Fortune 500 firm, pretty much every single day, every single hour of every single day, in fact. So this data is growing exponentially, and then when the data is growing at this rate, you cannot expect a human being to be on the other side all the time to handle it. So this exponential growth of data is handled by machines very easily. And then when we talk about the variety of data as well, let's say you need to go on to merge some data, split some data, basically bifurcate some data. There are varieties of data. There's unstructured data, semi-structured data, structured data. So it might not be possible for one human or a team of human beings to basically go on to do this with the amount of data I just told you, right? So when you think about it practically, the variety of sources through which the data comes in is again unlimited almost. So having a machine on the other end of it to take the brutality of the variety of sources, the types of data, the amount of data is going to make life more efficient for the employer as well as the employee. And then we come to processing speed.
If you want to make a career in data science, then Intellipaat has IIT Madras Advanced Data Science and AI Certification Program. This course is of very high quality and cost effective, as it is taught by IIT professors and industry experts.
Yes, again, I'm going to restate the same thing. Human beings might be the most intelligent beings out there, but then we do have machines which can be exponentially faster than humans when it comes to certain basic things, let it be mathematical calculations or anything as such. So this will provide unparalleled performance when we have to compare a human being's work directly to an artificial intelligent being's work. If we have to go on to directly juxtapose them. So this brings us to artificial intelligence developers. Who are these guys and what do they do? Well, you need to know this. Again, AI developers are basically computer science based people, and these people have to do a lot with coding, programming languages such as Python, languages such as R, and many other programming concepts. So why do they need all this programming? Well, this is basically to ensure that they can design, maintain, test, evaluate all the artificial intelligence solutions that certain organizations need. So let's say again, the AI technology which has gone into building Siri at Apple might be extremely different, is definitely very different than the technology which went into Tesla's autopilot, right? So these developers need to understand what the problem is, make sure they can formulate the problem and then formulate a solution for that problem as well, right? So designing a solution for an artificial intelligence requirement, and in fact maintaining that product after it's been designed and evaluating to make sure that it is performing right where it should, is again very important aspects of an artificial intelligence developer. And I have a quick question for you guys on that note. So I'm pretty sure most of you guys use social media, right? It might be Facebook, it might be Instagram, it might be Twitter, and it might be all the other fancy social media apps out there. Coming to Facebook, let's see how AI developers pretty much work out here, right? So AI developers are pretty much responsible again to handle about 350 million photos a day which has been uploaded to Facebook, and they do a lot with face detection and image recognition as well. So let's say you and your friends decided to go on a vacation. Let's say there were 10 people of you and you clicked about 300 pictures. Now imagine tagging 10 of these people in all the 60 pictures, right? So again, 600 tags you have to do manually, and this is going to take many hours if you have to do this. But then Facebook already would understand who the person that is in the picture, where the picture was clicked, and much more. That is what geotagging means, and location options too. So this is told to you very subtle. It says, hey, was the picture clicked here? Is this person that? I mean, it'll show you the name of the person and it'll show you the location as well, and you might be like, yes. So at that point of of time you might not recognize and realize the power that's working behind it to get you all the details, right? Again, and another important thing is automatic friend suggestions, right? So let's say you added someone on any of their other applications. Now Facebook owns WhatsApp and Instagram, so let's say you're in touch with someone on WhatsApp where you've saved their number or something. Facebook will tell you, it'll give you a friend recommendation saying, hey, why don't you add that person on Facebook as well? So imagine all the processing that goes behind this particular thing. I mean, it's so subtle, as I mentioned on the first slide, that we don't even know it's there anymore. And then when you talk about Instagram, see, there are 95 million photos which get uploaded to Instagram, and handling that is definitely a task, right? And the best thing that Instagram is known for these days is customized advertisement. So you go to Amazon, you're searching for the latest mobile phone, or you're searching for a mobile cover, tempered glass, whatever it is. As soon as you come back to Instagram, it's going to show you one advertisement which is beautifully put together. You'll feel like clicking on the advertisement. Basically, that's how customized these advertisements are. And again, face detection and object recognition as well. So
if you want to make a career in data science, then Intellipaat has IIT Madras Advanced Data Science and AI Certification Program. This course is of very high quality and cost effective, as it is taught by IIT professors and industry experts.
That plays a very important role in Instagram. Location recommendation systems, again, it will just tell you where the photo was clicked, what time the photo was clicked, and much more. Friend recommendation again. So let's say again you added someone on Facebook, or you guys just let's say there are two people who use Instagram. You guys have talked on another social media, but then you guys decided to meet for breakfast or dinner or whatever. And as soon as you come back to Instagram, it's going to give you a friend recommendation saying, why don't you add this person on Instagram? Again, how does this work? Artificial intelligence is at play, my dear viewers. And then coming to Twitter handles pretty much 6,000 tweets per second. Again, there has to be some form of pretty much a pipeline, a channel for the data to flow through in and out of the Twitter's storage area, where pretty much they need to understand, they need to work with this data, because it's not all about storing the data when it comes to Twitter, right? Because they perform sentiment analysis of every single tweet. They check if the tweet has a positive sentiment, a neutral sentiment, a negative sentiment, and what pretty much they can check to the depths of what person in which area liked or disliked this tweet on the face of the globe, basically. So this will add power to their organization. This will make sure that marketing can be done using Twitter, and in fact at the end of the day you're bringing more sessions to Twitter and they're happy. Coming to outreach analytics and customized marketing, again pretty much it'll tell you who your audience is, when they're watching your tweets, when they're reading it, and why as well, right? So coming to data analytics, again, you can pull out any number of statistics you want with respect to sentiment analysis of any tweet that's present on Twitter, guys. So think about it. We never knew a simple tweet can have this much of a complex circumstance in the back end when we talk about data and artificial intelligence, right? So this brings us to the most important aspect of this video, guys, which is the skills needed to become an AI developer. And let me tell you about 3 important skills that I think you should have. And the first one is all about mathematics and all about algorithms, guys. Because at the end of the day, you need to understand how numbers can in fact be used to achieve artificial intelligence. There is so much that you might not know, and to the intermediate level viewers, pretty much you will know how much of importance mathematics and statistics play a role. And then coming to algorithms, all the machine learning algorithms are again one step closer to making the machines intelligent. All concepts such as machine learning, deep learning, neural networks, all these work under the same umbrella of artificial intelligence. All of these terms that I told you, all of their goals is to achieve artificial intelligence at the end of the day. So having very good mathematical skills and being well versed with the top algorithms which works with, again, based on statistics, is very vital. And second of the 3 most important skills is probability and statistics, guys. Why did I mention statistics again? Well, it is that important. You need to understand all the concepts, everything from the basics of correlation all the way till how you can basically churn through data and make sure the data will give you insights that the naked eye might not tell you at all. So that is one of the reasons why statistics is extremely important. Coming to the world of probability, again, we need to sometimes understand that the values can be continuous, the values can be discrete. We need to find out what a possibility of occurrence of something is, right? So that again, pretty much an artificial intelligence algorithm of today will not give you 100% accuracy all the time. It will give you an accuracy of 80, 90, 95, 98%. Again, this 98% is 9 on 10 probability, so it says that there are chances that it might fail 2 times out of 100 times. Again, probability, right? So this is a very important second skill to have. Coming to the third most important skill is having the knowledge of a programming language, guys, because again, there are languages like Python and R which form a very strong requirement when you have to learn about artificial intelligence and to help you become an AI developer. And you can either go on to learn Python, you can go on to learn R, but then beginners do prefer Python because R actually has a steep learning curve which some of the beginners might find difficult. But then do not worry, you can pick up either Python or R and you can be on your way to become an AI developer. And then coming to what R is majorly used for, well, R is actually used to do a lot of data plotting, a lot of statistics, and it involves a lot of bringing mathematics and programming together is what I want to tell you guys. And then in a gist again, most of the companies which basically has open positions for AI developers has these roles always present. So you need R and or Python, you're going to need statistics, you're going to need to work with algorithms, machine learning, and so much more. And on that note, here is a step-by-step guide on how you can become an artificial intelligence developer. Let us begin with step 1. Step 1 is pretty much, again, you understanding data structures in detail. You might be wondering why you need data structures, right? Again, if you understand how your data is stored, how your data is talking to the other entity that is present next to it, then you will understand how you can increase the performance of an algorithm by making it, improve itself by drastically changing its understanding of its neighboring data. So understanding the right data structure, understanding when to use what data structure is extremely important. And this is step number 1. Guys, I urge you guys to pretty much whip out your pen and paper or make notes of these, as this will help you a lot in case if you guys are considering to becoming an AI developer. Coming to step number 2 again, as I mentioned, programming. So Python and R are the biggest names when it comes to a programming language to help achieve artificial intelligence. And programming knowledge is vital, guys. It is necessary. There is no work around this, and in fact, it is so much fun to work with, and I've been working on this for a couple of years and I absolutely love it. So, working on Python, working in R, there are libraries for machine learning, there is TensorFlow, there's Scikit learn, there's PyTorch for neural networks, there's CNTK, that's the Microsoft's cognitive toolkit, and there are much more. There is Tafe, pretty much, guys. If I have to go on to naming the frameworks, I can keep on going. So when you think about this, there are so many things out there that you need to know, and this already forms the step number 2. So what comes after this? Well, step 3 is understanding a little bit of mathematics, guys. You need to have some sort of clarity on how numbers can actually be used to drive a data driven entity into making it self-sustain, because at the end of the day, statistics will play an extremely vital role in making sure your machine understands what's going on in it and derive some sort of continuous or differential inferences based on that. And then this brings us to step number 4. Step number 4 is the most important part, ladies and gentlemen, because here again you will be finding a problem. This is how you have to go by with step number 4. Find a problem which needs a solution. Let's say it might be a new startup that your friend is starting, or you just spotted a common problem across your daily life. So find that problem and make sure that you can formulate the problem and understand what the actual problem is. Now find a solution to that problem, and after you found the solution to that problem in a general human way, try to see if you can get the machine to do it. If you can implement artificial intelligence to do it almost as good as you, if not better, then your job is done. But then you need to understand that at the end of it, you becoming an artificial intelligence developer. So telling the world about it is again very important as well. So there is this website called as Kaggle, where pretty much it's an amazing community where people pretty much come together, give out their problems, give out solutions. There are challenges that you can take place in, and basically it's like a GitHub for programmers. Again, GitHub is the same thing, but when we talk about it, Kaggle is a little different, and I'm sure you guys will know how when you go on to explore Kaggle, which is your step number 4. So coming to step number 5. Step number 5 involves you to understand a little bit of cloud computing, because again, in today's world, half of the organizations we see around us are already scaled to the clouds. So everything from Amazon Web Services, we have GCP, which is Google Cloud Platform, we have Microsoft Azure, and much more. So taking artificial intelligence and scaling it right up in the sky through the clouds is now booming. And as my dear viewers, I have to tell you that having a good certification which will train you on all of these concepts is extremely vital. Working on AWS, working on GCP or Azure or any of these, so having cloud computing knowledge and bringing it together with artificial intelligence are very vital. And coming to step number 6. Step number 6 is again an important aspect for an AI developer, because not only you'll have to work with one single computer at point of time, you'll have to work with multiple entities, multiple computers, because at the end of the day, you're going to use this to exponentially increase your computing power. And this is basically done to understand how you can gain some sort of systematic knowledge onto scaling this artificial intelligence entity that you're developing onto a modern infrastructure. This is very vital, guys. So to revisit all the steps, here's a recap. Your step 1 will begin by understanding data structures. Step 2 with a programming language and some libraries. Step 3 is mathematics and statistics. Step 4 is finding a problem, analyzing it, and solving it. Again, the next step involves scaling artificial intelligence to the clouds, and the last step is to understand how you can make use of artificial intelligence on multiple machines at the same time, which is basically distributed computing. And to basically strengthen everything that I've said, here are some of the sample job descriptions that we can check out. So here's a job description for an artificial intelligence developer from the Penn State University in the United States of America. Their requirement is this. They say proficiency in Python is needed, experience with machine learning library TensorFlow, Infinite Cafe is needed, and pretty much they say proficiency in mathematics is needed, as we discussed, linear algebra, multivariate calculus, and much more. Skill is required in JavaScript or R, as we discussed, data structures, and ability to communicate technical topics to the people who might be non-technical audiences. And then cloud computing, AWS, as I told you, right? So we discussed all the 6-7 points, and again, you can see just in one job description, we can see all those 6 points reflecting onto us, right? And then in fact, coming to a researcher's jobs, we just checked out the artificial intelligence developer role. Let's check out the artificial intelligence researcher's role. Again, this comes from the Massachusetts Institute of Technology. It's called Lincoln Laboratory. These guys as well, they require you to have experience in machine learning software, PyTorch, TensorFlow, MixNet, Scikit Learn, and much more. They would appreciate if you guys had experiences in working with large computer vision data sets, experience with big data, Hadoop, Spark, Elasticsearch, Cassandra. You'll be able to work in a multidisciplinary team environment. You have to have very good communication skills, oral skills, and sometimes you might have to travel as well. So guys, when we think about these two job descriptions of an AI developer and an AI researcher, again, when you come to think about it, we have validated all the points that we pretty much just discussed, right? And this brings us to the most important part of our live session, which is pretty much to tell you what the average salary is. So here is the average salary, guys. So pretty much again, when you think about it, the average salary of a junior AI developer is somewhere around $80,000 in the USA, 7 lakhs per annum in India, 45,000 pounds in the UK, and then a senior AI developer has up somewhere around $115,000 in the US, 15 lakhs per annum in India, and 60,000 pounds in the UK, guys. So these are some of the very big numbers that you can see when we talk about AI developers, AI researchers. And then, as I told you, this is a very lucrative career that you can pretty much jump onto, guys. Coming to the first question on these top deep learning interview questions set, the first question is, what are the differences between machine learning and deep learning? This is a very common question that's asked, and it is very important that you know the basic differences that lie between machine learning and deep learning. One very good commonality is that both of these are actually subsets of artificial intelligence, and deep learning itself is actually, a part of machine learning. So when we talk about machine learning, we're making sure that we find a way where we're training machines with a lot of data. We give it some data and we hide some data from it, in fact, and we use the hidden data later, which we also call as the testing data, to make sure that the machine learns something, and to verify if it has actually learned from its experience. When it comes to deep learning, we try to find methodologies and ways where we can sort of trick the machine into making it think like a human being, making it use the human brain structure in terms of working. In the concepts of neural networks, the entire concept is named after neurons and the use of neurons as well, just because how very similar to how it works in the human brain. So this forms to be the basic difference between machine learning and deep learning. Moving on to the second question, it says, what is perceptron? Perceptron is a very important concept in deep learning because it actually matches what we see in an actual neuron in a human brain. So coming to how it works in deep learning, a perceptron actually receives inputs from a variety of entities, and then later it takes these entities, applies some transformations on it, what we call as functions. It applies functions on this, and then it becomes the output. So input, perceptron, applying function, output. That is how the order goes. So if you have to talk about when perceptron is mainly used, it is actually used when we go on to perform binary classification, where we use an input. We try to see if we can classify something based on the output. There's so many factors when we talk about the functions as well. There is weights, there is biases, and there's a lot of things in a neural network in deep learning that has a lot of impact. And in this system itself, perceptrons play a very important role to take an input and transform it and work on it to give you a valid output in the case of classifiers as well. Now, coming to question number 3, it states, how is deep learning better than machine learning? Both deep learning and machine learning are very powerful in their own ways. To solve most of the complex problem in a very simple way, machine learning has got it covered. But then when you talk about deep learning will overpower machine learning, especially when it comes to working with data that has huge number of dimensions. Think about an Excel sheet which has about, let's say, 100 columns with 35,000 entries each, something like that. So when there's a lot of data in your data set and the dimensions are very large, deep learning will be exponentially efficient at working with things than compared to machine learning. So if your data is large, then a deep learning model will work very efficiently to actually solve it, handle it, and it'll make it easier for you to program and work with it at the same time as well. So this is how deep learning is having the upper hand over machine learning in a very simple and a concise way. Now, moving on to the fourth question, it states, what are some of the most used applications of deep learning? Again, this is a very common question that can be asked in your deep learning interviews. So at least make sure you mention at least 3 or 4 fields, and in fact I've put up around 6 fields on the screen right now. Everything from sentiment analysis, mostly Twitter, and all of that. Then we have computer vision to analyze graphics. Then we have automatic text generation, we have object detection, we have NLP, natural language processing, and image recognition. There are more fields. You can name about 10 to 12 offhand if you have worked a little bit on deep learning, but then it doesn't it doesn't really add a lot of value if you just list 10 to 12. So rather, just tell 5 or 6 and just explain 1 or 2 lines about what each of them mean. That way the interviewer has an idea that you are concrete with respect to all the concepts there as well. Now with this, we can come to question number 5 that states, what is the meaning of overfitting? Overfitting and underfitting are actually 2 very common issues that have to be dealt with whenever you're working with data sets and whenever you're working with deep learning. Overfitting, as the name suggests, is a scenario where you have a deep learning algorithm, and your deep learning algorithm is looking very hard into your data, and it is trying to hunt for meaning. It is trying to find some meaningful correlations in between the data in the data set. Now, in a way, what happens in overfitting is that it'll start vigorously hunting for the data, and this makes it pick up noise, what we call as noise, rather than any sort of useful data. So with this noise, it hurts the efficiency, it hurts the detection capacity of the model. So rather than picking up any useful valid information, your model will start picking up noise, and that is not a good thing. So what happens is, at the end of the day, you'll have a very high variance in your data and a very low bias. This way, of course, you would already know that your model will be very, very inaccurate in terms of detection and very inefficient at detecting new things, even if it has a good level of accuracy as well. So when you think about it, overfitting needs to be fixed, and underfitting is just the reverse of this. Anyway, coming on to the sixth question, it says, what are activation functions? Activation functions are very important entities in deep learning, because these are the actual functions that will take your input and make sure that you have something usable on it. So the transformations that happen, right, it is all because of the activation function. So what an activation function is basically is that it has the capability to decide if a neuron actually needs activation or not in that particular array, in that particular set of neurons, to see if there has to be anything modeled from that particular neuron in the chain in the neural network, or if it adds a value to the next set of neurons as well. So this is actually done by calculating the weighted sum of it and then taking the bias as well. So at the end of the day, whenever you're making use of an activation function, the model output will be non-linear. And if you have to talk about the types of activation functions as well, so there's rectified linear unit, or ReLU for short. You have softmax, sigmoid, linear, tanh, and many others as well. So it adds value that you answer it in a way where you tell what activation functions are, how they're calculated, what the output will look like, and what are the types of activation functions as well. With this, we come to the seventh question that states, what is Fourier transforms that is used in deep learning? Fourier transform is very vital to deep learning, because it is one of these packages that is used to manage and work with a lot of data when we work with deep learning. As you already know, in deep learning we will be working with huge data sets, so we need methods and tools and techniques where we can process these in real time, and we can make sure that we can handle it and work with it easily and quickly as well. So Fourier transforms is one of these packages that will make sure that you have high efficiency whenever you're working with data. And with Fourier transforms, your model is now open to a lot of signals where you can have the data processed from multiple entities, and to just make sure that you're opening up a dimension when you're working with the data as well. So Fourier transforms are a very vital part of deep learning. Now with this, we can come to question number 8 that states, what are the steps involved in training a perceptron in deep learning? There are about 5 to 6 steps whenever we have to talk about the perceptron learning, or training a perceptron as it's also called as, and these are the 5 steps. Firstly, the first step is always to initialize all the thresholds and the weights of the network. Then of course we'll be providing the actual inputs. The outputs are calculated based on a lot of things, and we have backpropagation, all the algorithms that run in the back end, and after which we'll have the steps where we'll be upgrading the weights in every single step. So after the weights are upgraded, then we'll again provide another set of inputs. We'll be calculating the weights again, and this goes on from the starting initial node all the way till the last node of the output neural network. And this is how simple it is to actually train a perceptron in deep learning. Now with this, we can move on to the 9th question that states, what is the use of the loss function? So whenever we talk about neural networks and deep learning, we need a methodology, we need a number, we need a numeric, where we have the ability to see if the model is working towards its goal or not, right? So the loss function is a measure of accuracy here as well, because we're trying to see if the neural network actually learned something useful from the data or not. And a loss function is a negative metric, where if the loss function's value is less, then it's good for the model. If the loss function value is high, it means that the model is not performing well. So at all times, it is very vital that you mention that the loss function has to be kept to a minimal extent. Now with this, we can come to the 10th question that states, what are some of the deep learning frameworks or tools that you have used in the past? Now this is a very common question that's asked in the interviews, because they want to find out, the interviewers want to find out about the experience that you have with all of these tools. So just make sure to mention of all the frameworks, tools and techniques that you might have used in your projects or your certification programs, or whatever it is that you have used, the methodologies that you have used to learn. Of course, there are many top deep learning frameworks out there. We have an entire video on that on the channel as well, so make sure to check that out after this video. Among the top deep learning frameworks, we have TensorFlow, we have Keras, we have PyTorch, we have Cafe2, we have CNTK, that's Microsoft's cognitive toolkit. Then we have MXNet, we have Theanon, we have many others. In fact, you can list about 12 to 15 very good top deep learning frameworks out there. But then just make sure to mention 3 or 4. But then if you of course used more than that, then do make sure you mention that as well. But then make sure that you are very honest about it, and do not I would suggest that you do not state a deep learning framework that you might have not used, as that might lead to you being asked questions on that, and you not being able to answer as well. So make sure to take care about that. Now with this, we can come to the 11th question that states, what is the use of the swish function? So the swish function is nothing but an activation function, as we discussed a while ago. So it's something called as a self-gated activation function, and it is developed by the people at Google. So one thing to note about the swish function is that it is extremely popular because Google has put up a very good claim that it outperforms all of the other activation functions that exists today in terms of efficiency. So we discussed the different types of activation functions as well, right? Tanich, Relu, and all of these. So then Google came about, they devised an algorithm, the activation function algorithm, and they put up saying that this will outperform everything else that already exists. So that is one of the reasons why this particular activation function has seen so much limelight as well.
Just a quick info, guys. Test your knowledge of AI by answering this question. What is artificial intelligence? A. Putting your intelligence into computer. B. Programming with your own intelligence. C. Making a machine intelligent. D. Putting more memory into computer. Comment down your answers in the comment section below. Whoever gets the correct answers will win 5,000 points in Intellipaat wallet. Subscribe to Intellipaat to know the winners. Now, let's continue with the session.
Now with this, we can come to the 12th question that states, what are autoencoders? Autoencoders itself are artificial neural networks, and this is something which is very important that you know. And of course, they do not have any supervision, as they have the ability to automatically try and map inputs and to find out outputs and work with it on their own. So it's a very interesting concept to work with autoencoders, and these are very efficient as well. But then when we talk about autoencoders, it is very vital that we talk about two important things. One is the encoder and one is the decoder. These two are the very important entities that we have to discuss about. An encoder will make sure that the input is taken and it is converted into a format which is understood by the neural network, into an internal computation state, of course. And then we have the decoder, which does the exact opposite of this. It will take the computational state data and it will make sure to convert it back into the output. So encoders, even though the name only has encoders, there are two operations that's going on. One is the encoder operation and the other one is the decoder operation. Now with this, we can check out the 13th question that states, what are the steps that have to be taken whenever you make use of a gradient descent algorithm? There are actually 5 to 6 steps that have to be discussed whenever we talk about initializing and making use of the gradient descent algorithm. The first step is always you have to initialize all the biases and weights for the network as well. And after you have initialized all the biases, you have to send the input data throughout the network, which forms to be, of course, the input layer, the first layer of your neural network. And then we'll actually calculate the loss function, right? So you'll have an expected value that you're expecting at that point of time, and there will be a value which is predicted by the model as well. So calculating the difference between this will give you the error of how far away the neural network is from the actual goal. Now, after that, you will actually change all the values in the neurons to make sure or to find ways where you can minimize this loss function, this difference that we just found out in step 3. And after which, of course, this entire process is an iterative process. You'll be looping it and doing across multiple iterations to find out what biases, what weights, and how best you can do to keep the loss function at its minimum. So these are some of the steps that have to be followed whenever you're working with gradient descent algorithm as well. So with this, we can come to the 14th question that states, differentiate between a single layer perceptron and a multi-layer perceptron. We already discussed that, if we're talking about a perceptron, in case if it's a single layer perceptron, it will not have the ability to classify non-linear data for us, but then a multi-layer perceptron completely can, classify non-linear data. And a single layer perceptron is a bit limited in one aspect where, the number of parameter that it takes in is very less when you compare to a multi-layer perceptron. And this in big deep learning models can have a very, very, disastrous effect as well for efficiency, for effective working and whatnot. So again, for the second point, I think multi-layer perceptron wins. And when you talk about the third difference, of course, a single layer perceptron has many things that it can do well, but if we are talking about efficiency when making use of large data, well, again, a multi-layer perceptron of course takes the higher end because it is extremely efficient to work with in the case of large data sets. Now with this we can come to the next question that states, what is data normalization in deep learning? So data normalization is a very, very important step. It is actually a pre-processing step where we try to make sure, we can move around the data, rearrange the data, and we can make sure to refit and pack this data into one particular range. This is the entire process of normalization. Why we do this is to make sure that, if your data is in one particular range, it means that your network has the ability to learn very effectively and be very efficient as well. So, when you're performing steps like backpropagation, having a data in a very structured range, a specific range, will make sure that your network can learn that much faster as well. So these are one or two reasons why this pre-processing step that we take called as data normalization is very important. Now with this we can come to the 16th question that states, what is forward propagation? So backward propagation is the scenario where we work from the output layer to the input layer, and here in forward propagation it is the exact reverse. We follow in the order of the neural network. So we go from the input layers to the hidden layers and then the output layer. So when you're talking about a complex neural network, there'll be more than one hidden layer. So for every hidden layer, the output of the activation function is actually calculated, and this is done until the next layer can actually be processed. The reason they call it forward propagation, as I just mentioned, is to make sure we work from the input and towards the output. And this is the exact opposite of the backward propagation algorithm as well. So to make sure that we use the output of the activation function and to calculate it for the next layers, forward propagation is very, very important. Now with this we can check out the 17th question, again coming back to the very main important question. Your interview could start with this question itself. What is backpropagation? So backpropagation, instead of talking about what, the first thing you have to always discuss is why backpropagation is even important, right? So it is to make sure that we keep the loss function or the cost function less, and to see how the values changes whenever we work with a variety of biases, a variety of weights. Whenever we change all of these, even a slight change can have a very big impact on your model. To understand how these work, we require the backpropagation. It's called backpropagation, of course, because it starts from the output layer, works backwards towards the input layer direction. So how is backpropagation calculated? Well, it is very easily calculated whenever you work by understanding the gradient that is calculated at every single hidden layer itself. So it's as easy and straightforward as that. Now with this we can check out the 18th question that states, what are hyperparameters in deep learning? So when you talk about hyperparameters, even though the term is very complex, they're nothing but variables that are actually used in deep learning to actually determine the structure of a neural network. So these variables are put into place to make sure that we have an easy way of understanding so many different factors and parameters in the deep learning model, be it the number of hidden layers that are present, or the learning rate of the model, and much more. So hyperparameters are very important variables that will give us a lot of insight into how the model or the neural network is functioning as well. So moving on to the next question, it states, how can hyperparameters be trained in neural networks? So training a hyperparameter is very important, and understanding how you can convey this to the interviewer is also very important, because these are long procedures and your ability to concisely answer it is very important. So, to train a hyperparameter, we'll require 4 very important components. It's the batch size, the number of epochs, and there's something called as the momentum, and there's a metric called as the learning rate. So what happens in batch size is that we'll take the input, we'll split it into batches. Batch size can be varied depending on however it is required based on the efficiency and a lot of other things. These batches can be cut into further sub batches as well, if that is the requirement. So instead of pushing all the input into a concurrent pipeline, we just make sure to dig it up into batches and then vary it across. Now when you talk about epoch, An epoch is basically a denotion of how many times the training data is run through the neural networks where it can train. So the number of epochs is the number of iterations at which the model, the neural network trains as well. So it's an iterative process. The number will depend on so many different factors. Doesn't mean that if you have a large number of epochs that your model will be very, very accurate with every single iteration. It will go up to a point, and then of course your model will work in fact in the opposite direction. Now, when you talk about momentum is actually put into place where we have an idea to check out what happens in the next consecutive steps. Whenever data is being moved around in a neural network, it is vital to understand what happens next, right? So, there is no point if your model is very inefficient where it's passing around data and not driving any momentum from it. So momentum is this particular track where we make sure we understand what's happening next as well. Now, coming to the last component, it's a very important component. It's the learning rate. Learning rate is what we are all after when you work with deep learning, because this is used as a very important parameter where we're trying to denote what is the time that's required to actually update all the parameters when your model learns and when your neural network is ready to take in certain inputs and give you meaningful outputs as well. So these, four form to be very, very vital, very important components in the world of deep learning whenever we go on to train hyperparameters. Now with this, we can come to the 20th question that states, what is the meaning of a dropout in deep learning? Now, dropout might seem like a very common term, but it is actually a technique in the world of deep learning. Dropouts are a very important technique, in fact, because these are used to avoid overfitting. Overfitting and underfitting are common problems, as we discussed a couple of questions ago. So to avoid overfitting, to make sure that your model doesn't hunt for noise, what we actually do is, we purposefully remove a bit of data which might not be useful for the model to learn as well. So if you have a dropout value to be very low, it will have a minimal effect on learning because you're not removing enough data and your model can still go towards overfitting. But then if you remove a lot of data, then what will happen is the model will not have enough data to learn. So it will underlearn and then cause inefficiency as well. So this value, right, this drop off value should be very, very vital, because if you have it too low, it will not have an impact. If you have it too high, then your model will not learn effectively anymore. So understanding this is a key concept. Now, coming on to the 21st question, it states, what are tensors? Tensors, you might have heard of these. These are another name of arrays, guys. So tensors are actually multi-dimensional arrays that are mostly used in deep learning, where we have to represent data across either one dimension or in fact multiple dimensions as well. So why can't we just call them arrays and not tensors, right? So tensors have the specialty of a name because they have been very famous. They have been very vital whenever we work with data of higher dimensions. So one very big advantage when we talk about tensors is that whenever we make use of it in any of the programming languages, right, the syntax is very readable. It's a very high level syntax. So what that does is it gives us a clear picture of tensors, even though if we do not have very high amount of training in terms of making use of tensors or its terminology. As soon as we look at the programs, we'll have a keen idea about what tensors are and what they might be doing in the program as well. So this is one very good advantage when it comes to working with these multidimensional arrays called as tensors. Now we can move on to the 22nd question that states, what is the meaning of model capacity in deep learning? Model capacity is again a very important metric that we have to discuss about, because model capacity deals with the capacity of the model to actually take in a variety of mapping functions. So how many mapping functions can your model handle? How many can it concurrently work with as well? One thing we drive out of this metric is that higher the model capacity, it literally means that there is a large amount of information that can be stored and worked with in the network. If the model capacity is low, as the name suggests, it means it cannot handle and effectively a large amount of information at a time as well. So model capacity is something which is very straightforward, but yet it forms to be a very important concept in deep learning. Now with this, we can come to the 23rd question that states, what is the Boltzmann machine? Boltzmann machine sounds very complex, but it is actually a type of a neural network, that we call as an RNN, or a recurrent neural network, where we make use of binary decisions, biases, and to do a lot of functioning and working for us as well. So Boltzmann machines are, like as I mentioned, RNNs. They are hooked together to create something that we call as DBNs, or deep belief networks. So these deep belief networks are extremely sophisticated. They have multiple number of hidden layers, and they're put into place because we have complex problems that require effective solving. So the entire goal of deep learning, in fact, is that we have extremely complicated problems and we need to find ways to make use of the power of computing to simplify that to a good extent for us, and a Boltzmann machine will do exactly that. Now, after understanding this, we need to check out what are the advantages of making use of one of the top deep learning frameworks out there called TensorFlow. So, of course, this could be a very important question in case if you work with TensorFlow, because understanding the advantages of it is very vital. So TensorFlow has many advantages, and to me the most important advantages where it will give you a lot of flexibility and platform independence whenever you're working with it. The platform independence is very vital because we all have multiple operating systems, multiple platforms that we work on, and of course, so it has the ability to power through and train on both CPU and your graphical processing unit as well. And with new technologies with GPUs, it just makes it very efficient to work with tensors too. And then when we talk about auto differentiation and the features it brings with it is again a huge impact. When we talk about threads and its ability to handle asynchronous computation, this is where TensorFlow wins over many other deep learning frameworks as well. The second most important advantage to me is that it's open source. It has a beautifully large community, so you don't have to pay for it, but then at the end of the day, there are so many things that are being added in terms of features, technologies, fixes, and so much more. And this entire community of open source is just a beautiful thing, and I'm sure you can relate to this if you work with TensorFlow as well. So with this, we come to the 25th question that states, what is a computational graph in deep learning? So a computational graph, as the name suggests, is a scenario or is a graph itself where we try to take inputs, arrange them into meaningful entities called as nodes, and later create a graph structure out of it. So these are done to simplify certain mathematical calculations as to visualize them better. So in terms of deep learning and in terms of backend functionality, it helps a lot whenever we're working with parallel processing, as it provides a huge performance boost over a single threaded performance in terms of making use of actual computational graphs, as your processing power is now 2, 3, 4, 5 or 10 times 10 folds better than how it was before as well. So computational graphs are very important units when it comes to working with deep learning. Now we can come to the 26th question that states, what are CNNs? CNNs and RNNs.
If you want to make a career in data science, then Intellipaat has IIT Madras Advanced Data Science and AI Certification Program. This course is of very high quality and cost effective, as it is taught by IIT professors and industry experts.
Are very different types of neural networks. CNN stands for convolution neural network, while an RNN stands for recurrent neural networks. Now, coming to the talk of CNNs, CNNs are mostly used to perform visual analysis or working with a lot of images and classification as well. You can have multiple images of many channels as well. So when we talk about images and channels, mostly we talk about colored images and black and white images. Colored images will have like 3 channels, red, green, and blue, RGB structure, and so much more as well, right? So a CNN has the ability to easily work with, classify, and give you meaningful outputs on all of these images and visual data. Now, if we talk about a little bit more about CNNs, the next question can be saying, what are the various layers that are present in a convolutional neural network? So when the talk is of this, understand that there are 4 important layers in a convolutional neural network. One is the convolution layer, we have the ReLU layer or the activation function layer as it's also called. Then we have the pooling layer and the connectedness layer. So when we talk about the convolutional layer, this is where we apply things and entities called as filters across the main data to have them as parameters to teach and train the network. So after the convolution step is done, we'll use the activation function to squish it and bring it into a range which is workable and understandable by the neural network. After the activation function is done, then there's something called as pooling. Pooling is where again we shrink the data to make sure we are not losing any of the existing data, and what happens after convolution is we lose certain data as well. So we do stuffing in the pooling layer as well to make sure that we add certain bits, dummy bits, to make sure that the size of the image is actually maintained after every single iteration. So with every iteration the image shrinks a little, and with padding we make sure that we are not letting it shrink out of context as well. And then when we're talking about the fourth important layer of the convolutional neural network, it's connectedness. Here we're just making sure that all of the activation functions are applied correctly by making use of the bias, and generally checking that the entire neural network is connected thoroughly and it's working as expected as well. So as the name suggests, this is a very important layer to verify the understanding of the neural network. So these are the four very, very important layers that you have to know about in this particular order itself. Whenever you're mentioning the working of it, the questions can be like, what is the working of a CNN, or what are the layers that are present as well. So this will develop as both of those questions. Now, when you talk about RNN, as I just mentioned, next question can be, what is an RNN in deep learning? So RNN, as I discussed, it stands for recurrent neural networks, and unlike CNNs, the working here is very different. The use of it is very different because RNNs, or recurrent neural networks, are very, very efficient at working with a lot of string data, textual data, genome data, handwriting data, and much more. So if you have already worked with any basic use cases where you're performing, let's say, handwriting prediction or detection of handwritten letters or whatnot, then there's a good chance that you've made use of an RNN. RNN uses the technique called as backpropagation that we've already discussed for all its training requirements, and it is very, very effective at doing this as well. Just like how CNN is very effective for working with images, it shows similar girth whenever you're working with textual data as well. So this is again a very important aspect in deep learning. Now with this we can come to the 29th question that says, what is a vanishing gradient whenever you make use of recurrent neural networks? A vanishing gradient, to be honest, can be considered as a scenario, because we already saw in the last answer that RNNs make use of backpropagation, right? So if there is backpropagation, then there's the calculation of the gradients at every single step. And whenever we work with backpropagation, whenever we calculate gradients, they tend to get smaller and smaller as the data works backwards from the output layer to the input layer. So since the value becomes extremely smaller towards the end as we approach the input layer, it causes a problem. So this basically means that your model will learn very slowly and it cannot be efficient. It will underlearn sometimes and it will cause a lot of problems. So this is a scenario of occurrence where your gradient values are becoming very low, and that scenario is what we call as the vanishing gradient. Now, I hope this is clear. So with this, we can move on to the 30th question, which states, what is exploding gradient descent in deep learning? Just like vanishing gradient, exploding gradients are another issue which work in a very different way, because here is a scenario where we're clumping up all of the gradients. Means what it does is it will create a large number of updates for all of the weights in the model whenever it's training. So your model weights are being updated constantly, more than required, and and we already know the working of gradient descent, right? So it's based on the condition to keep all of these updates small to make sure that your upgrades are controlled, and only then can your gradient descent have some meaningful impact on your deep learning model. So with this, we have to understand that whenever you control these updates that happen to the weights of the model, right, this will have a huge impact, in fact direct impact on the efficiency of the model as well. So this is another scenario, what we call as the exploding gradient descent, where we have large number of updates that happen to the weights, which make it very, very inefficient at the end of the day too. Now with this, we can move on to the 31st question. So the 31st question states, what is the use of LSTM? LSTM is again a very important type of recurring neural network that we use to perform a variety of operations whenever we work with textual data and string data, as I just mentioned a couple of slides ago. So it stands for long short-term memory. And the working of it is slightly different because it makes use of something called as feedback chains, where it gives the network the ability to perform like another general purpose computing entity as well. So when it comes to that, it is very efficient at working working with a lot of data, especially when we're talking about genome data and genomic sciences. LSTMs are very efficient at working with that as well. So again, just being a type of another RNN, it sort of trickles down to having all of the features and the general working of RNNs too. Now with this, we can come to the 32nd question that states, where are autoencoders used? So we checked out autoencoders before, but then there might be a follow-up question to that stating where they are actually used, right? So you have to understand that autoencoders again have a lot of usage in the real world. So whenever we talk about it, you can have about 10 to 15 uses that you might know already, but then it is vital that you at least mention 3 or 4 very popular applications of it as well. So let's say in the real world, if you have a black and white image and you want to have it colored out to what it actually was in its real life, then adding color to black and white images are very important use cases. And if you have any other old images where you have to remove noise, autoencoders are used here too. And then when you talk about dimensionality reduction and feature removal or feature variation as well, autoencoders seem to be very popular. And in fact, more than popular, they're popular for a reason, that is because they're efficient at handling all of these tasks. So make sure you mention all of these real life applications which are very popularly used as well. So with this, we can come to the 33rd question that states, what are the type of autoencoders? So, there's actually 4 types of autoencoders that you have to mention. One is the deep autoencoders, we have convolutional autoencoders, we have sparse autoencoders, and of course, we have the contractive autoencoders as well. So you really don't have to explain when you're asked for the types, but then it might add value if you can just state 1 or 2 sentences about each. But then it is very important that you mention all the 4 types that exist for autoencoders as well. So moving on, we come to the 34th question that states, what is a restricted Boltzmann machine, or an RBM for short? An RBM is actually a graph, if you have to talk about it in general. It's a graphical based model that we make use of in deep learning today, and it does a lot of things and can do a lot of things efficiently as well. So when you have to talk about performing operations such as classifications, or let's say regression, dimensionality reduction, be it collaborative filtering, topic modeling, or all of these operations that need to be performed that require an algorithm to do it, an RBM can do it very effectively in today's world of deep learning, where it can make use of the computation power of today and work with it effectively as well. So an RBM is again a very, very important, I know there's a lot of efficient being used in the case of deep learning, but then of course an RBM is very tricky to work with at the same time, but then the output that it provides is worth the effort. Coming to the 35th question, it states, what are some of the limitations of deep learning? We've been talking about advantages for 34 questions now. So it is very vital that you know what some of the limitations or the disadvantages are. There are not many disadvantages, but then there are a few disadvantages as well. The first one is, whenever you expect very good, very accurate output, you need large amounts of data, and your network has to have the capability to work with large amounts of data effectively as well. So that is one disadvantage. To gathering all the data might not be the case in all the factors. And then when we talk about how complex it is to implement, for example, an RBM is pretty complex for a beginner to work with and to get it working efficiently as well. So in a couple of cases, not just RBMs, RBMs might be easy to you, but then there are many concepts where it can be a little convolutional, it can be a little confusing, and it can be a bit complex to work with as well. So that is one of the disadvantages. And just like any other deep learning concept, your main focus always will be to make sure that your models are very efficient. So you'll be hunting on keeping that loss function down. You'll be hunting on making sure that your goal parameter is being met, and it is being met in a way where your model is very accurate. It is not overfitting a lot, it is not underfitting a lot, and it is performing as it should at its best. So hunting for these can take a lot of time, and it is not as simple as it's put out as well. So in case if you have had first-hand experiences working with deep learning, you will know what I mean with this. Now, we can come to the 26th question that states, what are the varieties of gradient descent that are available, or what are the variants of gradient descent? There are actually 3 very important distinctions whenever we talk about gradient descent. One is the SGD, or the stochastic gradient descent, then we have the BGD, or the batch gradient descent, and then we have the mini batch gradient descent. And whenever the talk is about stochastic gradient descent, the first important thing is that we only make use of one training example, and we calculate gradients based upon that. We update all the parameters based upon this single entity, this single example that we have. But then this is not the case when we talk about batch gradient descent, because once we calculate a gradient for batch descent, as the name suggests, we'll take the entire data set and calculate the gradient for all of the entities that are present in that data set, and then of course we update all the parameters one after the other in every iteration as well. And mini batch is again very similar to batch gradient descent, but then the batches itself are broken down into digestible pieces, or small sized chunks, or small sized batches as it's also called, and then work with it just like how if it was a stochastic gradient descent, where we again take a simple training example and we make sure that we calculate gradient, update all the parameters, and perform the same operations for different values across a variety of iteration as well. So these are some of the 3 important gradient descent, stochastic gradient descent, batch gradient descent, and mini batch gradient descent that you have to mention when you ask this question. So with this, we can check out the next question that states, why is mini batch gradient descent so popular? So why is mini batch so popular, right? So this is again a question that's asked a lot. In fact, it's a very frequent question if you talk about the previous question or a follow up to that as well. So one reason why it is popular is, of course, because it is very efficient when you directly compare it against stochastic gradient descent. And when we talk about avoiding the concept of local minima, mini batch gradient descent will help, because we'll be approximating all of the gradient values for the entire data set. And this is done because we use a concept called as generalization rather than hunting for specific values every single time by doing this concept where we're finding the flat minima and working with it. So what this does is this will make sure that we can avoid the local minima, we can approximate the gradient for the entire data set by the process of generalization, and it can be done very easily as well. So it packs a punch without having much effort into it. So that's one advantage of mini batch gradient descent. Now with this, we can check out the 38th question that states, what are deep autoencoders, right? So we checked out regular autoencoders. So what are deep autoencoders? Deep autoencoders are actually an extension of the regular autoencoders that we just checked out before. So here the difference lies where, the first layer is actually responsible for what we call as the first order function of the input. And if you have a second layer, then the second layer will take care of what we call as second ordered functions. Third layer will have a third order function. Fourth layer will have fourth ordered functions, and so on. So it goes on like that. So when we talk about a deep autoencoder, it is basically a combination of making use of two or more symmetrical DBNs that we discussed, right? So DBN is a deep belief network. So here in an autoencoder, we'll combine two or more of these deep belief networks, where let's say the first 5 layers is considered as the shallow layers, which will take care of the encoding aspect of it, and the last 5 layers, or in fact all of the other layers, can handle the decoding part as well. We checked out that encoding and decoding are two very vital aspects of autoencoders, and this is where deep autoencoders shine, and how they are complementary to the regular autoencoder as well. So with this, we can come to the 39th question that states, why is the leaky ReLU function used in deep learning? So ReLU stands for rectified linear unit. So leaky ReLU is also called as LREL, in case if you're asked about LREL, make sure to understand that it is the same as leaky ReLU. So, we use leaky ReLU in a concept, let's say, where we have the input values, and if they, if the input values are all less than 0, right? So what we try to do is we allow the passage of, small sized negative values to the function, where we use it to actually manage the function, work with it, and then, to drive the activation based upon that as well. So whatever neurons require activation, if the values are less than 0, leaky ReLU is very popular there, which will allow the usage of small negative values and drive meaning out of that at the end of the day. So after understanding leaky ReLU, it becomes very vital that you check out some of the examples of supervised learning algorithms. So, this is a machine learning question, but then we've seen this has been asked a lot in deep learning interviews as well. So what are some of the examples of supervised learning algorithms in deep learning is the question. You have to understand that there are 3 main supervised learning algorithms in deep learning. One is ANNs, artificial neural networks, then you have CNN and RNN, convolutional neural networks, and recurrent neural networks respectively. So you have to mention the 3 types or the 3 main supervised learning algorithms usages in the field of deep learning as well, and these will cover all of the subfields that come under them. CNN has a lot under it as well. RNN has a lot of types, as we just checked out in the previous set of questions, but then mentioning these 3 should be more than sufficient. Now, there can be a follow-up question to this stating, okay, what about unsupervised learning algorithms? Can you state examples of that in deep learning? Well, yes, there are 3 very main important unsupervised learning algorithms in deep learning. We've checked all of these out. One is the autoencoders, then we have the Boltzmann machine, and of course we have something called as self-organizing maps as well. So these 3 form to be very, very important unsupervised learning algorithms that find a lot of usage in the real world when we make use of deep learning and its concept too. Coming to the 42nd question, it states, can we initialize the weights of a network to start from 0? Can the weight be 0? The answer is very tricky. You might be leaning to say no, but then understand that the answer is yes. It is actually possible to start with zero initialization, but then of course it is not recommended to use, because setting it up to zero will make sure that your neurons will be giving the same output and the same descent and the same gradients whenever we go on to make use of back propagation. So the learning is almost next to zero or next to nothing here. What this means is that your network cannot learn at all if we start with zero, because there is no asymmetry, right? So each of the neurons have to be unique from each other, and they have to do a unique task that is assigned to them. So if everything is set to zero, then when we work with back propagation, there is no way to tell apart from one neuron to the other. So the learning rate is zero, as I just mentioned, and it really doesn't work. But then yes, it is of course possible where you can have zero initialization done to the weights before working with the network as well. So after understanding this, it becomes very vital that you understand something called as same padding and valid padding in CNN. So you remember CNN is used for image classification as well, and padding is done as a part of working with images. So whenever we perform iterations, with every iteration the images are being shrunken in size. To make sure that they're not shrunken beyond usage, we do padding where we apply more dimension to the existing matrix, right? So there are two types of it. One is valid padding and we have same padding. Valid padding is where it is used where where there is no requirement for padding actually. So the output matrix will have the dimension n minus f plus 1 multiplied with n minus f plus 1, which happens after the convolutional state. And with case of same padding, padding elements are common padding elements in fact are added across all of the output matrix as well. So same padding is a situation where we try to match the dimension of the input matrix as well, but then valid padding might not be matched because it can have its dimension on its own, which is calculated by the formula given there as well. So same padding will try to match all of the elements after padding to make sure that your output matrix will have the same dimension as the input matrix. So that is the basic difference that lies between valid padding and same padding. Now, it is very important that you might be asked this question, so make sure to concentrate on this as well. So what are some of the applications of transfer learning in the case of deep learning? Transfer learning is a very popular scenario where we take a large model, we train it with a huge data set, yes, of course, and then we make sure to use this model, which has learnt on very complex data, large amounts of data, to work on simpler data set. So what this does is its efficiency is boosted to a very high extent because it has actually trained on complex data, but it is now working on simple data. So this way it is very efficient, it is very accurate, and in fact transfer learning is being implemented in our daily lives very well as well. But then if you have to talk about the complex use cases of it, we have BERT, we have ResNet, we have GPT-2, we have VGG16, and many other popular examples of where transfer learning are made use of and how efficient and effective they are as well. But then understand the basic working of it. So you train your model on something very complex, but then you actually show simpler data to it at the end of the day where it can work with it effectively and be more efficient too. It's as simple as that. Now with this we can check out the 45th question that states how is the transformer architecture better than recurrent neural networks in deep learning? So, whenever we make use of something called as sequential programming, there are two important things you have to be concerned with. One is how much of processing power you're making use of at every single point of time. And so what is the difficulty that you're facing whenever you have to work with parallel execution, right? So sequential processing will raise these two red flags. And what this does is this actually gave away these two concerns were the primary reasons why we have something called as a transformer architecture now. So in a transformer architecture, we have something called as the attention mechanism. The attention mechanism will take all of the dependencies that are available and it will map in between each of the sentences whenever things have to be processed as well. So when we talk about concepts such as NLP, right, natural language processing, here since the data is mostly sequential, it'll of course bring up the two concerns as mentioned above. But then by making use of these attention mechanism, by mapping all of the dependencies, by making sure your model can recognize these entities faster and map it across to a dictionary faster, let's say, then transformer architecture is very effective as you can think about it. So with this, we can check out the 46th question that says, what are the steps that are involved in working with an LSTM network, long short-term networks, as we discussed in a couple of questions before. So, whenever you're working with LSTM, there is three important steps that you have to think about. The first step is concerned with the network actually picking up all of the information, where it has to remember certain things, it has to identify what it has to not remember and what it has to process as well. So that is the first step, where your network has the capability to know what it has to remember and what it has to forget. And then when we come to step number two is where we actually update all of the cell state values, but then updating all of these will depend directly on the outputs of the step one, because depending on what information needs to be remembered or not, the cell state values are updated based on that. The third step, in fact, also depends on step number two, because here what we're trying to do is getting the network to calculate and analyze what is the current state, and which part of the current state should in fact make it to the output and which should not as well. So the most important step is step three, but then without step one and step two, it is very difficult to directly move on to three, because you will need what is vital and what is not. Then you have to update the cell state values based on that, and lastly you have to make sure your network analyzes and calculates which part of the current state should make it to the output and which part should not as well. So these are the three steps that are very vital in the working of an LSTM network. Now we can come to the 47th question that states, what are the elements in TensorFlow that are programmable? So what are the programmable elements whenever you're working with TensorFlow as a deep learning framework? So the answer is very simple. It is very straightforward. In TensorFlow, all the users have the ability to program three main elements. One are the constants, one are variables, and one are placeholder entities. So these three entities are very important that you state out explicitly, because these are the entities that you can program explicitly, program manually, and work with them, depending on whatever model it is that you're working with as well. So after understanding this, we have to check out one more small concept called as bagging and boosting in deep learning. So the question can be, what is the meaning of bagging and what is the meaning of boosting in deep learning? So what happens in bagging is that, we actually take a data set, we split the data set, and we randomly shuffle around, move the data into multiple batches, or in fact we call it as bags, since the term bagging is used, and we use it to train the model as well. And then boosting is a different scenario where we take incorrect data points and we force a model to actually produce a wrong output. We give it a wrong input, we make sure it gives the wrong output. So this way the model has the capability to understand that, okay, this is wrong, and then it can retrain itself and increase accuracy as well. So this is a negative way of teaching the model, but then it works very, very well. If your model can understand what is wrong, that means that it knows what is right. So this way, making use of bagging, where we're splitting the data set, or making use of boosting, where we are giving it the wrong input and the wrong output derived from it to teach it better. Both of these are helping very effectively in the case of working with deep learning as well. Now with this, we can come to the 49th question that states, what are GANs or generative adversarial networks as well? So GANs are again very, very widely used. They are used to achieve this concept called as generative modeling in deep learning. What it is that it is an unsupervised task that basically is involved in a lot of pattern detection and pattern hunting in the data. So whenever we have an input data, we try to see if we can find out any patterns in it and make sense of it and convert it into a meaningful output. So GANs are very, very useful for this. So the generative part of it comes from the generator, where it is used to generate more than one example at a time, while we have another entity called as the discriminator. A discriminator will classify the examples which get generated by the generator. So the two entities, generator and discriminator, and it would add some value to your candidature if you actually mention these explicitly to the interviewer as well. So GANs are again they're very widely used, because whenever you think about it, everything is pattern detection in today's world, right? So GANs have a lot of implementation and a lot of requirement by us as well. Now with this, we come to the last question that states, have you earned any sort of certification to improve your learning and implementation process? Well, the answer to this is very important, because as you might already know, a certification program can give you a lot of advantages. Structured method of learning, a lot of use cases, real-time projects, expert guidance, live classes, and to you this is fine, but then to the interviewer, what they are trying to understand from your certification program is with the certification program, you are trying to show that you want to exceed in your career, that you want to build something, that you want to advance in your career. That is the first important point. The second important point is that, let's say if you're a fresher, if you learned it all on your own without having to learn it in college or something, that shows grit, that shows aspiration. And if you're a person who's moved from another programming language to come into the field of deep learning as well, that again shows very strong aspiration, that you are willing to put some time and effort, and that you've already put time, effort and money into learning all of these as well. And at the end of the day, that adds up to a concept where you're proving yourself to the interviewer that you are effective at what you do and you want to do this. So one very important thing that you have to know whenever you're talking about certification programs, right? So yes, you can list all the certification programs that you have had, but then what will add the most value is to tell the interviewer what you learned and how you used your learning to implement something new. See, because not just certification, any IT concept in the world, right? So we're trying to solve a complex problem using a simpler thing. So we're trying to make the complex problem very simple. So how have you taken a complex problem, how have you worked on it, and how have you simplified it by making use of your certification program is very important to the interviewer, and that is what you should talk about. Explain what you learned from it, explain how you learned and what you took away as well. And here is a small bonus for you guys. Apart from this, what would add a little more value is to make sure that you mention that that you're planning to use your learning in this particular way for that particular company that you're applying for, right? So you would have learned a lot of things. If you put it out in a way where you're telling the interviewer that, hey, I learned all of these and I think I can use it this way to help your company, that will impress the interviewer as well. So that is one very important way on how certifications will help you rapidly increase your career's dimensionality, basically. Well, with that, you have reached the end of this top deep learning interview questions. I take this opportunity to wish you all the best for all the interviews ahead. So you make sure to use this guide to understand how you can approach the questions effectively and how you can answer them precisely and with as much content and quality as possible.
If you want to make a career in data science, then Intellipaat has IIT Madras Advanced Data Science and AI Certification Program. This course is of very high quality and cost effective, as it is taught by IIT professors and industry experts.
Now that we are done with the session, don't forget to subscribe to Intellipaat and press the bell icon to get the latest updates on Intellipaat.